Department of Material Science and Nano Engineering, and a professor of chemistry. Professor Lowe was an young investigator award. He has got a FOSR and the recipient of Charles Deccan Award for Outstanding Academic Achievement at Rice. He is a fellow of Royal Society of Chemistry. He is also the, more importantly, we all know about the importance of the materials today, and we'll be wondering who the editor-in-chief of this, and here we have Professor Jim Lowe is also the editor-in-chief of Materials Today, the Elsevier flagship journal. And he is currently serves as the site director for NSF Industry University Collaborative Research Center of Atomically Thin Multifunctional Coatings, or called Atomic, exploring potential application of 2D materials, which actually gives us a very a nice opportunity to interact with his caliber of interaction with industry. I think that will help us also a lot. We can have some questions. We can also ask him how the industry academia interface, how NSF is doing. He has, of course, naturally has published a lot of papers, high impact journals, in several very well reputed one. He has more than 35,000 citations, high index of 56, and he is one of the highly cited researchers by Clarivate Analytics since 2018. So I think we would have loved Professor Zulu to have him here as a in-person, but Kano and Tiwari has given us a chance to meet him virtually, and I welcome you. And please go ahead. I think it's 45 minutes now. Professor Lu, the last yours.
Okay. Thank you very much, Professor Satyam, for the kind introduction. And I also want to thank the organizers for the opportunity to present here. It's a pity, certainly not able to travel to India, but given the circumstance, I hope in the next 40 or so minutes, I could share with you some of our efforts in this very interesting in-situ area. Okay, without further ado, let me get started with the talk today. I have been listening to some initial talks yesterday, and I am sure the participant has heard about this sentence many times already. Seeing is believing, right? So if you are able to capture the dynamic response of a material to certain external stimulus, at the same time when it's happening inside some kind of microscope, and in this particular case is electron microscope, you are going to be able to see a lot of interesting information that is not going to be available to you otherwise. So the in-situ technique, especially the in-situ technique inside electron microscope, has seen a very rapid development in the past several decades, 2 to 3 decades. And about a decade ago, a number of very active researchers actually they wrote a perspective paper in MRS Bulletin, and summarizing some of the most impacting and also the promising techniques being developed for the in-situ TEM experiment, as listed in this table. Okay, so we have heard some very nice talk yesterday about in-situ liquid cell, how that can be used to study a lot of interesting process, including catalysis and the crystal growth. And there are a long tradition of electron microscopists to apply strain and heating to study a number of very interesting material processes. And lately, because of the development of a nano indentation system, especially the in-situ nano indenter inside the TEM, mechanics are starting to play a role as well, to really trying to help people understand the mechanical response of materials in very different loading geometries. Okay, so I actually took the liberty by adding a new entry here. I think the combination or the marriage between the advancement of microscope development, a lot of those very interesting new development to enhance the electron microscopy capability we heard so far, with the advanced microfabrication. So you can actually make very interesting microfabricated devices that can provide additional stimulus to help you probe or perturb the material system and let them to behave under the direct observation inside the electron microscope. That actually provided a very, very interesting opportunity for us to answer some of the interesting questions that cannot be really answered, or a big challenge to be answered otherwise. Or it can also give you very interesting discovery that nobody thought about when you started the research. So hopefully today, I'm going to use some of the example coming from my group's research to demonstrate some of those ideas. Okay, so what I'm sort of advocating here is that seeing is believing is not the end of the story. If you can actually combine the observation power of the in-situ technique with the quantitative measurement, that will make this type of technique much more attractive and getting a lot more interesting for the number of studies. Okay, so let me actually give you a very quick overview about the kind of techniques employed by us trying to perform the studies. Specifically focused on the mechanical side, or what I call nanomechanical measurement. Okay, so here showing is essentially the early version of the nanofactory stages. A lot of you are probably familiar with that. They combine the TEM with AFM or TEM with STM holders, that you are able to pass the bias in your TEM sample and make the electrical measurement, for example, the IV curve. And also you can use the AFM cantilever combined with the STM probe and use AFM probe as a force sensor. So you can also perform mechanical measurement in a very quantitative manner. Okay, so later on I will show you some examples how we use this technique to study the very interesting metal plasticity size effect at a very, very small length scale, what I call ultra thin gold nanowire, less than 20 nanometer in diameter for those metal nanowires. Another type of approach that combine the quantitative measurement with the in-situ observation is this microfabricated devices that I just mentioned earlier. Here is just one example that being developed by my group. This is actually inspired by some discussion with Dr. Andy Miner from NSIM, almost 15 years ago. And in collaboration with in the early stage of development, we collaborated very fruitfully with the University of Minnesota Nanofabrication Center and Professor Ballarini, who was a professor at the time at UMN. So the idea of this device is very simple. We're going to employ a quantitative nano indenter that has already been developed for both SEM and TEM, and use that as an actuator and also sensor to actuate this very simple microfabricated device, what we call a push-pull device or rise microfabricated device, RMD. And as you can see from this symmetric design, when you actually push the nano indenter from the top, you're going to separate the middle shuttles symmetrically. So converting the compression force from indenter to the tensile force at the sample stage. Okay, so if you are able to essentially transfer small sample, the nanoscale sample, in this case, this is an individual nanotube or a nanowire, and bond them very securely at the two stages. When you start pushing the shuttle, you will be able to perform very beautiful uniaxial, very well aligned uniaxial tensile experiment on this sample. If you clamp one side and embed the other side into a matrix, you're going to be able to perform what we call a fiber pull-out experiment. The only difference here, the fiber is going to be an individual nanotube, which is much, much smaller than the traditional fiber pull-out that you perform using the Electron machine. So you can actually do that inside either SEM or the TEM. Or later on, I will also show you we are able to develop techniques to transfer two-dimensional materials onto the stage. And we can actually study very quantitatively the fracture and some other deformation behaviors of 2D material, and have found some very interesting behaviors and made some interesting discovery there. All right, so this is basically a dynamic cartoon showing you how things work for the nanowire or nanotube fracture test, and also the pull-out experiment. And the device, if you can look at the design, we actually have opening in the bottom side. So wafer is actually being carved out, making this device itself is electron transparent. So you can actually fit this into the TEM chamber as shown in here. This is fitted to a nanofactory indenter, but you can also fit that to a Isotron, or right now is a broker indenter inside the TEM. So we can actually perform those type of tests at much higher resolution than the SEM can give you. So you can actually perform that, and you can also collect the dynamic diffraction patterns during this deformation process. Okay, so due to the time limitation, I'm not going to discuss about that part of the work, but this is just the capability that can give you if you are designing those devices in a very essentially specific ways to use specifications. And additionally, if you don't have a nano indenter, in-situ nano indenter in your facility, you can also utilize the power of microfabrication, and design devices do not require nano indenter to actuate device. For example, on the right side, we have this chevron beam design. So by using the dual heating mechanism, you can also actuate this device and provide the tensile forces at the sample stage, which is showing here. I hope you can see my cursor. Okay, so this one does not require any additional setup. You can actually design your own TEM holder. You just need to design enough sufficient electrical lead that can drive those devices. And at the same time, you can also deposit the electrode on top of the sample holder. You can perform the electrical measurement as you are straining those samples. So we can actually perform so-called electromechanical test at the same time. Okay. In some cases, the in-situ TEM is very nice to give you detailed deformation process, especially if you are looking at the high resolution images and even at atomic scale, as we heard so far. But in some experiment, because of the very small field of view of TEM, people worry that the actual event may happen outside of the observation window. So in this case, you could actually utilize the large depths of view for the SEM and perform those quantitative in-situ nanomechanical tests inside the SEM. For example, this is a very simple homemade devices using AFM cantilever as the force sensor. And we designed a stage on both sides that has the 5 degrees of freedom that can help you align your sample to this load sensor. And then because of the layout of this device, you can actually observe the deformation of your sample in real time. Okay, I will also show some examples of using this type of device, very simple to make. And you can use that to do very interesting studies. For example, you can perform tensile bending or buckling test of 1D nanostructures, or you can do the pull-out test of the 1D nanostructure from matrices. Later on, I will show some example of that. So there are many other examples that has been developed in my group that we are trying to add into the capability of those in-situ nanomechanical tester inside the both SEM and TEM, and lately including some of the spectrometer like the top SIMS and some other technique that can provide you additional information during this quantitative mechanical measurement. Okay. Example including we can actually now do the using the 3D printing technique to design devices helping you to perform torsional experiment and also the pure shear experiment. Okay, for the time limit, I'm not going to discuss about those tester, but I think there will be a lot of room for the researchers in the community to develop their own gigs, their own devices to basically probe the kind of mechanical performances of interest to them. So those are just some examples, and I hope this talk can generate some interest in your research community. Okay, so with this background introduction, I don't know how much time I have, but I'm going to try to combine my talk in 45 minutes. So hopefully I will be able to go through all three examples I want to show here. Basically 3 classes of materials, the metal, nanometal, ultra thin gold nanowire, and the carbon nanotubes, as well as the interface related to the carbon nanotube nanocomposite. How do we perform those in situ quantitative mechanical measurement? And then some very recent work that we have been performing to study the fracture of the 2-dimensional materials. All right, so for metal, it has been very well known that we have very strong size effect in metals. The smaller the sample size or the sample volume, you're going to see a rise in terms of its breaking strength or the yield strength. Okay, so this observation was made back in the 1950s by Brennan when he was able to grow very pure metal whisker and studied the mechanical strength of those whiskers as a function of the whisker diameter. As you can see that smaller the diameter, the higher the breaking strength. At the time, Brennan actually attributed to those type of behavior to basically the elimination of the defect for the smaller volume sample, smaller diameter sample. Okay, and that explanation sort of helped understand what's going on in their sample, but it actually overlooked a very important process in metallic sample. That's essentially plasticity. Okay, so the size effect in plasticity was kind of rediscovered in the early 2000s with this very important work by Bill Nick's group at Stanford, when they actually was able to use the FIB focus ion beam to machine this nano or micro pillars out of any metal surfaces, and then use nano indenter to push on those pillars, and discover that the smaller the pillar size, the higher the yield stress and also the breaking stress or the failure stress. Okay, so this type of size effect was very widely discovered and also explored in many different metal systems. And they also come up with a pseudo Hall patch relationship as plotted here. The yield stress plotted against the diameter. Okay, so you can see this is very similar to the strength versus grain size type of Hall patch relationship. Okay, and when people actually started to reducing the pillar's diameter, there was a problem with this technique because inevitably the FIB focus ion beam is going to generate some surface damages to your pillar. So the smaller the pillar, the ratio of the surface damage layer to the volume of the actual pillar is going to be larger. And that's going to basically give you a much more effect compared to the larger pillars. And it's not going to be an intrinsic material response. Okay, so because of that reason, most of those type of tests was confined in the pillar size from a few hundred nanometer to a few tens of microns. It was very hard to get a very nice pillar that defect-free, a surface defect-free, if you're using the preparation technique. And it has been basically proposed there will be a deformation mechanism switch when the diameter of the pillar or the nanowire down at around 10 to 20 nanometer, it's going to be the switching from the traditional dislocation interaction mechanism, the Taylor hardening type of mechanism, essentially rely on the collective dislocation dynamic behaviors, to what people call surface dislocation nucleation, because when the volume becomes so small, you don't have actually space to accommodate those dislocation interactions in very small volume sample. And the surface dislocation nucleation and the continuous surface dislocation nucleation behavior will be the essentially the medium to to carry the plasticity for those samples. So this hypothesis was proposed by a number of theorists, but when we started this project about 12 years ago, has not been confirmed experimentally. Okay, so this is something we set out to do, to use a very pure sample, and also without any grain boundary, without any loading geometry effect. For example, I don't want string gradient during the loading of my sample. Don't want the grain boundary, so it has to be single crystal. Do not want any surface layer to confine the dislocation, so it has to be a noble metal. And we were able to get samples like that using several fabrication techniques. We are using gold here as an example. So we can actually make gold nanowire anywhere from a few nanometers to a few hundred nanometers, essentially cover that transition regime I just mentioned. Okay. So with the sample being made and confirmed being single crystal, the next challenge is how do we actually stretch those very, very thin and small nanowire, right? So we rely on this nanofactory AFM STM stage, and trying to clamp this gold nanowire between the STM probe and AFM, and then trying to pull that to observe the deformation and the fracture behavior during this process. The first big challenge we essentially encountered is how do we fix this nanowire? In the past, this technique has been very, very nicely applied to study carbon nanotube mechanics. Using the technique, people are well known right now, the electron beam induced deposition, EBID technique, to basically glue the nanotube to the two ends so you can start to stretch the sample. But that technique actually failed in the case of gold nanowire because of the density of the gold is actually much, much higher than carbon. It's much heavier for the same diameter of the sample. So the EBID induced glue that the amorphous carbon really cannot hold those samples. Every time you're trying to stress the sample, it always breaks at the location where you're trying to glue those samples to the stages. So we actually, in the process of solving this problem, discovered a very interesting phenomenon, what we termed as a cold welding of gold nanowires. Okay. So in order to solve that problem, we actually glue the sample using the crystal bond outside of the TM, which is much stronger bond to hold those gold nanowires. And in many tests, the student, Yang Lu, who is now a professor at City University of Hong Kong, accidentally discovered that when the two ends of the nanowire touch with each other, within seconds, they're going to fuse into a new nanowire without any apparent defect in there. Okay, so you don't need to pass current, as some of the latest studies show. You have to pass current. You do not need to irradiate the sample joining regime with high dose of electrons. So none of that is necessary. All you require is essentially the touching of the two crystal logarithmically matching surfaces, and they are going to fuse together. This is almost like the wafer bonding behavior. When you have this very clean surfaces, you put them together, they will just fuse together to form essentially a new integrated structure. So when we look at this fused sample, when we stretch them again, it fractures at a different location, not at the fused regime. When you look at their diffraction pattern, at the interface, they essentially have exactly the same crystalline orientation as the rest of the two segments being joined together. And if you pass the current through this new nanowire, you break it and then pass the current again and measure the IV curve. We actually did that for 11 times, and each time their resistance are basically dead on each other. There's no differences from the electrical resistance. Essentially showing this a very reliable way to fabricate a new nanowire in situ inside the TM. Okay, so with this technique, we are able to solve that clamping issue, then to perform the nanomechanical testing. Here are some quantitative measurements. The top figure shows you the engineering stress strain curve, and the bottom one is the true stress strain curve. If you look at those two, for the engineering stress strain curve, you actually see that after the initial yielding event, you have seen a very large load drop. That has been predicted by the molecular dynamics simulation for a very long time until this work has not been experimentally verified. Okay, so this is a very interesting phenomenon. Later on, I will show you some sequence of videos related to the generation and also the slippage of this surface dislocation outside of the crystal. Okay, and the breaking strength is pretty high. For engineering breaking stress is already 600 MPa. And if you converted that to true stress, that's already 7 GPa. Very, very high, almost approaching the theoretical strengths. Okay, so that's essentially correlate very well with the previous theoretical predictions for this particular system. Okay, and we made some very detailed observation. I'm not going to show the movie today here to save some time, but if you look at this sequence of the images taken from a movie, at some level, you're going to see a surface dislocation nucleated, and then very quickly slip across the sample and disappear from the other end of the sample. Then another dislocation demonstrated by this yellow angle was generated from the other side of the surfaces and then disappear again from the other side of the surface. And you have this alternating slip behavior, and then eventually form those very classical necking behavior. What is special about those necking is at the very end of the necking stage, we actually observe single atomic chains being pulled away. Okay, so you can actually really demonstrate this classical view of necking down to one point type of fracture in this pure, ultra pure gold nanowires with very small diameters. Okay, so this is essentially one of the early evidence to suggest that the theoretically predicted surface dislocation nucleation indeed could sustain plasticity at very, very small diameter nanowires in very small volume metal sample. What is actually interesting about those nanowire samples is we actually made somewhat serendipitous discovery that not all the gold nanowire will fracture like what I showed you earlier. In some of the gold nanowire sample, we actually saw some very brittle-like fracture, what we call brittle gold. If you know gold, ultra pure gold material, it's a very ductile sample, right? It's a very ductile metal. You would never expect that the gold will fail in a brittle manner. But in some of our sample, we actually observed this engineering stress strain curve that is essentially going up and down, right? It's almost like a linear elastic fracture of brittle ceramic material. Very different from the engineering stress strain curve I showed you earlier. You have a yielding, then the load drop, then the work hardening essentially take over. So to rule out the strain rate effect, we actually perform those tests at the different strain rate and find that the strain rate play very little role. At the very high strain rate, we still can see some of those ductile behavior. And at the low speed, loading speed, we can also see this brittle behavior. So it's not correlated with the loading speed. Okay. So performed many tests, and we basically listed some of the 20-something successful tests here. As you can see, only less than half of them behave ductile in nature. More than half of the other samples are essentially showing this very brittle-like behaviors. The criterion of brittle versus ductile fracture is listed in this table. So what really happened is that we observed a very interesting deformation-induced twin in those brittle-like gold nanowire. Once you form those deformation twin, the twin boundary intercepted with the surfaces of nanowire become a weak point, and the damage will basically initiate from those junction point. Okay, and you can actually observe that repeatedly in the brittle-like gold nanowire fracture samples. We basically collaborated with Professor Jun Song from McGill University, and he performed some MD simulation, essentially recovered what we observed in the experiment. Once you form the deformation twin, you're going to see very brittle-like behavior in the fracture and the deformation, subsequent deformation, the fracture behaviors of those nanowires. To make a long story short, we actually went back to the basics of dislocation mechanics and find that this differences in the brittle and ductile fracture is actually related to the twin partial formation and the non-twinning partial formation. Okay, and this is actually originated from the loading axis mismatch. Okay, in the TEM sample, when you perform those experiment, the tensor experiment, especially using the nanofacture stage, it is actually very hard to align your sample. So if you have a misalignment of loading axis relative to your sample axis, you are going to see very different results. So from this analysis, we actually demonstrated that if the misalignment angle is larger than a threshold, in this case, it's being calculated to be around 10 degrees, you're going to basically form those deformation twins. The twin will be activated first, and that will lead to the brittle failure. But if that angle is smaller than 10 degrees, then we're going to have the more normal partial dislocation nucleation and propagation that we observed earlier in the sequence of video, the images I showed you. Okay, so I think this is a pretty interesting example showing you the very powerful nature of in-situ observation combined with the quantitative measurement to understand the metal plasticity at small length scale. Next, I'm going to quickly go through some example with the carbon nanotubes. A lot of you know carbon nanotube very well, so I don't need to spend too much time introduce that. One of the important applications of carbon nanotubes is utilizing its very strong sp2 bond. It's a very strong material if there's no defect in those carbon nanotube sample. So if you can integrate them into the matrices to make carbon nanotube composite, that is being envisioned to have a major role in developing next generation ultralight, high strength, and high damage tolerant nanocomposite. Okay, but there are considerable challenges of integrating nanotube into the composite matrices. For example, how do you purify the nanotubes, disperse them, and align them? Basically, how do you integrate them very well into the composite is a very important processing challenge. And this processes, purification, dispersion, alignment, oftentimes involve chemical treatment of nanotube, and inevitably will affect your mechanical property. And another important issue in the nanocomposite is how do you engineering the interface? Because the nature of the interface between nanotube and the matrices is going to control the essentially overall performance of your composite, right? Because the interface will be the mediator for the load transfer. And how do you actually design that interface is going to be of paramount importance. So the two critical questions we set out to address in this part of research is trying to understand the intrinsic carbon nanotube property and the local interface behavior, the balance between those two factors, right? How do you actually design a process that can retain as much of the intrinsic strengths, but also be able to form a very good interface between the nanotube and the composite to essentially enable the effective load transfer. That's the thing will be very important for the design and the fabrication of the composite. So we're trying to use the nanomechanical testing setup to help answer some of the questions. So the first study we performed is to understand the doping, nitrogen doping in this particular case, the doping effect on the CVD grown carbon nanotubes. So the sample is showing here, it's CVD grown carbon nanotube, and the bottom one is just adding the nitrogen precursor in the chamber, so you can have this nitrogen doped carbon nanotubes. The major difference between these two samples, you can clearly see that in the nitrogen doped sample, you form those compartments, almost bamboo-like structure. And also the net number of the sidewalls is reduced relative to the pristine carbon nanotube. Those are multiple nanotubes with a diameter between 60 to 80 nanometers. Okay. And we use this device, and we actually glue those nanowire and well-aligned nanotubes across the stage, and able to perform the mechanical testing. Here are some of the stress strain curve and the corresponding maximum load and tensile stress data. So from this, it's very hard to tell the big differences just from the curve and also the data. Even though the load carried by the pristine tube are higher than the nitrogen doped tube, because of number of the walls carrying load is higher, is actually larger in the pristine case compared to the nitrogen doped case. So it's not surprising it carry more load. But if you normalize by the cross-sectional area, their tensile strengths actually have not too much difference. But interesting behavior is actually showing in the in-situ observation of the fracture surface. If you zoom in at the fracture surface, the pristine nanotube actually shows very, very flat fracture surface, corresponding to something you would relate to a very brittle fracture. But in the case of nitrogen doped sample, you see this very long tapering, almost like a necking in the nanotube case. Only difference here, this is really not a solid nanotube. This is actually a nested carbon nano tube. And you can clearly see at the very high magnification TEM images that for the pristine sample, almost all the walls fracture at a very close locations. The scale bar here is 5 nanometer. So if you zoom out, they almost appear to be fractured at the same surfaces. But in the case of nitrogen doped sample, you can clearly see a very interesting kink developed here. So this kink is actually not the sword and shield type of fracture. When the outer layer of multiple nanotube break, the inner layer will be pulled out. If you look at this kink, all the layers are actually present. It basically just form a kink at the location close to the fracture surface. So this type of behavior is very interesting because that's related to the so-called Stonewall defect, which is essentially the dislocation in the hexagon lattice case. Okay, so this 5-7 defect, if you look from the side, actually naturally form this type of kink. Okay, so in order for you to have the plasticity in the carbon nanotube, you have to ensure that those 5-7 defects, Stonewall's defect, is mobile, right? Having the dislocation is not the necessary condition for the plasticity to occur that everybody knows. You have to make sure that those dislocations are mobile, okay? So in normal cases, at the room temperature or at the condition we perform our experiment, the energy barrier for the dislocation to stop moving is very high. So most of the carbon nano material actually behave in a brittle manner under the ambient condition. But after the nitrogen dope, it turns out that the theoretical calculation suggested that the nitrogen doping at sufficiently high concentration was significantly lower that energy barrier for the dislocation to move around. And that's actually one of the early evidence we demonstrate that it could actually have a very interesting design rule to help you enable the plastic deformation of tubes under room temperature by chemical doping. Okay. I think I'm running out of time. Mr. Chairman, how much time do I have left?
You have about 7 minutes.
7 minutes. Okay. So I'm going to speed up considerably. Just quickly show you that we also demonstrated that if you put the chemical functionalization on the sidewall of multiple nanotube, it will affect the nanotube strength very significantly. Okay. And that's easy to understand because this chemical functional group disrupt the perfect sp2 hybridization, and that will actually deteriorate the mechanical strengths of your nanotube. But later on, I will show you when you actually perform the carbon nanotube pull-out experiment, those fluorination groups actually help you to improve the adhesion strengths between the nanotube and matrix. So there is really a balance between the different kind of chemical functionalization, how much functional group you want to put there to enable the separation and dispersion in the matrix without sacrificing too much of your intrinsic mechanical strengths while promoting very good adhesion between the nanotube with matrices. So I'm going to skip this introduction, basically showing you that to get interfacial characterization of nanotube and the matrices, many methods has been developed. The most direct method is this fiber Poiseuille experiment. We are just trying to shrink that fiber Poiseuille experiment many times to perform that at the individual nanotube level, as shown in this cartoon. And we're using the same device and embedding this nanotube into a matrix. And the other side is clamped. During this tensor test, we can actually pull out the sample and measure the force displacement. And if you convert that to the load extension, we can actually embed this nanotube at different embedded lengths and measure the mechanical response. Based on the contact mechanics theory, we can actually determine whether or not it's actually a linear response or nonlinear response corresponding to the short or long embedment lengths. And using a very rigorous model developed by John and Tan, we can actually calculate, very carefully calculate this interfacial fracture toughness, okay, interfacial fracture energy, and also the IFSS, interfacial shear strengths, in a very accurate way. And for the nanotube embedded in the epoxy matrix, if the nanotube is a high quality nanotube, in our case, is a Mitsui tube from Japan, because of the inner nature of the carbon nanotube surface, that the interfacial shear strength or this bonding between the matrix and the nanotube is actually very low. But if you actually treat that nanotube with fluorination, with the same system, we can see a 3 to 5 times of enhancement of that interfacial interaction, including the fracture energy, interfacial fracture energy, and IFSS. Okay, like I mentioned earlier, the balance between the intrinsic mechanical strengths and the interfacial fracture energy is very important for the nanocomposite development. I'm going to skip on this junction measurement and very quickly tell you something about graphene and the 2D material. So in the case of graphene, we all know this is a very interesting material. If you actually slice open a nanotube, you can obtain a graphene sample. And it has very similar sort of mechanical strengths as compared to carbon nanotube. We all know the prediction, theoretical strengths above 1 terapascal, and the theoretical modulus above 1 terapascal, and the breaking strengths above 100 GPa, right? So in many applications, innovation for graphene, including the flexible electronics, composite, and also the devices, mechanical strength is very important. But so far, the mechanical strength is measured under the condition of nano indentation. Okay, that's where the experimentally reported data I just mentioned being obtained. But one important question is, what is the resistance of this material to the initial defect, which is inevitable when you are processing this material into larger scale devices? So that's essentially a quantity people call fracture toughness. And that's how we use our device to, for the first time, measure this fracture toughness of graphene by essentially repeating Griffith's experiment at very small scale at the 2D limit, creating a pre-crack and being able to fracture the sample. And you can see the sample fractured along a very straight edge very quickly, very brittle behavior, okay? And if we use the Griffith theory to do the analysis, it actually shows very good correlation with the Griffith's prediction. And using the linear elastic fracture mechanics, since the lack of plasticity in those samples, we can actually determine the fracture toughness is in the order of 4 MPa per root meter. Very low in comparison to its high strength and modulus. This value is very similar to the box scale oxide, the ceramic. Okay, so in order to actually improve the toughness, the take-home message here is graphene is very strong if it's defect-free. But once you have some initial defect in there, the resistance for the damage nucleation and the propagation is very low for graphene. So we used the composite approach by integrating nanotubes into the graphene to show that it's possible to enhance the toughness of graphene. So I'm going to skip this part. This ACS nano paper is showing here. If you're interested, you can dig this paper out. So this nanotube essentially serve as a rebar, as the rebar in the concrete that essentially enable the crack deflection and the CNT bridging the crack as shown in this MD simulation. So you can actually effectively enhance the fracture toughness of graphene by the order of 2 times. Okay, so you can actually increase that by 2 times. And this is my last part. I really ran out of time. So I just want to say that it actually gets a lot more interesting when the lattices are becoming asymmetric. You're replacing the carbon atoms with boron and nitrogen. This asymmetric lattice geometry will give you unexpected toughening behavior in the sample. So this is a recent Nature paper we published and demonstrated for the first time. You can actually observe this crack resistant behavior. So the crack actually can grow and stop in the 2D material, which was thought impossible due to the brittle nature of this material. So I'm going to skip on the detailed explanation. This is really due to this the asymmetry bonding between the boron and the nitrogen, giving rise to intrinsic mode 2 stress intensity factor, which was going to be swapping during the crack advancement, gave rise to this repeated crack deflection as well as the crack branching that provided tremendous toughening behavior in the HBM lattices. All right, so I'm going to stop here. Most importantly, thanking all the students and the brilliant postdocs that worked with me over the past 15 years. It's them actually did the work, and also wonderful collaborators and our funding agencies. My last slide is going to be about the journal that Professor Satyam mentioned material today. And I just want to emphasize that this is not a review-only journal, and we welcome high-impact work from all of you that will basically be original research. I'm going to stop here and be happy to take any questions. Thank you.
So it's a really very wonderful talk by Professor Jun Lu. Thank you very much for giving a really variety of areas, right? Starting from nanowires to CNTs and then the breaking results in carbon nanotubes, particularly the CBNs as well. So, I mean, we are fortunate to have him here in this workshop, in spite of being a lot of time delay. It's right now at the past, almost close to midnight. He's still with us. Thank you very much, Professor Lu. And if there are some questions, we are welcome to take.
Professor Satyam, can I ask a question?
Yeah, please.
So, Professor Low, in case of carbon nanotubes experiments, where you show that if you break the nanotubes, sorry, not the carbon, the gold nanowire experiment, if you break the gold nanowires and then leave it there, they rejoin and form a new nanowire. Is it because of the enhanced surface diffusion happening at the level of that dimensionality, or is it because of the strain that is inbuilt in the these nanowires during deformation?
Yeah, that's a very good question. First of all, I think the strain effect, we have tracked the strain effect very carefully. You actually do not need to induce strain at the junction regime to initiate the joining process. Merely just touching the 2 segments of nanowire will be sufficient. Okay. We also checked that behavior with our theoretical collaborators, which basically demonstrate the same thing. But your second point is actually your first point is very, very well taken. The surface diffusion is indeed a very important process during this welding process. At that small scale, atoms is going to diffuse very fast, right? As you can imagine, the gold atoms, particularly, if you find the right terraces for the atomic planes, the gold atom diffusion does contribute to this joining process.
Okay, thank you. The second question I have is that in case of this hexagonal boron nitride, okay, you showed the fracture which is happening at these are all hexagonal material, right? They are hexagonal close packed structures. So what you understand, they are intrinsically poor, they have poor ductility, and making them 2D will decrease even the ductility further. So is it not expected that they will prill very brittle like a glass, amorphous things, and will not give any ductility at all?
Yeah, actually, this is a very good point. We all know that those are the layer structure, right? And when you actually are isolating those layer structure down to the monolayer, to the atomic layer, their behavior does give quite a bit of surprising to the researchers in the community. What I want to say is that indeed, the bulk HBN or the bulk boron nitride in general is a brittle ceramic, right? So from the conventional wisdom, you would expect that the monolayer sample will not behave differently. I agree with you on that. But when we actually study this sample, it turns out that at the monolayer limit, this asymmetry of lattice structure actually play a much more profound roles than we expected. Because at that limit, the edge stress effect is going to be amplified due to this monolayer limit. And we can actually see that the boron terminated edges and the nitrogen terminated edges have very big differences in the edge stress. That actually determines how the crack is going to advance when they meet the bond. In the case of carbon-carbon lattices, the carbon-carbon lattice essentially have the symmetric arrangement, right? Both sides of this bond has the same carbon atoms. So if the only path for the crack to go forward is to zip through that bond, open that up. But in the case of the boron nitrogen, you actually have a difference in the choice of the path due to this edge stress effect. Okay, so that's actually the surprising discovery. We actually didn't expect that when we first performed the experiment. In fact, in most of the two-dimensional material we studied so far, their behavior are very brittle-like. This is the first time we have seen in an intrinsic 2D material without any kind of nanotube or other composite being added to the surface of the 2D layers. This is the first time we observe this type of behavior.
Yeah, thank you.
Yeah, I think thank you for this. And Chandra has, Dr. Tiwari has a question. So please go ahead and ask. Chandra.
Hello, Professor Law. Chandra here.
Hi, Chandra.
Thank you for such a fascinating talk. Dr. Low, you started with the talk and I never thought in this way, but it sounds little crazy. So you have these cracks and in this 2D material, and now if you try to close it, so what I mean is try to bring back closer. Do you think this 2D material will also join like your tubes and wire, what you started discussing in the beginning?
Yeah, that's a very interesting proposal. But I think the challenge here with those 2D materials, once it's separated, it's going to be hard to maintain their relative position. So if you look at some of those fractured surfaces, they actually will be flipped over. So the two free atoms are actually pretty far away from each other. Unless you figure out a way to actually put them closer within certain range, I think that joining will be very difficult to realize in those experiments.
Right, but maybe as soon as they're starting, like in this particular one, if you have figure B, you see the it's just they started. So rather than
Yeah.
moving in the same direction, if you go opposite direction, maybe it will come closer, and I don't know, it may start showing welding.
Yeah, that might be a very interesting experiment to do. We haven't done that. I cannot say this is not possible,
Right.
but this is a very interesting thought. If someone can prove that, that will be fascinating, right? You have basically the healing behavior of the
Exactly.
crack,
Exactly.
inside this 2D lattices. That will be
Right.
fascinating.
Right.
Yeah.
And one more question just connected to that. So in this welding or joining this wire experiment, so most of this, if you look at some of the paper, they talk about ceramic material generally under electron beam. They do see some diffusion or beam induced diffusion. So some
Yeah.
of those joining experiment, how we really avoid those kind of artifact and defect.
Yeah, that's a very good point. I think the difference between that particular work of ours to some of the electron current or electron beam induced joining is that we have been very careful tracking that. Actually forced by the reviewer. We have done almost 1 year of experiment to rule out those effects. In fact, during the joining process, we shut down the beam. So there's actually no beam irradiation during that process. And we actually tried to pass different the current at different intensity to the nanowire. And it shows very, very different effect. And in our case, we actually pass no current. You don't need any current to join in the sample. So I think in a lot of those experiments, you have to be very careful controlling your condition. The metal case, as mentioned by Professor Biswas, we have advantage that typically metal atoms like gold atoms diffuse very fast at that scale. Okay, so that actually gave you some leverage to facilitate this joining process. But what's actually amazing is during this joining process, you do not change the crystalline orientation. You actually do not form any defect there. There's no grain boundary or the phase boundary at the joining point. So I think that's an interesting behavior that the healing of this two segments are almost perfect from our characterization.
Thank you, Professor Loh. Thanks a lot.
Yeah. Are there any questions? So if not, I would like to ask a small question. So can I ask you some question, Professor Lu?
Yeah, please.
So we had done some experiments with filled carbon nanotubes and found out that due to electron radiation defects, particularly the displacements happening, the extrusion, that means the filled material comes out of the nanotube. This we do in situ heating measurements. But then we realized, we found that electron beam induced, just now you talked about it, actually that plays a role. And much earlier temperatures, if you play with the beam current, we see that this extrusion or the material coming out from the carbon nanotube is observed at higher, lower temperatures. So my question here is, because of the defects formation, particularly being a boron, carbon, nitrogen, all the displacement energies are quite less. Particularly if you have a 300 keV, you easily knock out the nitrogen. So how much role do they really play on the mechanical measurements? Because there is a lattice change at nanoscale. You are creating the defects. And then I think at atomistically something should be happening. It may be enhancing the radiation enhancement should be there.
Yeah. I think the effect of electron beam interaction with nanoscale sample is always a sticking point, right? For those in-situ measurement. Yeah. So for those of us using those TEM or SEM as a lab instead of just a microscope, we have to be very careful with that electron beam current control. So for a lot of experiment we perform in order to avoid the electron beam damage, we typically shut down the electron beam during the quantitative measurement for collecting a large amount of quantitative data. The only time we actually open the beam is in order to see some of what really happened during this process. But again, once you kick in the beam, then inevitably there could be some artifact introduced by the beam irradiation. I think this is a challenging, I think it's a big challenge for the in-situ technique. How do you actually utilize those high energy beams as a probe rather than the, the disruptors of your structure? You don't really want the beam to modify your structure such that the behavior observed may not be intrinsic to the sample you are studying. I think this is, I agree with you, this is a big trouble.
I think there are, a lot more questions, but due to lack of time, I'm sorry that they're not taking more questions. So thank you very much, Professor Jan Liu and Jun Liu. And I think I request the participants to directly in touch with Professor Liu. And I'm very sure the way he's interacting will be really helpful for us. So thank you very much. We appreciate your presence and spending time with us, the Indian Electron Microscope community. And we move on to the next one. So thank you, Professor Liu.
Yeah, so thank you very much. It has been a pleasure.
Thank you. So now we move to, could you please, maybe you can unshare the screen. I think we are unshared. So now it is Pawan is around, Dr. Pawan.
Yeah, he's in the list. He's sharing.
Yeah, so I see he's already put. The next speaker is Pawan, Dr. Pawan Mukala, and he will be talking about, as you see it, observation of reversible oxygen migration, an interesting topic. And he graduated from IIT Madras, and then he did PhD in Pennsylvania. Afterwards, he moved to postdoc at several places. One of them is France, and he was also a Marie Curie fellow, which is we all know that. And he had been working on nanostructure, functional materials for quite some time. And now he is working as an assistant professor in Sense in IIT Bangalore. So I take this opportunity to invite him and present his talk. Dr. Pawan Mukala.
Thank you, Mr. Satyam. Can you hear me?
Yeah, please go ahead.
Yeah. I think there is a problem with my camera, so I cannot. But yeah, so I'll probably put a photo of myself at the end or something, so you know how I look. Okay, great. So first, let me thank the organizers for giving me this wonderful opportunity. This is the second time I'm talking in one of these EMSI events, and that's been a pleasure for me in the past 1 year. So today I'll be speaking about one of our most recent works. So a part of it was also done after I came to IISc, especially the data analysis part. And this is trying to understand what ferroelectricity looks like in these new ferroelectric materials. By that I mean hafnium dioxide, doped hafnium dioxide thin films, using in situ biasing experiments, and this will be done at an atomic resolution. Okay, so let me just go forward. Yes, so just before I so the most important part of this work is it's a group effort. So I'll take this opportunity to thank everyone involved here. It's a collaboration between University of Groningen and after I moved to IISc, one of my research associates who is also a PhD student. His PhD was in statistical biology actually, but he decided to help me in this project, and that was a very nice collaboration to him. And I also want to mention this person who is working as an intern with me from IIT Indore. Pranav, he's a second year BTech student. So there is a lot of scope for data analysis for if you're BTech, MTech students, especially in this age of big data. And also I'll show you a brief work that we did at synchrotron also. These are complementary to the electron microscopy experiments, and that was in Sweden. Most of the electron microscopy was done in University of Groningen, and a special thanks to one of my very nice friends and collaborators, Majid, in terms of the in-situ TEM work, and special thanks to one of my students, Yevgenios, who is currently in London doing his PhD for the synchrotron work and growing samples and things like that. Okay. So let me get started. So before I jump in directly into this ferroelectric materials, let me also tell you that I've been working on this in-situ microscopy for quite some time now. So I started my PhD by looking at phase change memory, and these are nanowires, as was shown in the previous talk, but with electrical biasing. And all these, so we looked at dislocations in these nanowires, twin boundaries in these nanowires, how they conspire to form these amorphous phases in these materials in a very solid state way, and thus that would reduce the power for switching these materials. And so these discoveries were quite useful in making real devices with low power devices of phase change memories. But I'll not be talking about that today. This was done at nanoscale. So we took, recourse to diffraction and, the bright field, dark field TEM modes to actually look at the activity that is happening in these materials when you electrically bias them. But today, what I'll be speaking about is actually this unconventional ferroelectrics, or new type of ferroelectrics, as I'll say. And this work will be shown at an atomic scale, what is happening at an atomic scale. All right, so that's not there. So today, let's just jump into nanoscale ferroelectricity. So what is nanoscale ferroelectricity? Why is it problematic? So first things first, ferroelectric materials are these materials which have a spontaneous dipole moment. And then this dipole moment can be switched by the application of field. Now, if you make these materials thin enough, you have to worry about what these surface charges are. So if there's a dipole in the material that creates the surface charges, this is nothing but the definition of dipole moment. And you have to be able to screen these surface charges. And for that, typically people put this in a capacitor geometry with a metal on the top. This metal would provide opposite charges and it would screen these surface bound charges. If you don't screen it, so for example, in this work, there's a ferroelectric layer here. This is lead titanate. And this is interfaced with an insulator. This is strontium titanate. Strontium titanate does not have these electrons to screen this ferroelectric polarization. Then it forms all these very nice vortices of polarization, but nevertheless these are not ferroelectric anymore. It doesn't have a unique polarization either this way or this way. Okay, so and this comes up because the surface charges induce what is called depolarization field, and depolarization field tries to kill the polarization that is actually created. So you make these materials thin enough, you can use the best of the metals available, but they still cannot screen these depolarization fields completely. All right. So ferroelectricity seems to be incompatible with miniaturization. Now, this is a bummer because, so we have all these ferroelectric materials which were known to be these low power solutions for memory technology and things like that. But now you cannot really use them in microelectronics because everything wants to go small in microelectronics, and ferroelectrics are not really compatible with them anymore. Now, in that context, enter hafnium dioxide. So in 2011, there was this discovery that you take hafnium dioxide thin films in crystalline form, dope it with several different elements, silicon, aluminum, gadolinium, etc., lanthanum, strontium, yttrium. You see these very nice ferroelectric loops. The thing about this ferroelectricity, the good thing, the desirable things about this ferroelectricity is that hafnium dioxide is a well-known silicon compatible material. You can directly grow it on silicon. This is nano-only ferroelectricity, which means you get this only in nanoscopic sizes, less than 10 nanometers or 15 nanometers. And then this ferroelectricity becomes more and more robust with miniaturization. So for example, here I show, so these are the samples that we grew later on, so using pulse laser deposition. So this is these are what are called epitaxial samples. So this is a thin film of hafnium zirconium oxide, so hafnium dioxide zirconium oxide alloy. And then this is interfaced with 2 of perovskite electrodes. Okay, so these are actually metals, although there is this complex formula and it's an oxide. Electronically they are metals, so they are actually well-known perovskite electrodes. So you have this capacitor geometry. And if you look at this capacitor geometry and then you look at the polarization hysteresis, you see that for a 9 nanometer thick film, you have a remnant polarization of about 18 microcoulomb per centimeter square. Whereas you lower the thickness, the polarization actually improves, right? So this ferroelectricity is unconventional. It is going against the principles of ferroelectricity that we know, right? Okay, so so that's interesting. So what is it that is making it robust as you keep on reducing the size of the material is a question that we tried to answer as soon, I mean, in 2017, 2018, that period of time. So hafnium dioxide and zirconium dioxide, so all these are sister compounds, so I will be interchangeably using them throughout the rest of this talk. So it is these are what come under the broad class of materials called the fluoride materials, and these fluoride materials show a plethora of phases, right? So there is huge amount of polymorphism, and out of these polymorphism, if we go by conventional wisdom of what ferroelectricity is, you should look for these materials with the point groups which are polar. And so one of the phases is this orthorhombic ferroelectric phase, which is the least energetic polar phase, and you have other polar phases also, the ones that I color in this blue color, and there are other phases such as rhombohedral phases, which are slightly more energetic than the orthorhombic phase, but nevertheless they are also polar. Now, if you are doing a thin film growth and experiments growing thin films, it's not necessary that you always get a thermodynamically stable structure. You can actually get all these metastable structures, and roughly the hand waving principle is within an energy a metric of about 200 MeV per formula unit. Right, and all these phases, actually the R3M phase, lie in that window, and so it is not impossible to get that from experiments. And then there is quite a bit of literature from nanoparticles in hafnium dioxide. For example, this is a work from Santa Barbara, where they suggest that these are experimental results, and they look at the thermodynamics of nanoparticles of hafnia. As you keep reducing the size of hafnia, the hafnium actually becomes so it transforms from a tetragonal phase to a cubic phase back to an amorphous phase. So in fact, if you look at hafnia, the monoclinic phase is the most important phase. It's the ground phase of ground state of hafnia. It is a low volume phase, okay, it is a low density phase, which means it has a high volume. Now you can think of applying some nanoparticle pressure or something like that to reduce the density of this phase, and then you get tetragonal and cubic phases, which are low volume phases. Okay, so as you keep reducing the size of this material, you go from a higher volume phase to a more lower volume phase. All right. So what is it that is happening in our material, in our thin films? In fact, if you look at our thin films, you see that these thin films are made up of several domains, right? So here is one domain, and then you rotate this by 180 degrees, you get this other these are what are called ferroelastic domains. This is nothing but martensitic domains in the metallurgy literature. And then if you look at the size of these domains, they are corresponding to the size of the film, right? So if I have a 10 nanometer thick film, I have a domain size which is about 10 nanometers. If I have a 5 nanometer thick film, I have a domain size which is about 5 nanometers. Now, based on that, so we can think of, integrating this with the nanoparticle literature, we can think of these domains as being interfaced with domain boundaries, which are like surfaces. And so you can think of this as nanoparticles which are of this dimension, and then there is huge amount of Gibbs-Thomson pressure in these nanoparticles, about gigapascals of it. That is already enough to stabilize these nanoparticles in a cubic phase, right? Because cubic phase is a very low volume phase. And on this cubic phase, you start. So let's assume this is a cubic phase which is growing along the 111 direction. And in any cube that is growing along the 111 direction, you apply a compressive strain, and that compressive strain can come because of thermal mismatch, or just the substrate induced strain in these thin films, in these epitaxial thin films. You expand the body diagonal, and then you contract the others, and you transform from a cubic to a rhombohedral phase, right? So this is the first discovery of a rhombohedral hafnia thin film, and this also turned out to be quite ferroelectric. All right. So here, actually, by 2018, in this Nature Materials paper, we actually explained how this rhombohedral phase can be formed, and later on we tried to give guidelines of how to form rhombohedral phases in many different systems and substrates, because they have a robust polarization compared to the orthorhombic phases that are generally reported. Now, the point is, okay, so we have this rhombohedral phase, all right. So there is a strain argument, but so I explained how the polarization is coming. but then how does it switch, right? So we have to get into the kinetics of it. How does the polarization switch? And then I don't answer the question as to how this ferroelectric switching is robust against the depolarization effects. I started by saying you miniaturize the depolarization effects, kill it, but then somehow these materials seem to be robust against depolarization. So for that, we decided to do in-situ TEM and then put these thin films, thin film devices inside a TEM, and then actually see atomistically what is happening. And this has recently been published in Science. Okay, so a bit of the technique information about the techniques that we use. Of course, so these are all STEM modes of imaging. So the most common STEM mode of imaging is to collect these electrons which are scattered to larger angles, the HADF STEM, the so-called HADF STEM. But if you are interested in atoms like oxygen, you really don't have any information about oxygen, lighter atoms like oxygen coming from this HADF detector. Because it's a large annulus detector, and then if you there is no real signal coming from scattering of oxygen and hydrogen and low atomic number elements like that from here. So there is another recent technique, and this is what David was talking about yesterday. He was talking about tachography. So this is what is a poor person's tachography. This is called differential phase contrast STEM. And in differential phase contrast STEM, what you actually do is you make use of the fact that these electrons actually when they pass through atomic columns, each of these atomic columns has an electric field associated with it, or an electric potential associated with it. And this field would actually deflect the ronchigram that you're seeing here slightly towards one of the four directions. And as a result, what you can do is, instead of integrating the annulus of the detectors and then forming these HADF, ADF kind of images, you can actually look at the deflection of this beam. So you can actually segment this detector into four different segments and look at how the center of mass of my ronchigram is changing. Right? So this is called center of mass imaging, or it is analogous to center of mass imaging. There are some differences between how you do this and the exact center of mass imaging. But so using center of mass imaging, you can directly measure the atomic fields, the atomic fields or the nuclear fields at every atomic column. You integrate the atomic fields, you get atomic potentials, and we want to actually see the atomic potentials. That is nothing but seeing the atoms, right? You differentiate the atomic fields, you get what is called DDPC. So this is called IDPC, by the way. And in DDPC, you see the charge densities, right? So here's an example, and this work comes from my collaborators. Sidze and Bart, who are authors on the science paper that we have also right now. They demonstrate that you have this titanium hydride interfaces, and using IDPC. So this is IDPC, this is DDPC. You can actually clearly see hydrogen atoms which are in between this this titanium shell or titanium framework, right? So I don't know of any other technique that can image hydrogen atoms, right? So it is this Foreman's topography or DPC, using which they can clearly show that there is you can image such low atomic number elements such as hydrogen. Now there we go. We have the requisite technique to actually see our hafnium and also oxygen, because it's hafnium oxide. There are only two. There's a cation, there is an anion. Anions play an important role in determining the polarization of this material. And here's the IDPC image, one of the IDPC images of our hafnium dioxide, the rhombohedral phase of hafnium dioxide. As you can see, this bigger blobs are hafnium columns, and the smaller blobs, which the doublet or this dumbbell kind of thing that surrounds this hafnium, are oxygens. Okay, so you can clearly see that. And you simulate how a rhombohedral structure should look like. It exactly looks like how experimentally we image the IDPC STEM images, right? Now you can do something more. You can actually, since you have the complete information about positions of oxygens and positions of hafnium, you can calculate the dipole moment in this kind of units. And you see that the net polarization you calculate is less than 2 microcoulomb per centimeter square. So this is actually, so this is not giving as much polarization as we measure from macroscopic measurements. So from macroscopic measurements, we are measuring about 35 microcoulomb per centimeter square. So there's a huge discrepancy between what we calculate the dipole moments from these images and the dipole moment that we actually measure experimentally. So what is happening, right? So that was surprising. So we really wanted to understand this. And here's our in-situ temp setup. Just a brief word about that. So we use this Keithley parameter analyzer, which is currently being used in most labs for actually doing very nice pulse measurements. It has a low noise floor and things like that. And then you interface this electrical measurement setup with your TEM. Aberration corrected machine, the system is Z, using a holder, and this holder was what was acquired from this company called Henny Z. Actually, it was acquired from Henny is our collaborator in this work. And as you can see in this holder, you have these 6 different electrodes, and each of this electrode, and then you put in a MEMS chip that goes into this holder. There is a small silicon nitride membrane, right? 4 of these electrodes, with these 1, 2, 3, 4, they form a coil-like structure, so you can actually heat your material, right? So because it's just resistively heating, and 2 of these, with 2 of these leads, you can bias the material, right? So you need to put your material there. And putting the material is also a challenge. So you have to do very nice FIB. And the problem with FIB is this over deposition, gallium implantation, and all these things. In fact, you can see that there is a lot of, and first of all, doing this on silicon nitride membranes is not quite trivial. So you have to be very careful about how you do this. But we did develop very nice protocols, and then they work in any lab now. So if you're interested in this, you can always talk to me. And then, so you have all this junk that is deposited when you over deposit it because of the fib. So you have to clean it properly. So otherwise you'll have shorting between this electrode and this electrode. And finally, you just make the electrodes between, so these 2 pads here, right? So that's how you make a device. And now my device, looks something like this. So you have LSMO, HZO, LSMO. HZO is the half nim zirconium oxide. LSMO is my top electrode and bottom electrode. And this is the capacitor of interest, right? So I bias here, I apply positive voltage, I apply voltage here, and I always ground this contact. Okay, so with this setup, let's see what is happening. So at 0 volts, when you apply absolutely no volts. So first, let us talk about the evolution of this layer, the bottom electrode layer. And this bottom electrode layer is quite grown epitaxially on the top of the other perovskite. Okay, so which is strontium titanate. Now, so the way this should, so the way a perovskite looks is something like this. So you have octahedra. So this is MnO6 octahedra here, and this octahedra are tilted in a zigzag fashion with respect to each other. This is called the antiphase tilting of the octahedra, and this is how the virgin structure of this perovskite should look like. And in fact, that is exactly how it looks like. So you can see that this is oxygen, manganese, oxygen, oxygen, manganese, oxygen. So you have a zigzag, which corresponds to this tilting of octahedra in this, oxygen, manganese, oxygen, oxygen, manganese, oxygen, and so on and so forth, right? This antiphase tilting is very nicely captured in this images. Now you start applying voltage to this device, and then so I'm applying bias on the top electrode. So I apply 2 volts. You can see that the oxygen, some oxygens start moving closer to manganese, and some oxygens move. So there is some displacement of oxygen that is happening. Now you can actually see, so from here, what we did was we were actually, and in fact, you can look at how the oxygens are, with respect to oxygens, how the manganese is displaced. So originally in a perovskite, if you take 2 oxygens, the manganese should be at the center connecting these 2 oxygens. But here, in this case, the manganese seems to be displaced away. And you can do some data analysis from various such images. These are 370 different points. And then you can see how the manganese displacements are. And on this polar plot, you see that when you start applying bias, manganese just gets displaced randomly in all different directions. Whereas in the virgin, it's more or less localized. There is absolutely no manganese displacement you can compared to this. And then, so this is a perfect perovskite structure. So what is happening chemically, right? So here we see what is happening structurally. So you can do EDS. Again, you have to do it with the 4 quadrant, the 4 detectors that we have in most of the new systems, right? So the super stem or chemistem it is called. And then you have some sensitivity, some nice precision for oxygen. So you have to take several such images, and then you have to make sure that the precision is good, and then you acquire the data for a long time. So you can do nice EDS and then actually measure oxygen nowadays. And then you see that this is the top LSMO. This is 3 different regions in bottom LSMO. You see that the oxygen content in the virgin phase in bottom LSMO is more or less the same everywhere. Whereas when you start biasing it with this 1.5 volts in this case, you see that there is a gradient of oxygen, which means this part you're creating oxygen vacancies, and and you are pushing this oxygen to the top part. All right. So you can actually then what happens when you increase the voltage to 4 volts? When you increase the voltage to 4 volts, there is a phase change. And here actually what you can see is, instead of seeing these MnO6 octahedra, what you see is so this layer is MnO4 tetrahedra, and this layer is MnO6 octahedra. So it looks something like this. These manganese come together, and that forms a doublet here. And then this manganese is, so this is the MnO6 octahedra. So in this layer, there are 2 oxygens missing. So what you're actually doing is imaging oxygen vacancies, right? So these holes here are nothing but oxygen vacancies. Now, this is a well-known structure. It's an oxygen-ordered structure. This is called a Brown-Millerite structure. So what you're actually doing is you're removing oxygen from this layer, right? And then you're changing the coordination polyhedron from being an octahedron to something which is a square pyramid, square pyramidal like, by creating these oxygen vacancies to something which is an octahedra tetrahedra combination, right? Now, okay, so all that is fine. So when you apply voltage, it's easy to remove atoms from PEM, right? So you're doing this under vacuum. So can you put it back? That's the important question. So in fact, you can put it back. So here I'm showing you the same field of view at 0 volts, and then now I reverse the bias to minus 1.3 volts. You can see that wherever there are oxygen vacancies, these holes here, in the same locations, oxygen starts populating. Right, so you're removing oxygen from here and you're putting it back later on, and then you apply more voltage. So go back to minus 3 volts. You restore the perovskite or perovskite-like structures. Okay, so that's fine. That is what is happening to the bottom electrode. So what is happening? Where is all this oxygen going, and then where is it coming from? So the suspect is this Hafnia layer. And so you can actually see that, okay, in the virgin state, I take this region, right? So this supercell of Hafnia, and then we do some data analysis here. We see how the oxygen is displaced, right? And we correlate the displacement with the oxygen vacancy displacement. And you can see that the oxygen vacancy displacement, the oxygen, when you start applying a positive voltage, the oxygen vacancies are moving from this layer. So it just moves to the LSMO layer, right? So you have less number of oxygen vacancies here, and the oxygen vacancy concentration increases, and the actual displacement is in this direction. All right. So this is clear. So this is giving oxygen vacancies. This is taking oxygen vacancies, and in the reverse process, this okay. So and then you increase the voltage to 4 volts. Then the phase of this changes. Here, it's no longer a resolvable image anymore. So you start forming these other oxygen-rich phases. So you're removing oxygen vacancies from here. So what you're doing is you're forming oxygen-rich phases, and these phases turn out to be the orthorhombic phase, the monoclinic phase, which are more oxygen-rich. So from these experiments, actually, we know that the phase that we are forming is slightly oxygen deficient, and that is what is giving rise to the ferroelectricity, right? So, all right, and then you again change the voltage back to minus 3 volts. You recover back this wonderful rhombohedral structure. So the simulation actually corresponds to how your the rhombohedral domains look like. Okay, so what is happening, at least from these the steady state experiments? So these are not really time resolved experiments. So what is happening is you can see that there is a flux of oxygen. So oxygen vacancies are just transporting from HZO and LSMO top layers to the bottom layer when you apply a bias in this direction, and when you reverse the bias, they go back, right? So, and these oxygen vacancies are what are charged. So this gives you exactly the same output, or same macroscopic output as a polarization switching, because if you're in polarization switching, you're looking at surface charges, how they're reorienting, right? So this is a completely different phenomena, and this actually explains how you have a barrier for oxygen vacancies here, and if this barrier is small, then the switching is faster, right? So, and the switching is even more, right? You have more flux of oxygen vacancies that go from the top electrode to the bottom electrode. But okay, so with TEM again, there is always issues, right? So this is what we have been studying for the past 2 days. Since yesterday, which is it's done under vacuum, so you're losing oxygen from the surface. Now, if here I have an electrode which is LSMO, which is oxygen reactive. What if I have gold or something like that, which doesn't react with oxygen? Then what happens, right? So all these questions come up, and also time scales. What happens to time scales? So typically these ferroelectric measurements are done at higher frequencies. 1000 hertz and things like that. But what we are doing here is DC biasing. So at DC biasing, maybe, you can just, you're doing this at longer time. So you can activate all these slow processes of oxygen diffusion and stuff like that, right? So for that, here I'll quickly show you what we did at a synchrotron. So at a synchrotron, we made several devices. So we went to this synchrotron. This is the detector actually, and here you put the sample, and this is where the X-rays come from. And on this detector has this nice quality that you can take about 1000 diffraction images per second. So you can operate at about 1000 hertz or less than that, right? So to get good statistics. So we make devices, we go and then we investigate this part of the device. And then this part of the device, you have, so the top electrode, you can change it from an oxygen reactive to an oxygen non-reactive electrode. And this is the bottom electrode. Now, and then you capture the hafnium Bragg spots. So this is the hafnium dioxide Bragg spots, and you see the evolution of that Bragg spot. Okay, so we start doing this cyclic measurement, and this we apply pulses from minus 3.5 to plus 3.5 volts, and these pulses, they are applied at a frequency of 100 hertz, so that you have at least 10 data points. So you're measuring at every 1 millisecond, and your pulse is for 10 milliseconds. So you have 10 data points for triangular pulse. And then you take you add up, and then you build up statistics. All right. So you can see that after about 10,000 cycles, if you have LSMO as a top electrode, LSMO as the bottom electrode, nothing really happens to HZO, right? So HZO remains as it is. But if you have gold as the top electrode, initially you start with a gold which is in the rhombohedral phase, and later on you start getting a phase mixture. So you have a monoclinic phase and you have a rhombohedral phase. So both of them start appearing, right? So and then, okay, so let's go back to LSMO again. So so is there any difference in hafnia when you actually polarize it down versus polarize it up? I mean, from TEM, you can see that in LSMO changes its structure a bit. So it is not exactly perovskite, but it's moving to this structure, which is at 2 volts, this structure, which is a combination. And this is on the top layers. So at the interface with hafnium dioxide. So it moves to this structure, which is a brown millerite precursor structure, right? So which has this alternating, which has this square pyramidal, like MnO5 octahedra, quite disordered in nature. But nothing really happens to hafnia. I mean, nothing significant happens to hafnia. Maybe, I mean, there are subtle changes that happen. It actually looks quite rhombohedral. So from these experiments, and then if you have gold as the top electrode, you see that as you keep increasing the bias, you keep increasing the monoclinic to rhombohedral ratio. So you keep increasing the monoclinic phase. And this is actually consistent with the fact that as you increase the bias, you are actually putting in more and more oxygen into hafnium zirconate, or oxygen vacancies into LSMO. As a result, these oxygen vacancies have nowhere to go. They should stay inside hafnium dioxide itself, which is a very thin layer, about 5 nanometers of hafnium zirconate. So it is accepting all this oxygen, and then it has to change its phase eventually, right? So it goes to an oxygen-rich phase, which is the monoclinic. Yeah, so before I conclude, let me just give you finally how the dynamics looks like. So far I said we can do all these dynamical measurements. We can see how the hafnium lattice parameter is changing with at a resolution of 1 millisecond. And if you actually do that, so there is a slight change of hafnium, lattice parameter, and this is very small strain. I mean, this is even 0.002% or something like that, and this variation is in picometers. But you can collect it because you're able to measure such large statistics, and so it is, and so with ferroelectric switching, the way the ferroelectrics are also piezoelectrics, conventional ferroelectrics are also piezoelectrics. So if you look at how the lattice parameter of something like PZT changes when it is ferroelectrically switching, it follows this butterfly kind of loop. Okay, and then these things here are consistent with where the coercive field should be, which is where the polarization up changes to polarization down, right? So the maximum of that is where this upturn of the Euchre begins, right? But here you can see that there is absolutely no correlation. So these are the ferroelectric switching peaks, which we obtain simultaneously when we are doing these lattice parameter measurements. There is absolutely no correlation between the coercive field and how this, the lattice parameter is varying of hafnia. And we are slowly trying to, we are slowly coming to this realization that this actually happens because of, some increase in, again, this is related to oxygen vacancies. This actually happens because of some net increase in oxygen vacancies in hafnium dioxide when you apply bias in both positive as well as in negative direction. But this is some data which is still under analysis, and this is what Pranav has been working on currently. Just to summarize, so what is happening? So when you have an oxygen conducting electrodes on both bottom and top electrodes, as both top and bottom electrodes. So this is a source, this is a sink, right? And here's a highway of oxygen vacancies. Hafnium zirconate is just a highway of oxygen vacancies. You have a destination 1, you have a destination 2. So your oxygen can easily flow from destination 1 to destination 2 through this highway, right? And then it can flow back. It has to go back to its home. So it goes back to its home when you change the bias. And this is what is resulting in ferroelectric switching. But if you have something like gold, well, the destination that you have, the people there are not really accepting you. They say, why are you coming to our house and all these things? So you have to stay on the road for a longer time. So when you apply bias in this direction, you just, so you put in oxygen vacancies from hafnia to here. And then when you apply bias in the opposite direction, this is actually how the oxygen vacancies are stored. So hafnium,
I just very good.
This is the last slide. This is the last slide.
Very.
So this is the sink and source of oxygen vacancies, and that's why you see all these weird phase changes, and so you put in oxygen vacancies for a long time, they change their phase. Okay, so what we show actually from this is, what is important here from an atomic scale, we show this is that oxygen voltammetry, which is what people in battery community speak about, not the ferroelectric people as much, is very much intertwined with ferroelectricity. In fact, that is most likely the reason for the ferroelectricity and all these discrepancies that I'm showing, right? And these oxygen conduct. So then we also have design principles. Why only hafnium dioxide? Can we use any oxygen deficient, material to carry out this new type of ferroelectricity? Yes, that is something we have to test and actually find out, right? So that actually results in newer proposals that we can think of to have these interfacing electrodes which are oxygen reactive and having an oxygen conducting layer in between, which is a highway. Okay, so with that, let me just thank you for your attention, and then let me also take questions now. But I would like to say, if you have any questions, please email me. Just a couple of announcements. So we, so after the corona, we are also looking for, at least I am looking for bachelor's and master's students who are interested in long-term internships. Motivated PhD In-situ microscopy, please do write to me, and then we can see how to go from there. And the last two announcements, since there are industries here, so we have this very nice ecosystem right now for what is called INSENSE in Center for Nanoscience and Engineering, and IAC in general. So if you have ideas of making new holders, or so how to all these, the in-situ technology is currently not an optimized technology, believe me when I say that. So if you have new ideas, startups and other things, we are very supportive of this. And even more established industries, you can use clean room facilities in so there is a very well-built professional ecosystem built for this. So please make use of these opportunities. And I think this is a very nice conference to say that there should be more academic industry collaborations to move this forward and not miss the boat, so as the other countries are doing. All right. So let me thank you for your attention, and I'll take questions.
Yeah, thank you, Pawan, and really a very nice talk and clearly presented. And the session is open for questions. Couple of questions, I would say. We are running short by about 10-15 minutes, at least 15 minutes, but I hope we'll cover it up. Thanks for completing the talk in time, Pawan. So it's open for questions. So I think if there are no questions, I think as he said, he has already given you some email account. Please contact him, and we move on to the next speaker. This is Dr. Arup Das Gupta. Dr. Arup Das Gupta is right now a senior scientist at IIT Kharagpur. I would say, of course, so he has contributed to the Electron Microscopy Society immensely, I would say. He was also the General Secretary a few years back, and he He's always there whenever we have any conferences, workshops. He always come forward and gives wonderful talks. And I think before he joined IIT Kharagpur, he did 1 year training. He was in the training school of ERC and then did masters from I think IIT Kanpur, sorry, IIT Kharagpur, right, Arup?
Yeah, I was not from training school,
Oh,
but I did
that's
my
right. You're
MSc
right.
MTech from IIT Kharagpur. That is correct.
See, you were such a good friend of me, but still I thought it's from Kharagpur. Okay, that's good. So anyway, I think he has been working in electron microscopy for more than 2 decades, and certain areas of diffraction is very specialist in that one. So I request him to give his talk in this seminar, and it's a welcome, Arup.
Thank you, Satyam. And yes, I will try to stick to time. I know that you are a very strict teacher. So anyway, so basically, I am really thankful to the organizers, in particular, Professor Krishanu Biswas and also Chandrasekhar Tiwari, and also the EMSI for hosting me. I'm glad to make this presentation. I am also very much thankful to my previous speaker, Pawan, because he has covered so many of the introductory slides, which I just now deleted. One is, of course, on the holder. It's similar. It is the Nano X, which we use to do all the in-situ work. And he has mostly presented how it works. And also the IDPC and DDPC, so which we have the facility now at our center for doing the IDPC and DDPC in our themis. So basically, I'll be making a presentation which will be a mixture of the in-situ heating work together with some in-situ heating in XRD for corroboration of the data, and also some advanced microscopy in the themis. And I'm also happy for Pavan. He has covered so much of the oxides, because I will also be talking about oxides. The only difference is that these are not ferroelectric materials, but then we are talking about structural materials in which we put the oxide to strengthen them for operating at higher temperatures. So as I said, I'll be talking about the structure of dispersoids, the so-called oxide dispersion strengthened materials. I will include works from many of my colleagues like Sham, Vaishnavi, Shivakumar, Pradyumna, and others. If you have any questions beyond my talk, you can always email me. So basically, as I said, the ODS structural materials are many, and they are one of the most exotic and possibly a futuristic structural material which can withstand really high temperatures. The only issue is that you cannot make them by normal melt route because these are oxides, but you have to do it in powder metallurgy, and gels quite well with all the 3D printing and stuff like that. So basically, we are presently working on 2 classes of materials, oxide dispersion materials. One is a ferritic martensitic steel, which is for our fast breeder reactor core applications, in which we make the fuel clad tubes for the future fast reactors, and they need to withstand something like 700 degrees centigrade. Presently, we use austenitic steel, but then the austenitic steel has problems of sensitization and also has a FCC close pack structure, because of which they are not, they have poor void swelling resistance. And if you want to increase the lifetime of the fuels and reduce the cost, you need to use the open space ferritic steels. The other material is, of course, the nickel-based superalloy, alloy 617, in which we put the ODS. They can really go up to 1100 degrees centigrade, as they do not have any phase transformation right up to their melting point. And it can be used with very high temperature reactors and even gas turbine applications. So basically, the dispersion strengthening, a small introduction, and some of you, of course, already know about it. It is a material in which we disperse small oxides. Ideally, they need to be small and also separated by small distances. So if the size is R and the separation is lambda, you can actually calculate what is the shear stress that is required to move a dislocation across these dispersoids, and they leave behind a loop. And thus the strengthening occurs which is both dependent on R and then lambda. So basically what you need is a uniform dispersion of dispersoids. So you cannot put the dispersoid so that they are clustered in one place. They do not get the required strength. And also you cannot put a lot of them, because we have done a study in which we have put quite a significant amount of these oxide dispersoids, and we have observed that the just like biological cells, the metallic grains really spit them out, and you get a kind of glassy interface. The result, when you do it properly, is a very coherent interface between a dispersoid and the matrix, which we will see in more details in the coming slides, and you get a significant enhancement of the strength. So the processing steps are, of course, involves mixing all the powders. We have the pre-alloyed powders being mixed with your oxides, tiny nanocrystalline oxides, and you then mill it to that they are nicely mixed, and then alloyed as well, and then it is scanned, and then you have a high temperature extrusion, and then you can form all the shapes. And we have made as long as 3 meters of long clad tubes, which are of these dimensions. ID and OD are of the order of 6.15, 6.6 millimeters, which means the wall thickness is about 400 micrometers, which is quite good. This work was done in collaboration with ARCI Hyderabad and NFC Hyderabad, of course. Well, as I said, I will basically try to stick on the oxides because of the paucity of time. And as I said, they are ball milled. And then we are actually working on 3 types of oxides: the BCC yttria, and we also synthesize the ex-situ pyrochlore structured Y2Ti2O7, and also the monoclinic zirconia. But I will stick to one and not confuse you with all this stuff. So what I'm showing you here is a X-ray diffraction pattern of the yttria powder as you keep on doing the milling: 0 hour, 4 hour, 8 hour, 15 hour, and 30 hour. You start with cubic, and then gradually start getting the monoclinic phase, and then it is completely converted to monoclinic yttria at about 30 hours of milling. And this way, actually, we have found out a method to produce monoclinic yttria, which is not available in the market. And it is a metastable phase. And we have found that it is stable up to some 350 degrees centigrade. And then we can produce in any quantity that you want. So the other things are that, see, the volume fraction of the 2 phases as the milling duration progresses is the cubic decreases and the monoclinic increases. That is what you saw just now. And if you see the strain, which is very interesting and plays has many roles in the transformations that are happening. And both the phases are extremely strained as the milling duration increases. Since the milling is something that you can sort of compare with pressure. I do not know if you can compare with hydrostatic pressure, but definitely there is pressure from all directions to the powder particles, and they get milled and they become of finer sizes. As you can see here, the crystalline dimensions of the cubic decreases, and then this is where the monoclinic is nearly stable at a lower size. This also shows that the monoclinic yttria stabilizes at the lower sizes. And we also observe that if you continue to mill, it also becomes amorphous to some extent beyond monoclinic. And if we go to the TEM and also try to do the same size, there is very clearly you can see the monoclinic is out here and the cubic is much bigger in terms of crystalline dimensions. So therefore, as I said, the monoclinic yttria is only a metastable phase. We need to study its stability and then how it actually evolves as you heat it in an in-situ heating device. So in this case, we will talk about the TEM as well as the X-ray diffraction. And this will try to help us to understand the transformation, and which actually governs the dispersoid structure and chemistry in the materials that we are talking about. So to start with, in the in-situ heating holder, of course, this is the structure which Pawan also showed. So you have a resisted heater, and basically the MEMS chip is used to read the temperature very precisely. So the control of temperature is very, very precise in this system. And you have a large number of, this is a silicon nitride grid, as I told you. And there are a large number of holes of various dimensions. And you need to try to go into these holes, try to do your imaging. And we have ramped it up from room temperature of about 22 to 23 degrees centigrade up to 1000 degrees Celsius in about 6 hours. So this is a 6-hour duration experiment. And while we have taken a continuous video from here to here, at each of the ramping stages, we have also paused and taken images in various locations so that we get the proper high resolution imaging. And then we also have generated the time-lapse images of this entire experimental process. So this is a video, doesn't tell too much, but you can carefully look at, you can stick to some locations and you can keep looking at them. And so this is running now at about 84x, because this is a 6-hour experiment, as I told you. No point in showing you everything. So initially, you see the thermal drift is very high, and the holder sort of stabilizes as the temperature increases. And you will see that there are changes happening here and here and here. So these are the crystallite transformations that are already taking place 350 upwards. And here you can clearly see that the moire fringes, that some crystals below are growing. There is no growth as such, but there is a transformation, of course, that is going on out here. Anyway, I'm going to show you the time-lapse videos of these as well, and the analysis together with that. You can see somewhere on the north as well, all these things. Yeah, and it runs for some more time. So let's go up to 1000 degrees centigrade. And it's 650. What I wanted to show you is, maybe let us go a little faster. There is also escape of atoms at the high temperatures. So if you look at the bottom, which looks like a beehive out here, it's decreasing, and as you can see, it's really become thin. So it's evaporated. So difficult to do repeat such experiments within a microscope, because you might contaminate your column as well. So briefly, these are the 4 regions we will try to concentrate. Okay, region of interest 1, which we call a beehive type. So just for the sake of remembering, this mimics sort of Gujarat. And if you go here, this is a bridge which you can concentrate. Interestingly, we also have a region. This is, of course, on the silicon nitride and not a hole. And there are fine filaments. They are basically amorphous. And we will see what's going on. This is the SAD from the entire region. And this big plate here out with the diffraction is characteristic of monoclinic. The entire phase is fully monoclinic to start with. So if you go for the time lapse from here, yeah. So these are the time lapse experiments. What you need to do is that please concentrate on the FFT, and you will clearly see that the phase evolving out here. So this is a 211, possibly the most unique peak to begin with. So the 211 is really developing, as you can see, as the temperature has gone up to 1000 degrees centigrade. So what we have done is that we have tried to see how, where, and how these are the new phase, whether it is just atomic transport of the existing phase, or they are nucleating and growing from one of the interfaces. What is interesting is, if you see here, so this is a Bragg filtered image, looks very ugly because we have taken only the 211, but at least gives us an idea that it started all over the place. It's not that it has nucleated, it's possibly the atomic transport. The results are very new and we are still analyzing, but we still believe that it is, the phase is just atomic transport, that's monoclinic. By that there is a movement, shear movement of the atoms going over to the cubic phase. So if you see, this is at 1000 degrees centigrade, of course, and it has fully converted. You're not seeing the whole thing as Bragg filtered. That's because I have chosen just one plane, and this is polycrystalline. So now if you look at the bridge type structure, it's all the same. Again, keep looking here. See, just about 350 or 400, this keeps coming. And you can see, of course, the crystallinity is improving. But the problem is, when it is at high temperature, your atomic movement, the thermal vibration of the atoms are so high that it is difficult to retain the atomic resolution unless you stop and then image it again at every stage. So doing this again at this is, of course, at 600 degrees centigrade, and you see here, again you start seeing the filaments, and then at 1000 degrees centigrade, yeah, it's nearly done. The only thing that you need to look here is that it's initially, if you remember, the cubic crystals were bigger and the monoclinic were smaller. So there was, of course, a size effect. But it is very interesting to note here that even the cubic phase exists in a smaller size also after this kind of transformation. If I go to the another region, which I said looks like, kind of Gujarat, and you see same, this is more crystalline. You can see very spotty patterns of the 2-on-1 right in the center out here. The monoclinic is going out and it's gone. It's highly crystalline. And the same way we can try to see, and yeah, this is only at 650 degrees centigrade, and it's coming up all over the place, the new crystals. And at 1000, it's done almost very nicely crystalline. So regarding the amorphous, of course, it is, you see, this is possibly the most interesting part, and these are on the membrane, and now are the crystallites which starts appearing. So you see they are all crystallites that's happening. Okay, so basically even the amorphous phase is also crystallizing at about 500 degrees Celsius. So if you go to if you zoom into one of the crystallites which formed out of this amorphous things which we started up, and then they're very nicely crystalline, of course. So after annealing, this is what we have received, a fully cubic structure. And if you clearly remember that before annealing it was this way, and so after annealing, yeah, you can compare. You can see the difference. The structure remains the same, and possibly crystallite size also basically remains the same, but you have got a transformation. So you end up getting a finer size of the cubic crystals. And as there are a lot of papers, even for zirconia and yttria, both, that if you want a transformed phase, metastable phase to stabilize, you need smaller sizes. But we have a methodology in which now we can stabilize even the cubic phase in the smaller sizes. So we try to repeat this in the X-ray diffraction. If you look very carefully, so the blue is the monoclinic line. There is a shift; it continuously moves right, and the red one, the orange one, is a cubic. See, at 1000 degrees, it's completely converted. Now, I just now showed you that there is no big difference in the size of the crystallites. So that's it becoming, that it is becoming very sharp. It also indicates that there is a relaxation of the strain at high temperatures, which is obvious. This is happening due to relaxation of the strains. So now this is all about the in-situ stuff and some applications of this, and we put these oxide crystals, nanocrystals, in the steel, and finally this is the structure of a clad tube, basically thin wall clad tube, and you get the martensitic structure. This is ferritic martensitic with the oxide dispersed all over the place. This is dark field. As you can see, the size is peaking at 5. I showed you right in the beginning, you need to have a system in which your dispersoids are dispersed in sizes of around 5 nanometers, so that the separation remains 5 nanometers, because the volume fraction of the yttria you can add maximum is about 0.5%. So given that conditions, you need this 5 nanometer is a kind of a magic number that you need to achieve for this kind of applications. So if we zoom it up, of course, this is distribution. So for the sake of the studies, we concentrated on some of the larger dispersoids. This is how they look in Hadaf, bright field, and dark field. And if you do an EDX, you will see that all of these are rich in yttrium and then titanium and also oxygen. So basically YTIO kind of dispersoids out here. Titanium is what it is getting from the alloy composition itself. If you zoom into one of these dispersoids, a very complex structure, and it's not uniform because it is large. So this is one reason that they need to be of smaller sizes so that you can get uniform composition everywhere. Otherwise, if they are big, they're really non-uniform, looks like this. A lot of matrix elements also enters into them. So a lot of dispersoids, people who present papers saying that matrix element have entered into their system are relatively coarser dispersoid. The finer dispersoid, very fine, I mean 5 nanometers or less, the matrix element really don't enter the dispersoid stream. So now basically the problem to do high quality research in a aberration corrected microscope using a magnetic sample as the ferritic steel is very difficult. So it's a boon actually to have the alloy 617, which is a nickel-based superalloy, and does not interfere with the magnetic field of the objective lens coils. So they're very stable and you can work with them. So to start with, what you see here is atomic column chemistry of the matrix. So you get a lot of nickel and chromium and cobalt. This is, by the way, EDS mapping of the atomic columns, and this one is HADAP. So this is the alloy composition mostly. Apart from that, you also have some iron and molybdenum and also a little bit of aluminium. Please remember that it has aluminium, because what happens is that the yttria being an oxide, and at high temperatures when there's a lot of diffusion of bond elements, these oxides actually attract all the other oxide forming elements. So in the previous case, it was titanium. In this case, it is aluminium. The aluminium is attracted towards these oxides, and sometimes they enter into their matrix and form YALH compounds. Depending on the type of aluminium, they have different kind of compositions, of course. Sorry. What you have here is basically a panned image of a HADAF, of a large area of the sample. If there are carbides, of course, you will get carbides, chromium carbides. And what is interesting to note here is that, this is a HADAF image. So there is Z contrast, right? So atomic number contrast is always there. Some of them are looking bright, some of them are looking dark, and some of them even have core shell structures, and some of them biphasic structures. So these are all very interesting. I will not have a large amount of time to dwell into all those things, but just to show you briefly, so these are the white dispersoids, measuring about, you see, 10 nanometers here roughly. And if you go into the EDS and yields from across, this is a line spectrum across this, you will see that it is enriched in, of course, your yttrium, aluminium, and then oxygen, but also the matrix element like nickel, chromium, and all have not gone down to zero. So presence of these matrix elements into this, in spite of the high Z yttrium and the low Z aluminium, it appears bright with respect to the matrix, which means it has an effective mass or effective Z, which is greater than the system. So that's why it appears bright in the HADAF image. The same way, this appears darker because there is a large amount of aluminium in the system. Okay, so aluminium is quite high, so it starts appearing dark. What is interesting is we do have some biphasic also systems, which tells a lot about this aluminium diffusion and then coming together and then getting inside. Sometimes they're not able to get inside, they just come as a cap, around the yttria and so on. So as you can see here very clearly, there are two steps here. So basically one step here and then down. So these are, you get what is, this is the darker one is aluminium oxide actually. It also picks up oxygen from the matrix as it travels. And then this is actually YAL and so on. So this is briefly about it. And how much time do I have, Satyam? Hello?
Yeah, you have 5 minutes.
Oops, okay, fine, thank you. So basically, this is a IDPC image that Pawan was talking about. And this is this integrated differential phase contrast in the themis. And you can actually see, so these are actually your yttrium atoms within these dispersoids. And these are your aluminium atoms. And within these, the smaller ones are actually oxygen. So you start seeing at these light low Z elements in a TEM is very exciting. And as of now, we have seen up to carbon, and with respect to carbon, oxygen is quite easy basically. So if you concentrate on the interface, basically, so we use a simulated image of the atoms on top of it. So the red one is basically yttrium, green one is of course aluminium, and the blue ones are oxygen. And so this is basically a hexagonal close pack structure by YLH. And this is the nickel-based matrix. And you can see there is almost a one-to-one correspondence at interface. The interface is nearly
No.
Yeah,
No sound.
his net connection has some problem. Dr. Dasgupta, are you there? Hello. Maybe Chandrasekhar, can you call him?
Yeah, I'm trying to reach him.
Yeah, see, his screen is also gone. So he has to rejoin.
Yeah, so I think before he rejoins,
Next speaker is, I think, Dr. Professor Praveen Kumar. Yeah, he's there in the panel.
so what about Dr. Guru Rao?
Yeah, that's what I'm trying to reach him. He's there, but he is not able to join in the panel. I don't know. Maybe he's using web to join the panel.
No, I am there.
Called him. He's
Hello?
not taking.
Hello.
But you cannot present. Are you able to see the share screen button?
You make him, no? Make him as a co-host.
No, he has to. No, there is a problem in this. This is not like a normal Zoom. Here, I have to make first him a panelist.
Nilesh, you can share your screen and we can change for you. That should not be a problem.
You
You can send email the PPT to either to me, Krishanu, and we can change the slide for you. That should not be.
It's okay, but you can try join using the app.
So before, I think I forgot to inform about Arup, little more details.
He's joining.
So,
He has some internet connection, so he's joining.
Yes. So I just thought I will let him join. He completed his PhD from IACS, and also, he was a postdoc in English. He joined IGCAR in 2000. He was also a fellow of Electron Microscopy Society of India, and he had got several awards. One is Young Physicist Award. Is he joining now?
Yeah, but Professor Dr. Dasgupta, you are muted.
Arup, you are muted. So again, the network issue, Arup, looks like he's frozen.
Yes. They don't use Zoom. Zoom is not allowed.
Yeah, that is right.
And they're using from home, so that's what the problem is.
So
I
was just telling him, he has got a lot of laurels. One of them is young physicist and also young engineer. So he is very rare occasion that you can get both young engineer award from INEAE and also he got a DA. Yes, now. Yes, I can hear you. I'm telling something good about you.
I don't know what happened. I think I just switched over to my second connection. Shall I continue?
Good. Yeah, continue.
Please.
Do I have time? Okay, give me some time.
2 minutes?
Yeah, I'll finish in 2 minutes. Just a minute.
Okay, thank you.
I was almost there. Share screen and this. Can you see the screen?
Yes, you can see beautiful.
Okay, so I think this is where we stopped. So this is the monoclinic atria, and it is because of the complex structure, it doesn't seem to mate well with the nickel-based superalloy matrix. The matrix, the interface is, so if you zoom in, so what we see is matrix is composed of basically a non-stoichiometric aluminum oxides. So if you see, these are the simulated images, and of oxygen is there, but the aluminum are not there in all places. So they are partially occupied, as you can see from here. So the conclusion is that when the structure is complex, you try to get a core shell structure, because many people report the core shell structure for the dispersites, and it's not a rule of law. It doesn't happen always. Sometimes you get this. So with this, I am coming to the end of my talk. I would like to thank all my co-workers in my group. Chanchal, I think he is still attending from Sandia. He will be back soon. Pradumna, he has just graduated. Alfish is still doing. Sham is a visiting scientist from IISc and Max Planck, and he has joined us recently. Raghavendra graduated and left for Quebec, and Shivakumar is about to submit. So is Savikumaran. Tirupati has left, and then Vaishnavi, Sripriya, Akhil are still doing. Kannan is the engineer. I'd also like to thank my peers, the director of the center, Dr. Bhaduri, and director of the groups and subgroups, Dr. Saju and Dr. Raju. scientists of the other groups at IGCAR, ARCI, NFC, and of course the organizers of this symposium, Professor Krishanu Biswas, Chandrasekhar Tiwari, EMSI, and of course Professor P.V. Satyam for being the chairman of this session and giving me this opportunity. Thank you very much.
Thank you, Arup. And actually, you did make up for a lot of time as well for us, and completed thing with wonderful images and a lot of OSD work. So the session is open for questions, couple of questions. There is somebody.
So Satyam,
Somebody has raised hand.
Can I ask a question, Satyam?
Please, sir. Please, sir. Please, sir.
Arup,
Yes, sir.
great talk.
Professor,
Enjoyed
please.
listening to that. Good
Thank
to
you,
see
sir.
your microscopes working very well also.
Yes, it is.
And well, the one thought I had, and this also is a consequence of Eric Stark's talk yesterday,
Yes.
something Pavan mentioned today, something you mentioned today, and that heating stages in TM are clearly, we have to worry about evaporation.
Yes.
And that might significantly complicate the kind of results that we observe.
Yes.
And I was wondering if there's a case, and is it possible at all that we can do heating only in gas cells such that we avoid this evaporation problem? I don't know too much about gas cells and so on. That's the question.
Sir, our plan is as follows. So all the heating experiments that you saw today were carried out in the Talos 200 FS.
Right.
Not in the Titan. I would not like to contaminate that chamber.
Okay.
So what we do is that, as you can see, that the transformation has started as early as 300, 350 degrees centigrade, where evaporation is not there. So we plan to now take another sample to the Titan and then limit the temperature to 200, 250 and try to do it in the stem mode. As you can see, beyond 350, the holder is very stable. So, and we can do, so all the experiments that I showed you today were in the TEM mode. You have used a parallel beam. So our Titan is basically more of a dedicated stem. So we need to do stem. So therefore, I think we plan to do it at around 400, 450 and try to catch the actual atomic migration at that stage in the Titan and not raise the temperature beyond 500 in the Titan.
Okay. But what I was trying to get at is, if we do have to look at higher temperatures, should we only do such experiments within a gas cell such that evaporation is prevented? Is that possible at all?
Can I comment on that, Professor Banerjee?
Anybody? Yeah.
So I think even in the presence of gas, actually the pressures are still significantly low. It is only slightly better than in vacuum. So I think evaporation will still be a problem.
Well,
higher the temperature, worse the problem will be.
Yesterday, someone talked about 1 atmosphere gas cells. So I was, that's what I was, that's what provoked the question. Yeah.
So I think, for example, even under normal conditions, in ambient, for example, the higher temperature you go, the vapor pressure keeps on increasing and there'll be significant loss of material. So 1 atmosphere may be some very, very special thing actually. So it may not be possible in all the...
Besides, there is one more point to think about. These transformations of nanocrystalline materials are very much ambient pressure dependent. So if you are going to have different kind of vacuum, these temperatures may shift up if you increase the pressure. So whatever we are seeing at 300 may be appearing only at 500. So we have seen this very characteristically. 2 things about nanocrystalline materials transformation. You never get a first order transformation in nanocrystalline materials. You will have a very broad transformation starting much early and ending roughly at the temperature where even your alpha to gamma transformation in steels are very, very wide, even if you put it in a DSC. So this is very characteristic of nanocrystalline materials. Second thing is the temperature at which the events will happen will depend on pressure.
Yeah, I thank you all. I just was wondering, Professor Banerjee's concern, is it because of the deposition onto the lenses?
Yeah, no one wants to contaminate a column.
Is that the main issue, or
also this phenomena itself is dominated by some other process which is not your main thing? So that is the evaporation. You don't expect it to be, but that sometimes dominates. So it's not, you're not really seeing what you want to see. I think that was the point.
As you see, if you go up beyond the melting point and you did see this evaporation, so vapor pressure goes high. These nanostructures, they have a very low melting point. That also plays a role, right? So I think we move on to the another. Is there anyone asking question? Pawan, do you have any question to ask? No. Somebody has raised the hand, so I was just wondering. Okay, so if there are no more questions, let us thank Arup.
Thank you.
And thank you very much for a wonderful talk.
I think Dr. Dipankar Banerjee raised hand.
Yeah, I think. Sir, do you have any more questions, sir? Professor Banerjee? But he's muted, so we cannot able to. I think we'll come back.
Okay, I can have the questions in email and I will love to answer. There's no problem.
Yeah, sure. Now, what is missing is students, questions from students is missing. So that would have been nice. I think I request the students to ask questions. Make use of this.
You can use chat box to write the questions.
Yeah, I'm watching chat box, but I don't see in the chat box.
The only way you'll get students to ask questions is to say that you'll subtract marks from their exam. I've come to this conclusion.
That's a good conclusion.
Yeah. I did that for my class this time and it worked very well.
Yeah.
Krishanua Chandrasekhar, lesson for your next seminar.
So minus 50, they'll get minus 50 out of 100 if they don't ask questions.
Right, exactly. Okay. Thanks, Arup.
Yeah,
Okay.
Thank you, sir.
Yeah,
Thanks a lot. Thank you.
Thank you. And we move on to the next talk. So I think I just wanted to Krishanu is Praveen or
Nilesh.
Nilesh is okay. So we'll welcome Nilesh. I hope Nilesh can share the.
I'm sharing Colin here. Can
Okay.
Can you see now the screen?
Yeah, we can see that one.
Okay.
So Professor Nilesh Prakash Gurrao is the associate professor in IIT Kanpur. He did his bachelor's in BNIT Nagpur and PhD in IISc Bangalore. And he has several awards. He has IMSI Medal for Young Scientist, Young Metallurgist Award from Ministry of Steel, and he also had a IMSI DFG Bilateral Exchange Fellowship. He is also known to be a very good teacher. So he got a teaching excellence certificates from Director IIT. And the more important thing is he will be, I think, also has a complementarity with the synchrotron, in-situ synchrotron radiation research. So I suppose he will be talking about the complementarity as well. So Professor Nilesh, welcome, and please proceed with your talk. Thank you.
Thank you, Professor Satyam. First and foremost, let me thank the organizers for not just inviting me, but also for agreeing to change my slides. So what I'm going to talk today is about going a length scale above than what we have been talking for probably the last 2 days, with the exception of the last talk yesterday, wherein Ehsan talked about in-situ EBSD. So that is what I'm going to focus on and try to impress upon you the advantage that electron backscatter diffraction in a scanning electron microscope offers, which is suitable for deformation, phase transformation, and recrystallization studies, which are important in metallic materials. So if you can move to the next slide, what I want to emphasize is like this is going to be the overall outline of my talk. I have chosen 2 simple case studies. One is based on titanium, which has a hexagonal closed packed structure, and it shows anisotropic mechanical behavior. And we are going to look at the mechanical behavior not just in uniaxial tension, but also for load reversal and for cyclic loading. And for a aluminum magnesium silicon alloy, wherein we see that as a function of temper, as we go from solutionized to say a p-cage condition, how does the mechanical behavior change, and more importantly, how we can help this knowledge and combine the observations that we make using in situ electron backscatter diffraction to develop new constitutive models. So this is what I'm going to emphasize on. So we move to the next slide, and I'm going to start with again the slide which was this graph that you are seeing on the right hand side. This was shared with me yesterday by Professor Biswas, wherein this is the latest paper that has been published in Nature, which talks about breaking the so-called strength ductility paradox, wherein you go away from this banana curve for obtaining a good combination of strength and ductility. So whenever we talk about structural properties, it is not just about high strength with sufficient ductility, but one also needs to worry about what is the fracture toughness, and also how does the strength and ductility vary as a function of temperature. Similarly, not just the monotonic deformation, the cyclic deformation as well as dynamic or high strain rate response, depending on the application, is important. The major emphasis for all these studies is lightweighting for transportation, for energy saving, and therefore this has led to a lot of emphasis for kind of improving the specific strength of ferrous materials, as well as for developing new non-ferrous, for instance, titanium and aluminum alloys. And of late, the major emphasis has been on in terms of manufacturing process, on additive manufacturing, and there is a lot of emphasis also on the so-called complex concentrated alloys or high entropy alloys, because they offer a much wider composition space, and by the logic, it is expected that they will offer us a design space or a property space that is not explored yet. So if you move ahead to the next slide, what we will see is that in terms of simple, a mechanical behavior course, if you were to tell how to make a material stronger, you have to make the motion of dislocations difficult. On the other hand, if you want to get ductility, you have to get strain hardening. Now, how to make dislocation motion difficult? Well, we are aware of all different strengthening mechanisms, starting from grain boundary strengthening to precipitation hardening to solid solution strengthening, while making mobile dislocations available at all the strains, or at particularly at higher strains, is a little tricky. And this can be done by accommodating or by giving access to additional deformation mechanisms. So unlike simple slip, you can also have twinning, or we can have transformation, wherein you can get from FCC to BCC, martensite, right, like austenite to martensite transformation, or these days in complex concentrated alloys, it is from FCC to HCP martensite, which is not just a one-way transformation, but also a two-way transformation, right? So you can also get the HCP to FCC reverse transformation. And this is where, to study all these processes of slip, twinning, transformation, or reverse transformation, that is where our EBSD becomes important. And all these processes, when we talk about, we have to worry about the reversibility of it, because when we are doing monotonic deformation or deforming only in tension or compression, dislocations are going to move in one direction, or like your transformation or twinning is going to occur in one particular crystallographic direction. But things become interesting whenever we talk about cyclic loading. So if you move to the next slide, what we will see is a simple stress strain curve. And now if you look at this simple stress strain curve of a ductile engineering material, say something like aluminum or copper, if you are a design person, you are more interested, in the part of the stress strain curve up to the yield strength. While if you are a processing person, you are interested between the yield strength to the UTS, right? Because that is where you want to give shape. And if you are looking at the failure processes, right, if you are a fracture person, you are going to look from the UTS to the fracture stress. And during all these processes that are happening, conventionally what we have been doing is to pick out samples at different values of strain and do post-mortem analysis. And this could be conventional SEM or optical microscopy. And with the advent of electron backscatter diffraction, we could obtain information about the crystallographic texture, the grain boundaries, the interfaces that we have, and we could comment again about the operative mechanisms. And here I would like to mention that if you look at a polycrystal in itself has a lot of heterogeneity in terms of grain size, in terms of defect content, for that matter dislocations, and the entire process of plastic deformation in itself is heterogeneous. So this is where EBSD has an advantage because it captures the heterogeneity of deformation. And that is why if you see for the last 20 odd years, any paper on deformation, be it not just simple tension or compression, but any kind of deformation, you will always find electron backscatter diffraction, few maps from electron backscatter diffraction. So on the next slide, what we will see is that we will do a SWOT analysis, which is the strength, weakness, opportunities, and threat, what EBSD offers. So that kind of analysis, if we do for EBSD, it certainly loses out in terms of the spatial resolution to a TM, while the angular resolution is not as good as, say, X-ray diffraction. But in EBSD, we can get information in the reciprocal space. So you can see over here on the left hand side the Kikuchi pattern that you are seeing. So you can literally look at the information from the reciprocal space, which gives you a lot of information on the defect structure. On the other hand, you can simultaneously also make an electron image. So you are also getting a glimpse of the real space. So EBSD is one beautiful technique with the fast detectors that we have these days, which can give you kind of information from the real space as well as the reciprocal space. And with the advent of these stages wherein we can apply external stimuli, be it, tensile or compressive or cyclic load for that matter, or for that matter heating, we can study different deformation, recrystallization, as well as phase transformation processes. Mind you, all these processes are quite heterogeneous in nature, and EBSD can give you a glimpse of capturing all these processes. So if you move to the next slide, what we will see is that if you have a good tool that is good enough, and what I have seen over the last 20 odd years is that, whenever there is a new tool, so EBSD people use it as just another colorful RGB image. But as Francis Bacon said, that, a prudent question is one half of a wisdom. So it's not just with EBSD. If you have an in-situ EBSD setup, and we have not one but two at IIT Kanpur, the only trouble is we get slots once a 6 months. So the question is, what is the pertinent question that we try to address? And I will just say that many a times, I talked about optimum combination of strength and ductility, and this is again something that we know, that toughness is nothing but the area under the engineering stress strain curve. So you may feel that, oh, I want always high toughness, but that may not be necessarily true. So it is like there is more than what meets the eye. So if you look at a simple application, so what you are seeing on the right bottom of the slide is a crash box for an automotive. So this is the crash box, and if the crash box, in case of an impact, this crash box is supposed to absorb all the energy. Now, you don't want the crash box to deform a lot, right? Because you don't want the passenger to get injured. So it is going to take small strain, right? Strain of the order of 15 to 20%. So even if you look at the tube steel, which is shown over here, the twinning induced plasticity steel, and the age-old DP800 steel, which comprises of ferrite and martensite, you see that for a crash box kind of an application, the DP steel is a far better choice than your tube steel, because tube steel you don't really, your material is not, or your component, your material may see more strain till it fails, but your component, you don't want it to see a lot of strain. So therefore this is important. So therefore what I want to emphasize by giving this example is that just saying that, oh, we want to optimize the strength and ductility is not sufficient. You have to really look at applications, that at what strain, what toughness I am looking at. And therefore what I have kind of chosen are two very simple examples which do not have an application, but these are like two model questions or two model problems which we will try to address to build up as a case study. So what we have chosen is a hexagonal close pack titanium, wherein we are going to see slightly different stress strain curve depending on their crystallographic texture, right, or preferred orientation of crystallites. And what we have done the other way around is to look at, in the other case, look at the aluminum magnesium silicon alloy AA6061, wherein we look at, different classes of tempering where the texture remains more or less same, but there is additional strengthening because of the precipitate. So your dislocation precipitate and the overall dislocation interaction changes. So these two very different appearing but very classical problems we have chosen, and what I'm going to try and emphasize is how we can use in situ deformation to get better insight into the operative mechanisms. So we move to the next slide where we look at titanium. So titanium, hexagonal unit cell, as you can see, and because of the hexagonal unit cell, the C/A ratio is less than ideal, 1.588. So it is basically a prismatic slip metal. So wherein the prismatic A slip gets operative, and to accommodate deformation along the C axis, what we end up getting is your pyramidal C plus A slip, mostly the type 1 slip. Or if we move to the next slide, we will see there is the occurrence of twinning. Now, twinning is another shear process which is not exactly same as that of slip, which is gradual in nature, while twinning causes sudden reorientation. And why do we need twinning? Well, we need twinning because we do not have 5 independent shear systems which are needed for deformation of polycrystalline material. And the reason we need this twinning, and unlike simple twinning that we say in FCC, here in HCP materials we have what is known as extension and contraction twins. So what is extension twin? Extension twin is when our C axis is in tension, so we call it as extension twin, and when the C axis is in compression, we call it as contraction twin. So twins are very, very interesting because they help you in accommodating strain along the C axis. At the same time, the twins are going to make additional interfaces. So they lead to what is known as dynamic Hall pitch effect, right? And because of that, they contribute to strain hardening. But at a later stage of deformation, the twin matrix interface acts as a weak link where damage can accumulate and your void nucleation can take place. So twinning plays a very important role in the entire process of strain hardening till UTS, and beyond UTS, it plays a very important role in your void nucleation and subsequent void growth and coalescence and ultimate fracture. So which we will see in due course of time. So when we talk about twinning, twinning is not just like slip that, okay, there is one step of shear. And what has been has been clearly shown, not just using simulations, but also using experiments. And this involves a lot of transmission electron microscopy experiments, that twinning comprises of nucleation. So the stress state that is required for nucleation is different, and this generally happens at a triple junction or at a grain boundary because of a pileup of dislocations. And after that, there is this step of twin propagation, which you can see, right? So the twin propagates, and once the twin reaches the other grain boundary, the opposite grain boundary, then there is this process of lateral thickening. And remember, the thickness of the twin is decided by the twin shear. In case of FCC materials, the twin shear is very, very high. So the twins are much thinner, and we get these bundles of twins, which you can resolve using TM. But in a hexagonal closed pack material, the twin shear is not large, and we generally get thicker twins. Now, unlike simple motion of dislocations, which is simple shearing, all these motion, if you have remembered, the kind of Burger's vector I had, 101 bar 1, these dislocations are known as zonal dislocations. The reason they are known as zonal dislocations, because the planes in hexagonal closed pack, crystals, materials with HCP crystal structure are actually corrugated. They are corrugated, meaning that you don't just need simple shear, you need shear plus shuffle. And it is because of this that the CRSS for your twinning, if at all you were to assume a CRSS for twinning, the CRSS for twinning is higher. But nevertheless, twinning is extremely important in hexagonal closed pack material, and we need to understand what is the role of twinning by capturing the initiation, the propagation and growth, and if possible, the damage accumulation with twinning as a function of strain using in situ EBSD. So on the next slide, I will just show you the macroscopic behavior. So if you were to take a sample and do a stress strain curve, what we see that instead of having the stage 3, which is like the decreasing strain hardening rate, kindly look at the curve on the right hand side bottom. So that is the strain hardening rate, d sigma by d epsilon as a function of your strain. What we end up getting is a hump, and this hump that you get is because when the stage A ends, that is where twinning kicks in. Twinning kicks in, and because of twinning, there is dynamic Hall pitch effect, and you get strengthening. So the curve changes, so you get this additional strain hardening, and then you have again this decrease in strain hardening rate. So this is the additional strain hardening that is provided in HCP materials. Similar processes are also explored or exploited in twinning induced plasticity steels. But we could have looked at that, but we didn't look because, again, as I mentioned, the twins are much smaller. So titanium offers, or HCP materials like titanium, which are ductile, offer a very model case wherein we can study the role of twinning. So let us move to the next slide and see that I talked about twinning. And if we remember that in case of slip, the plus Burgers vector, positive slip and reverse slip does not matter. But if you go to twinning, twinning is polar in nature. So you cannot get, kind of twinning in positive direction, and there is twinning in reverse direction. So this is something that one has to keep in mind. Even for slip, if you do, take a single crystal and try to do tension and then do unloading and do compression, we get what is known as the Washinger effect, right? We get this Washinger effect because even our slip is not completely reversible, even in a single crystal, right? So this gives rise to a Washinger effect, which is a mechanical thing, right? Like you see that your yield strength in reload tension is different from what you had in uniaxial tension initially when you did. Right, so this is our Washinger effect, or for that matter, the way it is defined is like if you go in tension and then after that you do unloading and you do compression, the yield strength in compression is different from that in tension. So remember that, this is a kind of Washinger effect defined in terms of the mechanical behavior. In terms of microstructure also you can see, so this is like a simple, beam that is being bent, and I think Professor Praveen Kumar in the next talk he's going to talk about bending. So we'll all get to learn more about that, about bending in the next lecture. But here what I just want to emphasize is that here also you can see the force required is different, right? When you do bending and unbending. And not only that, you see that there is change in color, which corresponds to the orientation. So we can see that, there is textural change, there is microstructural change in terms of, the misorientation, right? What you are getting here, the band that is kind of disappearing. So you can see here on the right hand side. So all these are occurring concomitantly. So we want to capture this. Now this is only possible if you are doing an in situ electron backscatter diffraction experiment. So let us move to the next slide and see what exactly we are talking about. So the processes of detwinning, if you want to understand it in more details, we have to go to a TM, and already investigations people have shown that as a function of, stress, if you apply some deformation, how does a twin propagate, how it can interact with other twin or a high angle boundary, how the twin can get blunt, and how it can cause, a step formation at another boundary. So for finer details, we can go and look at these processes. And for this, we have to go to in situ TM. But we want to see it at the sample level, and for which we will go to the next slide and have a look at the tools that we have utilized. So we have this Gatan stage, one at our Advanced Center of Material Science, which I'm going to present here today, but we also have one at the Advanced Imaging Center. So this is the stage that we have. This is a good equipment because, you can do tension, you can kind of some way, do compression by just, bringing the samples closer, the jaws closer together, but we can also heat the sample up to 500 degrees centigrade. But let me tell you, if you go and look at the stress strain data that you are getting, even with digital image correlation, it is not very attractive. So what I would emphasize, and probably this has been emphasized by all the speakers before this talk, that we have to always complement it with bulk test, right? Maybe the bulk X-ray diffraction, or in this case, bulk mechanical testing, so that we have enough confidence in our data. So that is what we started with. And what I'm presenting now in the next slide is the work of Shubhashish, who kind of took a titanium block, a cold rolled and annealed block of titanium. You cut simple E606 standard tensile specimen from different parts of the rolled block, which you can see somewhere in the middle, and you do tensile test. You can see that there is slight difference in the tensile behavior. In the top left corner, you can see that, right? A, B, and C. You see that sample A shows, higher yield strength, rather lower yield strength, but higher UTS, while sample B over here shows higher yield strength, but lower UTS. And when you look at the microstructure, so this is like all tensile tests done. And after that, the samples, the tensile specimen were prepared using conventional metallographic polishing, and we do EBSD. I want you to focus only on the top row. As we move, increase the strain, you can see a lot of intersecting twins. While on the other hand, if you look at the second row on the right, you can see that the texture is different. You can see blue and green in the second row. In the first figure, while in the top it is you see a combination of everything. And here you can see as you move from the grip section to the fracture tip, there is more and more twin, right? But these twins appear to be parallel, unlike the ones for sample A and C orientation, where these twins are actually intersecting. So this will be clear in the next slide, wherein we see I have focused only on the A orientation for the want of time. So what we see is that in A orientation, if you look at the left hand side figure, there is there you can see a lot of twins. So these lenticular features that you are seeing here, these are twins, and these twins are intersecting each other, right? In smaller grains, you do not get that many twins, but you do get contraction kind of twins. So it is like a combination of extension and contraction twin. And what we see here is that we look at the Schmidt factor, so which is nothing but the cos phi cos lambda with respect to the twin plane and twin direction and the loading axis. We see both that there is Schmidt behavior, wherein, you know, a twin with a high Schmidt factor is observed, while on the right hand side, what you see is that the twin with a lower Schmidt factor. So if you see here A4 and A5, here the Schmidt factor is lower. So you can see here everything is red. So those twins are observed. While here the Schmidt factor is not very high, you don't see any red things over here. Still some of the twins are observed. So we get both Schmidt behavior as well as non-Schmidt behavior. And why does this happen? Because this Schmidt factor that we are calculating is a macroscopic Schmidt factor. While what is happening microscopically is different, because the stress state, as we have seen earlier, is that the twin nucleates at a grain boundary or at a triple junction. So what is the local stress state that we are not aware of? So this is something that one has to keep in mind. And there have been lots of work over in this area to find out the twin behavior, like where does it nucleate. So this is about the twin nucleation. Now, if we move to the next slide, we see that it is not just about the twin nucleation. You can look at different properties like the dislocation density, the geometrically necessary dislocation density, which can be determined from the lattice curvature. This information we are getting because we collect data in EBSD from in a pixelated way. So pixel by pixel, we have orientation information. So we can look at the lattice curvature, and from that we can get the geometrically necessary dislocation density. We can look at the dislocation density inside a twin in the matrix and then compare them. So if you go to the next slide, we made a very important observation, and all this is by conventional testing, not in situ, that we see that yes, twins which form, they can mostly the extension twins follow the Schmidt behavior, while the contraction twin follow the non-Schmidt behavior. But irrespective of the type of twin, the lateral thickening of the twins is dependent on the difference in the modulus, the elastic modulus of the twin and the matrix. So whenever a variant forms, which has a drastically difference, you can see here red and blue, you can compare. Whenever a twin forms, which has a different modulus, or the difference in the modulus of the matrix and the twin is high, you are going to get thicker twins. So all the thicker twins, you can see that the difference is higher. So if you move to the next slide, what we will see is, like, once we have this, we do not stop with that. You measure texture using microfocus X-ray or a synchrotron diffraction, and then we carry out VPSC simulation to match the stress strain response and get an idea about the difference activity of your twinning. So you can see in sample A, the extension twin is operative. It goes over here and then it drastically falls. While here you can see the twinning activity is not that high for sample B. So all this is obtained using, so if you move to the next slide, what we will see is the VPSC simulation, right? So I think that slide went missing. If you go back one slide.
This is the one?
Yeah, so no, go ahead. I think that slide we missed, but this is done using what is known as VPSC or EPSC simulation, the elastoplastic self-consistent simulations, wherein we consider each and every grain as a ellipsoid in a homogeneous equivalent medium, and you take out the ellipsoid and try to fit it in, use the Gauss-Hardening parameters and all for modeling your slip and twin. And what we can do is to predict the stress strain response, the slip and twin activity, which we match with the microstructure, and measure the bulk texture, and we try to match all these. So this is a combinatorial approach that we have been following. Now, if we go to the next slide, we will see how we can use in situ. So this is like one of the first experiments that we did. So, you know, in situ experiment, I don't know where the twinning is going to start. So first I need to take a very large scan with a coarser grain size. And then as I keep on loading, I see some action happening in one of the grains. And now once I see as I'm increasing my load, so here it is the load value and T indicates tension and C indicates compression, you can see that I can see multiple twins which are forming over here, right? And you can see here as you go on increasing, from here to here, the twins grow, different variants of twin form. Now from tension, if you do unloading, you see that the twins are there. There is not much of a change. Now, when you do compression, you can see that the twin actually kind of, the thickness actually reduces. And then when you again from compression, you unload and you go in tension, you see that the twin thickening occurs. So, you know that when you are going to do tensile loading, the thickening of the twin is going to occur because you need shear stresses along that. And just for fun, what we did was, we ramped up and we went to 500 degrees centigrade for half an hour, and we see that this deformed microstructure completely changes to a recrystallized microstructure. So what I'm trying to emphasize over here, that once we have an in situ stage wherein we can apply load as well as heating, we can actually use it as a thermomechanical simulation tool inside SEM. So that is what I want to emphasize. So if you move to the next slide, we have done some, really high resolution. So here you don't see blurred images. What you can see is as you deform. So I want to look at, the textural, can look at this blue grain over here. If you look on the right hand side, the starting sample, you see that as you go to tension on the right extreme, you see that the color changes. But again, when you go to compression, it kind of comes back. So you see that we also observe that indeed, in addition to, this mechanical kind of Borschinger effect, which I told you, you can also have the textural Borschinger effect. And this is for, only the orientation. But if you look at the twin also, you see that there is some reorientation of twinning. And this will be clear in the next slide, wherein we have really focused. So, so this is like the mechanical Borschinger effect that I'm showing. So you do a test, you fix up the strain, and you see that the deformation behavior of A and B. Remember, I showed you that the A orientation of titanium had higher ductility but lower yield strength, and B orientation had higher yield strength but lower ductility. So here you can see that the Borschinger effect is slightly different. There is no unique trend. And if you go to the next slide, we will see the microstructural evolution. So here you see that if you go to different orientations, we don't see these thick twins that we were seeing earlier. But because of this load reversal, what we see that multiple twin nuclei are forming. So at very high, magnification, you can see over here, these all small lines that you see parallel. So if you go to the right, you can see this arrow. Okay, the 1.67 sample, there is an arrow and which shows the gray color, gray scale image. And then if you go below that image, which is over here, you see a lot of parallel, lines. These lines are not scratches. These are all your twin nuclei. And out of these twin nuclei, one of them is going to grow, right? And then the twin will form. One or two twin will form. Not only that, this is for A orientation. For B orientation also, we see that, there is a lot of the black region is because of, your poor pattern quality. But when we blow up and go to the extreme right image, we see that these are actually contraction twins. So this is what in situ EBSD can offer. If I would have had a FIB, I would have just simply plucked out a lamella from here, put it in a TM and kind of do much better, microscopy to get a good idea about the geometry of twin and all. So the resolution is not good, but you can always combine it with higher like a TM technique. So if you move ahead, what we will see is actually, so where we do this tension and compression, we can see how the de-twinning happens. So these are like more higher resolution images where you could actually measure that, yes, indeed the twin propagation is kind of reverted. And here also you can see that, the twin assisted twin nucleation. So here the twin ends, if you go to the extreme right image, you see that the twin ends in grain number 7, the blue grain, and there is, at that orientation or at that location, there is another twin which is starting in grain named 8. So, so all these kind of aspects you can actually capture by doing in situ experiments, which, post-mortem you can see, but here you can actually capture. So which was not possible by doing conventional deformation, deformation followed with characterization experiment. So if you go to the next slide, we did not stop here. We see that, in monotonic loading, twinning is good because twin thickening occurs. You get motion of dislocations. But when you have load reversal, de-twinning tendency is important. And this need not necessarily be helpful. So if you go to the next slide where we are doing all this low cycle fatigue and all, we see, I want you to go and look at the table at the bottom. You see that the number of cycles to failure, for a given, strain amplitude, it is much higher for B. Remember, mind you, the B sample was showing lower ductility for your tensile loading. But here in terms of cyclic, number of cycles or the cyclic strain that is accumulated in B sample is in fact higher. And this ends up happening because, in sample A, if you go to the next slide, we will see that in sample A, we have these intersecting twins, right? Which do not undergo detuning. While in sample B, where we had this parallel bunch of twins, they undergo the tendency of detuning. There is no 100% detuning, but the tendency of detuning. So you can see here, top image over here, there are more twins. And here there are less twins. In A, you do not see twins because, here also there is some detuning, but the detuning tendency is not that higher. And this will be clearer in the next image or the next slide, wherein we show that what exactly happens. So what happens is that we also carried out X-ray diffraction experiment, wherein we show that, the back stress that is relieved. So this is determined from the kurtosis of the X-ray diffraction peak. We see that the kurtosis indeed reduces for sample B, which essentially indicate that the back stress is relieved because of detuning, and therefore the low cycle fatigue behavior is far superior than that of your orientation A. So to summarize this aspect of the deformation behavior of titanium, we move to the next slide wherein I have written that this twinning deformation process is very, very important for hexagonal closed pack titanium. And we see that multivariant twinning, which is very, very good for monotonic tension, is not necessarily does not necessarily have good detuning tendency. And this is what we could capture using not just the bulk level testing followed with characterization, but our in situ experiments. And this is the beauty. And what we would like to go further is if you could do a in situ cyclic loading experiment. So there are holders which are available, and we hope that in the future we can have that kind of a holder so that we can do a complete, if not a high cycle fatigue, but a low cycle fatigue experiment inside a SEM and actually capture these twinning, detuning processes. So now I will just give you a kind of another example wherein, we are not going to change the texture, but we are going to change our strength. So if you move to the next slide, this is a simple aluminum. So if you can go to the next slide, please. Yeah, so this is a simple aluminum magnesium silicon alloy AA6061. Simply by doing precipitation hardening treatment, you see I can play with the strength and the ductility, I can get the toughness. Now, what is important over here is the strain hardening behavior. And you see here that for the pre-caged and the under-age sample, you see a clear nose of the sample, right? Nose in the strain hardening curve on the right-hand side. While here for the over-aged and the solutionized sample, there is this gradual, decrease in strain hardening. Okay, so this is essentially telling us that, the strain hardening behavior, there is a transition. So to understand this better, what we did was we carried out in situ test. But before we do in situ test, we have to really see whether our texture is same or different. So let us go to the next slide, wherein we see that yes, indeed, the texture remains the same for our pKh sample as well as the solutionized sample, because the temperature at which we do solutionizing we do aging is much lower. So there is no change in texture, but yes, the precipitates do form and they actually contribute to the increase in strength. So now if you go to the next slide, we see what we do is that if we just prepare the sample using colloidal silica or electropolishing and do a tensile test, we see that there is surface roughness evolution for your pKh sample. While for solutionized sample at the same level of strain, you do not see the surface roughness evolution. So this in itself indicates, so this is an indication that you get restricted or single slip in your pKh sample, while for solutionized sample, surface roughness evolution is not there because multiple slip systems are getting operative. And this is further seen by just simply looking at the SEM image, the SE image, the secondary electron image at higher magnification, wherein you can see parallel slip lines. So if you go to the next slide, we carried out in situ EBSD, and what we see is something like a classical textbook example. So we know that this is borrowed from textbook, where you see that if you do tensile test for any orientation, the grain tends to rotate towards 112. Now, if multiple slip is operative, it is going to move towards 100. If planar slip is operative, it is going to move towards 111. So what we see for the solutionized sample is that, as we deform these grains, we do get, this motion of your orientation. They tend to go towards your 100. So all these grains you see, they tend to move towards, your 100. On the other hand, if you go to the next slide, we will see the pKh sample. So in the pKh sample, it moves classically towards your 112 orientation, which is in between your 111 and your 001, because there is planar slip. So we thought, okay, if at all there is planar slip, why not try to do this loading unloading experiment? So that is what we did in situ. So we did loading unloading experiment. So in the next slide, you will see that when we do loading unloading experiment, we see that, this is kind of nicely toggling between 112 and your 110 or 011, which is the compression texture component. So this is all at much lower strain. If you see, the strain values are maintained or mentioned over here. So this is happening because, it is, just think of it, that only one or few slip systems are getting operative. So your dislocations are moving on one plane. When you apply tension, when you apply compression, they kind of revert back. So they will encounter these obstacles, but the motion of dislocation is restricted only to the slip system, right? One slip system. So this is something very, very important. So we get restricted slip in your pKh sample in the presence of your precipitates, while in the absence of precipitates, we get multiple slip. That means there is a lot of cross slip. So if you go to the next slide, what we wanted to do was, kind of get some idea about this by doing full field or rather mean field viscoplastic simulations, wherein we take this information of all the grains and all, and we try to do, all these, initial texture and try to deform it. And we see that we are able to, kind of toggle between, moving towards the, 112. So in tension, we move towards 112. Which is the top middle image, and then you see the C stand for compression. In compression, we move towards the 110 or 101 component. So this is what we are able to capture. So what all hypothesis I put forward, even with conventional, our simulations, by including the slip activity and the slip rotations, we can capture the crystal rotation because of slip. We can capture this effect. So now if you go to the next slide, what we see is that we do not stop here. We have the bulk mechanical behavior. So we visited, the strain hardening behavior. If you have to explain, you can go to the Cox and making model, where you talk in terms of d rho by d epsilon, the evolution of your dislocation density. There is a storage term, which is k1 square root rho, and there is a recovery term, which is minus k2 rho. So that is how you model your evolution of dislocation density, and this is how you view your strength. You can see this equation for your strength. So what we wanted to do, in fact, was to capture this transition from, restricted slip to multiple slip. So this is what we have observed. So what has been done up till now is that, the Taylor model is fine, or the Cox making model is fine. But even better is the two internal variable model, which takes into account the forest dislocation density, the immobile dislocation density, or like in the cells, the dislocations which are at the cell walls, and the mobile cell. So that is the two internal variable model. And we mentioned that, from our observations, that in this, forest dislocation model, which you are seeing over here on the left column, on the left hand side bottom, see this d rho f by d epsilon p. So what we are writing down, instead of m, which is your Taylor factor, we say that we go from an orientation factor, which is like a single slip criteria, which is like the inverse of the Schmidt kind of deformation, the iso stress condition, to the iso strain condition. So we go from the Schmidt factor to the so-called, the Taylor factor, the Schmidt kind of deformation to the Taylor kind of deformation. So we write down an evolution equation for my m also, or m double prime, that I am using. And here you can see that this goes from the saturation value of this is the Taylor factor, which you use for polyslip, while this is like the inverse of your Schmidt factor, which is used for single slip. So what we can see is that by revisiting the two internal variable model, which is for strain hardening, which was proposed by Barlat, we have modified that model and incorporated this transition from single or restricted slip to multiple slip, so that we can predict the strain hardening behavior of our solutionized as well as the pKh sample. Now, I'm not showing here due to the paucity of time, but with any existing model till date, we cannot predict the strain hardening behavior. But now with our approach of, using this transition from single or restricted slip to multiple slip, we are able to capture this. Not only that, this is not just for aluminum, magnesium, silicon alloy in different temper condition. If you go to the next slide, I want to tell you that if you make a good model, if you develop a good model, It works for all FCC materials. So you see here, there is a nickel silicon alloy. So if you see the grain size is varying, we know that twinning is favored in coarser grains. So you get this higher, strain hardening, the bump in the curve on the top left.
Professor Nilesh.
Yeah, I'm done. I will take 2 minutes to finish off, right? Thank you. So you see that we can capture the effect of grain size. At the bottom, you can see we can capture the effect of composition, wherein, as the silicon concentration is increasing, your SFE is decreasing. So we can capture that. So the model that we have developed by doing this in-situ test, coupled with, bulk tests, bulk tensile testing, we can build up a model that can predict the strain hardening behavior of FCC materials and capture the effect of grain size, stacking fault energy, as well as temperature. So if you go to the next slide, I will mention that this is what an in-situ experiment can do, not just to stop and get some beautiful images. Yes, a picture is worth 1,000 words, but it is more important that how do we analytically use this information to generate more knowledge and create and be more wise. So I will just conclude by showing the way forward. So this is the slide what we have. So now that we have included all these different models, what I am trying to say is that we have developed a constitutive model. The next step is to employ these models in constitutive modeling or doing a full field simulation. So if you go to the next slide, on the next slide, what we will see is that we have developed a microstructure sensitive constitutive model. And this constitutive model we can include in the kind of simulation that we did. So that the VPSC simulation that I showed you or the EPSC simulation was kind of a full field. Nowadays, there is a lot of emphasis on mean field, or rather that was a mean field simulation. This is a full field simulation where you can actually capture, the microstructure. So this is the work of, Srinivasan and Rupam, who are working with us, and they have recently done this, in-situ tensile test, and they are able to capture and see where kinking will happen. And in this kind of model, we are presently using some phenomenological law, but what we want to do is to use a constitutive, a microstructure sensitive constitutive model. But having said that, we are at the end of the day looking at, few hundreds of micron. So we have to look at actual bulk samples. And for that, if you go to the next slide, we have to go and use finite element method. So herein I show that not only the deformation behavior, but we can also get information about, the void size and all by, kind of comparing it with or kind of combining it with the damage evolution. So this is the classical GTN model, the Gerson, Trevergaard, Needleman model. You can get information about fracture and all. And if you can play the slide, you can see the voids and all. Because, on such a large scale, if you try to do CPFEM, the crystal plasticity FEM or the CPFFT simulations that I showed you earlier, they are very computer intensive. So what you do is you use a simple abacus at the macro scale. And then at the local scale, you use a CPFEM or CPFFT model, what you can see on the right hand side. And what you see on the right top is a DIC, the digital image correlation setup. So this is measured experimentally, and this can be combined with in-situ synchrotron, X-ray or EBSD measurements to get an overall idea about deformation processes. So we'll go to the next slide, wherein I just have the conclusion. So I have said, I will say that in-situ experiments, yes, you should know what question to ask. We'll get a good image, fine. But more than that, what we want is what is the knowledge that we are generating from it. And the future wherein lies is that where we have to combine these in-situ experiments with development of constitutive models and numerical simulations to establish the microstructure property linkages in material. And I will thank, let's go to the next slide. And this is the acknowledgement. And thanks to the organizers, the chairperson, as well as all the participants and my collaborators and the facilities at IIT Kanpur for making this work possible. So thank you very much.
Yeah, thank you, Professor Nilesh. It's a very clear, detailed and nice presentation on the use of in-situ SEM and also combined with other complementary tools to study the deformation. So there is one question in the chat box, question answers, that is, I don't know who is asking, but it's written anonymous. So the deformation twinning has both shearing and shuffling of atoms. Has any in-situ TM work has been done to capture this? This is the question.
As of now, I'm not aware, because this will this has to be I think this has to be at the HRTM level, right? Like where we are seeing the atomic
sure.
level. Because what image I showed you, that paper of Berlin and all, that was MD simulations. But this can be very interesting because the kind of TM work that we have seen for yesterday and today morning also, I think that is something that can be looked at. This process of twin nucleation, if we can capture that, how the twin, where does it nucleate, and with like geometric phase analysis and all that level, if we can capture, I don't know how much will be the surface effect there, but if we can do that, nothing better than it.
I agree with you. So any one question, actually we are supposed to close the session now, but we are running short. I'm sorry for this, but
Kim, can I ask a question?
yes, please.
Quick one. Nilesh, nice talk. I have an engineering challenge for you, Nilesh.
Okay, sir.
And this is that you know that engineering titanium alloys contain 6 aluminum and some oxygen to strengthen the alpha phase, the ACP phase. But what those two elements do is they also promote planar slip and completely eliminate twinning. Well, not completely, but to a large extent.
True.
So the challenge for you is how do we promote twinning in 6 aluminum 1500 ppm oxygen containing alloys? What sort of alloying will do that? And the engineering benefits from that could be quite substantial because of the damaging effects of planar slip and so on. So if you have a nice proposal for that, the incentive is maybe we can solve your EBSD access problems. And I'll leave that for your thinking, okay?
Right, sir. No, this is a very good suggestion. So I think I will think over it, and maybe I will drop you a mail, sir, on this, because this is really very interesting. This is really very interesting, because if you could induce that, this will not only it solves the planar problem, it also gives us an opportunity to kind of have additional strengthening mechanism or like additional strain hardening mechanism in Ti-6 core. So yes.
Right. Okay. Right. Thanks.
Thank you.
Thank you. Enjoyed listening to you.
Yeah, I think I request all other people to send questions to Professor Nilesh, and we'll move on to the last talk of the session. This is given by Dr. Praveen Kumar, who completed his BTech from IIT Kanpur, and then MS from University of Southern California, PhD from again same place at University of Southern California, and then but right now he's at IISc Bangalore, of course, as associate professor. He joined there in 2011, had been working since then. So he is working basically mechanical behavior of the materials, electromigration, quite a lot of interesting stuff. And I take this opportunity to invite Professor Praveen Kumar, and the stage is for you. Thank you.
Thank you very much. Yeah,
you can share the screen now.
I can share. Okay.
Yeah, please.
So you can see my slides.
Yes.
Great. So thank you very much, Professor, for kind introduction, and I also thank the organizers for inviting me for giving this talk and sharing some of our work. And it's really nice because this is the first time for me to give a talk at this platform. As a matter of fact, this is the first time I'm giving talk to electron microscopists, and perhaps what I will try to do in this during next 30 minutes or so is to give a perspective of how great work that electron microscopists have done, which has made life for us, like a person who is interested in mechanical behavior, so much easy, and how it has allowed us to learn more from these experiments when they are done inside SEM. In this particular case, inside SEM, to learn so much about the deformation mechanism and what goes on in there. So what I will do in my talk is that I will go and I will look into some of the examples, some of the problems that we have been working on for the past several years, and highlight some of these accomplishments, some of these stories that has come out. This work, the most of the work that I will talk today was primarily done by Ali. He is currently a postdoc in University of Colorado. And then some of the work in the beginning, especially on the solder joints, were done by Anvesha. The work on crystal plasticity simulations and titanium alloys were done by Yazer, Tejnath, and Manak. And of course, the collaborators that I have had in the past, Professor Satyam Suhas, Professor Dipankar Banerjee, who is also here today, and Professor Vikram Jairam has, led to some very exciting discussions, very exciting discovery of the problems itself. And of course, it has been a pleasure to work with them and learn from them. And I acknowledge all their help. The work has been funded by MHRD and Ministry of Power through imprint program, and DRDO through its, DRDO or ARDB through GTMAP program. So with that, let's start with a very simple example. And the simple example where SEM, and especially because, there is a large, depth of focus, can allow us to do is to just look at what happens in the deformation of these constrained metal joints. And to demonstrate this thing really nicely, we took the system where we were working on tin joints. And tin joints, why tin? Because tin is the closest that we can think of when it comes to solder alloys. Lead-free solder alloys have 95% of tin in them. And then they're constrained by copper. Now, if you look at the compliance of tin and copper, or the plastic behavior of tin and copper, they are really, really different. And hence, if we can look into this material system, tin and copper, and we look at what happens when under this constrained system, then perhaps other systems will be a little easier to look at. So we start with a very simple design, like say we start with a thick joint. And when I say thick joint, I'm talking about a millimeter, about 900 micrometer thick joint. This is the tin and these are your copper. And then as we load it, we can start to see this slip patterns forming up. And they are always starting from the nearby, from the edges, because these are the places of higher stress concentration. And then these things keep on evolving. And then finally, we have classic fracture. On the other hand, if I reduce the joint thickness to about 285 or 280 micrometer, then, if you look at this, then we do have slip, but not as prominent as what we see in the thicker joints. These things continue there, and the fracture essentially initiates, rather than here the crack is coming at the locations or the stress concentration coming at from the edges. Here, essentially, you have classical crack nucleation at the center, and then eventually it fractures. So by looking at this thing itself, we can clearly see that if we had just looked at this sample post facto after the fracture itself, this kind of clarity of where the crack nucleates, how the slip continues, and how does the joint thickness affects this would have not been possible. So this is really a nice way of doing, learning about these things if we can do these experiments inside the SEM. And of course, we have a way to understand what thing that we are seeing here corresponds to what stress and strain values. This also allows us to essentially, plot this, how much is the contraction that is taking place as a function of how much is the axial strain. And you can see from this plot, if it was all good, then it would have been, we have just been seeing the, the Poissonian contraction. But as a matter of fact, from the difference between this thick and thin joint itself, you can see that there is a significant constraint on the thinner joints when it comes to the lateral contraction. And that gives rise to higher triaxiality in the thinner joints, and hence the fracture that you see there is more close to the brittle fracture. What interesting thing that also we can see from here is that there's a nice equivalence between FEM analysis, which is a completely continuum analysis, with these experimental data. And at least at this length scale, when the joint thickness is still about 200 or 300 micrometer, perhaps FEM is a good tool to work with. We don't have to get into crystal plasticity or other tools. However, when we did the same experiments at a much thinner joints of the thickness of about 100 micrometer, we started to see some deviation from the FEM, and hence in those length scales, crystal plasticity or something similar models will be important. Nevertheless, that is something that we can discuss later. Here, I just wanted to show you these two slides to show that how useful SEM can be to understand some of these things, which is so clearly. And this is all, thanks to these in-situ experiments. Now, what we learned from here is that even though the sample, even though the surface of the sample goes a little bit out of the plane, we are still be able to capture it. We're still able to keep those points in the focus, and that can essentially be used in DIC. Now, Nilesh just mentioned that the DIC is useful, and as a matter of fact, he has set stage for the rest of my talk really nice, where we are going to play with EBSD, crystal plasticity, in-situ experiments to figure out certain things. So thanks to Nilesh, some part of my work is really, really easy now. So we start to look at this DIC and how can we do DIC in SEM. That's essentially will be the focus of rest of my talk, and what can we learn from there. Now, DIC, just a brief introduction, is just essentially tracking the points. So you make some points, what we call it as a contrast points, and we see how this contrast point move or shift as a function of deformation. And then we can relate this, this deformation, field to the strain, and then we have the strain field. Now, this is really nice because by doing the DIC, we can have, the 2D strain field. And traditionally, people have been using optical microscope to do DIC. And by the way, optical microscope and DIC using the optical microscope is just fabulous. It has a lot of simplicity in it. However, there are some limitation, and the limitation is because of the, what kind of resolution one can get from the optical microscope. It is limited by the light. And hence, we cannot really look into what is happening inside the grain and what is happening to the dislocations of the structures and so on and so forth using this so easily. I will not say that we cannot do that at all, but it's not that easy. Whereas SEM, given its resolution and ability to do higher magnification, can in principle resolve these issues. But again, at the same time, SEM brings its own challenges. And the major challenge that we have faced so far is simply because of the electronic drift, which has to be minimized and compensated. Now, what is electronic drift? As you can see from this image. Now, this is a video that has been taken, or has been taken at a very, very bad condition. For example, this is at a very high magnification, very high working distance. I'm right, but this actually shows you what I mean by this electronic drift and what kind of problems this can bring. So this is a sample. This is a stationary. It's not moving at all. I'm right. And when you are looking at, when you are imaging it, you can see these points are just simply moving. Now, nobody can do DIC with such kind of images at all, because we need to know where the points were, and all the movement that is happening in the points we have to attribute to the deformation. So this is a bad example, and this is because of the electronic drift that is associated with the SEM. And because of this problem itself, many people working in DIC will say that don't even think about SEM when it comes to DIC. But the problem is that it's not that bad. We can make some use of it. And here are some guidelines that we have been following to still do some meaningful DIC with SEM. And the basic idea is that you use all of these things only as much as you need. Other than that, just try to minimize it. So for example, use a magnification that is just enough for whatever features that you are interested in. There's no point of going to 200,000 magnification when you can get your information even with 5,000 or 10,000 magnification. Try to minimize the dwell time. As you can see here in this image, this is images with different dwell time. And you can see that the drift is generally less when you are using less dwell time, and the drift is a little bit more when the dwell time is higher. But again, at the same time, this is an optimization process. You need to have some dwell time so that you can make, have enough good contrast and you can distinguish between the different features. Similarly, try to have the minimum field of view, minimize the acceleration voltage, as you can see from this image. As you go, this is the same sample. As you go with the lower, voltage, you can see, dramatic effect on the quality of image that you can obtain. So there are, again, try to minimize the working distance, maximize the number of pixels that is there in the image. And if none of these things work, you're still having a lot of this electronic drift, then try to see some stationary points and then try to calibrate or try to shift all the images by using some algorithm so that you can identify the points. You can remove the translation altogether. This is all purely translation anyway, and this is an artificial translation, so that should be fine. But then again, adding these stationary points in your test setup is going to make the test setup itself cumbersome. So if this works, nothing better than that. Otherwise, we have to go here. But nevertheless, we can make it successful. So here is one example, the first example that I'm going to talk about. This is about when we were interested in looking at, what happens when we reduce the size of the sample on the creep. So we did essentially uniaxial tensile test as well as compression test. The samples thicknesses, or in the case of tensile samples, varied from 500 micrometers to 5 millimeter. Similar diameters we use for the compression test. This is your DIC speckle patterns, and this is at a higher magnification. So essentially, you can see that the distance between these the contrast points, which is essentially what your DIC is tracking, is of the order of a micrometer. So let's say 2 micrometer to 3 micrometer, 3 micrometer to 5 micrometer, and so. Now this distance is much, much smaller than the expected subgrain size that we expect here. So that means we will be able to obtain the strain field inside the subgrains also. And that is going to be very helpful, as I will explain to you in a few minutes, when we try to understand this creep behavior itself. Again, this is not possible with optical microscope, this kind of resolution. And this was possible when we were doing the SEM. And again, these samples are still not so small. So they are, again, beyond the realm of what we can do really test inside a TE. So this is a simple, DIC strain pattern. And this is your creep curve. And we can see how does the, what happens to the strain concentration. As long as we are in the primary and secondary, the creep is, the strain is fairly, homogeneous. There's not much, there's no systematic, effect of anything that we can see there. But when we look at the steady state strain rate as a function of stress, we see that, of course, as the samples becomes smaller, am I right, the strain rate becomes higher and higher. And these are data, these are self-consistent data, and this is, we compare with what have been published in literature, they all kind of match with each other. So we see that this is a real trend. This is validated against for the bulk samples. We have validated with other data. So the question is that why is this happening? And this one, we can then look into, how the dislocation density varies as we go from the surface to inside. And what we see from this picture, this is an H-pit picture. As we are closer to the surface, there are less pits. That means dislocation density is lower. As we go inside, dislocation density increases. When we look at the EBSD, we try to see how the subgrain sizes vary away from the subsurface. Again, we see the same thing. Closer to the surface, we have larger subgrains. As we go interior, we have lower subgrain size. And same thing across the thickness also. But then look at this. There's not much difference in the terms of strain concentration. So what we can say is that still this material is deforming as per the isostrain condition. The strain, what we have, is not really affected by the subgrain size. And what it essentially means is that something else is compensating this or giving this stress, a strain, equivalency in the strain isostrain condition, that which we later on harness when we are developing this model. Is essentially the stress has to then redistribute. We can then go ahead and we can look at how this subgrain sizes change with the stress. And there is the variation that you see on the surface, near surface, and the variation that you see in the interior are slightly different, which is fine, which is something that we can quantify and we can use later on for our modeling. Again, we can do a little bit more. We can see how big is this surface affected region. Essentially, what is happening is that surfaces being near to the open, because it's open, it likes to attract dislocations. So dislocations disappear from there. And hence you have lower dislocation density near the surface region. And because you don't have dislocations, you don't really form very large, very small subgrains. We can quantify this distribution, and then again, we can bring in how does it affect, how does it vary with the stress, and then we have this quantification also. Now we can put all of these things together in this nice model, which Ali developed in his PhD, and this is available in this paper. So we understand that the deformation is isostrain. So that means we can think about there is a difference between the substructure that forms at the surface and in the interior. And we can then develop this composite model. We can understand how is the stress affecting your fraction of this surface affected region, because we know the relationship between the subgrain, the width of the surface affected region with the stress. And then we can use this isostrain condition. That means because both the surface as well as the interior are deforming at the same strain rate. That means they are looking at, they are experiencing different stresses. And this is the stress that I'm applying. That means the stress at the same strain rate. That will mean that this is the stress that is taken by the interior, and then you can calculate what will be the stress that is going to be taken care by the subsurface. And then you just put it in the model. You try to, then start to predict how the sample size is going to affect your strain rate and so on and so forth. This is a model prediction that you can see here. These are the data points that we have got from the experiments. And then again, you can predict even for other sizes and so on and so forth. So we can see that as we reduce the size, the strain rates increases, and also there is a change in the stress exponent that goes from 4.5 to almost 3.85. Now, all of this, of course, is possible because we could establish the strain distribution and how that is isostrain distribution. And of course, we understand, the microstructure, substructure developed there. Again, this is all partly thanks to the in-situ experiments that we could do. Now, very quickly, I think that Nilesh told that I will talk more about bending, but I'm going to talk only about one slide here. So essentially, bending creep also we can do in situ, where we are essentially applying, we have a cantilever, we are applying a load, and then you have a stress-strain distribution. So from one sample itself, if you can track all this strain evolution and we can try to figure out what stress that is responsible for those strain evolution, we should be able to get multiple pairs of strain rates, steady-state strain rates and stress values, which can be used to get the value of stress exponent and other creep parameters. So this is the sample. Now again, this is the larger sample that can be easily cut using the relatively larger sample. This can be cut using EDM. And then if we are interested in the smaller samples, which is something that we also tested, something let's say of this dimensions, then essentially, of course, we can go, we can take these samples, cut as small as possible using the EDM, and then the rest of the cutting we can do in the fib. Then we, in this ones, one can put the DIC speckle patterns using the, the platinum source that is there in the FIB itself. This is just one example. Then we can put it in the, in the in-situ experimental setup, DIC, and then the DIC data can be collected. And you can see here, from one sample, by tracking at these different points, one can have, like tons of creep versus time graph, as you can see here. And which is what can be used to essentially understand the steady state strain rate behavior as a function of stress. Interestingly, what we see here is that in the case of the bending creep, we see that as we reduce the dimension of the cantilevers, they become essentially stronger, which is contrary to what we see in the uniaxial condition. And what we think why is happening because of the presence of the strain gradients, because the strain is not uniform across the thickness. There's a strain gradient, not just across the thickness, but also along the length. And these strain gradients are responsible for producing large amount of GNDs, which gives you additional strengthening. And you can see from this nice CAM map also, this is a smaller a smaller cantilever, 500 micron, this is 5 millimeter, same stress levels. And you can see that there's a large amount of GNDs, large amount of strain concentration, strain gradient in case of the smaller joints. But interesting thing is that later on, we can quantify all of these things. We can correlate again these things with the strain fields, and we can develop a model. Now, if anyone is interested, we can talk more about it. But this is where I will end on this issue of understanding about the creep in presence of only the surface or in the presence of strain gradient also, and how the conducting in-situ experiments in conjunction with, of course, the traditional microscopy has helped us to understand this creep, which has been again a very nice journey for us, all thanks to doing in-situ experiments. Now I come to the last part. This is the work that Ali and others did in guidance under supervision of Professor Dipankar Banerjee. So let me go over some of these things. This is quite interesting. Now this is a titanium alloy. It's a high-strength titanium alloy, which is often used in landing gear of the aircraft. This is 5553. And what you see here is that they have very, very large grains. These grains are of the sizes of the order of a millimeter or so. And this has, when we look at one of these grains, which is actually a beta grain, when you look into one of these grains, beta grains, then essentially you see a lot of these alpha phase all over the place. Now, the width of this alpha phase can be a few nanometers all the way up to a few microns. And the length is about tens of micrometers. And this is just dispersed all over in one of the beta grains, and which the beta grains itself are fairly large. So in principle, one can make samples which contain a lot of these beta grains, and inside the beta grains you will have this alpha. Or you can make small samples out of one of these grains. Then essentially, in principle, you are testing single crystals with all of these dispersed distribution there. And this allows us to actually look at the strain distribution or the strain, what is happening to the strain evolution at multiple length scale. For example, if the multi-grain samples are tested, then you can see how the strain is being transmitted, or how the strain is distributed across the grains, across the beta grains. When you are looking at the single grain of beta, then you can see how the strain is distributed across, or the slip is transferred from beta to alpha and so on. So this is a very interesting problem from that point of view. And this essentially, again, comes under the realm of using the DIC, but at different levels, a different magnification DIC, and how that can help us to understand the deformation behavior. So to understand that, the samples were made. These samples, we like to call it as a bow tie samples because they look like bow tie. These are slightly different than the classical, classical dog bone samples, because we have multiple radius of curvature here. What does that allow us to do is that the strain or the stress field that you have in the gauge sections, it becomes uniform, but also there is not much stress concentration at this transition zone, which is often seen if you just use only one radius of curvature. That's the case of the dog bone samples. So this helps a little bit. So sample thickness is about 500 microns, same is the width, and the sample length, the gauge length here is about 1.5 mm. A special fixture was, Ali designed this a special fixture for testing the samples. So these are the things that will be put on the grip of this micromechanical tester. And inside that you have a groove, and inside the groove is where the sample is placed. This essentially helps to handle very small samples without getting affected by what can be done on the standard grips that has been given to us. All the tests were done at room temperature, but this sample design also allows you to better heating the sample itself, because in principle we can heat these fixtures, and that can then establish a uniform temperature field over the sample. So this is how it looks like inside the SEM. Now the key here is to how to do this DIC, and the DIC was done, as I was just telling, that we can look at different grains at the same time, and these grains are fairly large, or we can look at what is happening inside the grains, which are actually, then we have to look at something that can resolve the distribution of the alpha particle itself, which are very, very small. So Ali came up with this very interesting solution to look into that, and what he did was he used these gold nanoparticles. So these gold nanoparticles individually, they themselves are very small, less than 10 nanometers, so the order of actually 5 nanometers. Okay, and then he dispersed these nanoparticles over a sample. Now, of course, he has used quite a elaborate process, which involves a lot of chemistry and solutionization, hydroxylation of the surface. But with that, he could disperse these nanoparticles, and these nanoparticles could attach really well to the metal surface. And when he disperses it, essentially you see this kind of images. Now, if you look at this image itself tells you that there is a bright region and there's a dark region. These are actually, by the way, very large scale. Essentially, the distance between these contrast points is of the order of about 100 micrometers. Okay, but if you zoom one of these bright regions, then essentially we can see these small nanoparticles also. So basically, in these small particles, there exists some contrast point, and here the distance between this contrast point is of the order of 10 to 20 nanometers. So if you choose to do this DIC or measure the pictures at lower magnification, we will use this contrast point essentially, which is a colony of these nanoparticles. And if you want to increase the magnification, then essentially we can discern the individual particles in one colony, and that can then give us what we call it as a micro DIC. So at this length scale, we will get micro DIC, where we are actually resolving things, a spatial resolution of about 100 micrometer. At this scale, we can distinguish, or we have the contrast point of the spatial resolution of the order of few nanometers, which is good to differentiate between what is happening inside the alpha phase and the beta grain. And this is good for understanding what is happening in between the two or multiple beta grains. So this is one example done at a very low magnification. This is how the sample looks like.
Professor Praveen Kumar.
Yeah, I'm just finishing. I'm just finishing.
Okay,
Just 2 more minutes. So this is a large grain, and we can perform these experiments, and nicely at lowest or smallest strain, you can essentially feel these boundaries here in terms of the strain boundaries also. So this essentially shows you that there is a localization of strain as we go from one beta grain to another beta grain. At a large length scale also, there is a strain heterogeneity in these samples, which is something that has not been so clearly talked about in the past. And of course, we can see here that DIC allows you a little better estimation of the modulus. Polycrystalline 120 GPa is something that we expect. In this one, if you look at what is happening in a single crystal, this is how it looks like. We can look at, inside this DIC, this is a test that is being run. And from this test, we can then calculate the strain field. Again, the same thing. We can distinguish between, this is, by the way, this is at still the sample is large, the view of it is small. We can distinguish the accumulation of the strain and how does this strain heterogeneity evolves. Inside a grain also, this is a single crystal in that sense with a lot of these alpha phase. This is the last thing in this. So for example, which is something that Nilesh was also talking about. So let's say that we start with this EBSD map of this sample. So we have, essentially we have all the 12 variants of alpha here inside one beta grains, right? And then we can feed this into your crystal plasticity model. We can get these strain fields, as you can see here. And very nicely, you can see that there are some of these alphas, which are essentially not getting any strain at all. And whereas, again, same alpha, but depending on their in-plane distribution, in-plane orientation, essentially they get a large amount of strain. And this is the beautiful thing about this, these variants and how they are distributed inside the grain, inside the beta grain. And the same thing we also see from your micro DIC, how this strain field is. Here, essentially, these black lines that you see here, these are simply the boundaries of your alpha phase. And when we compare the simulated results that is coming from the crystal plasticity and the experimental that is coming from the DIC, there's a very close match. And this is very nice because now you have a validated crystal plasticity model. And once you have the validated crystal plasticity model, we can learn more about the mechanics of this plasticity overall. With that, I would like to conclude, and I would like to tell you why I love doing experiments inside an SEM. Being a mechanical behavior person, I love SEM in that sense, because it allows us to, its large depth of focus allows us to understand the deformation mechanism and failure of joints, like its compliance and non-compliant mechanism. We can understand the sample size effects when we are doing this DIC at lower magnification, relatively lower magnification, but this is still higher than what we can get from the optical microscope. Of course, at the higher magnification, we can learn a lot about phase, like what is the role of phase distribution, chemical compositions, even the dislocations of the structure, how does that affect the microstrain and strain distribution. And with that, to concur with Niles's view, if we combine this EBSD and micro DIC, it can help us to actually calibrate crystal plasticity, because as a matter of fact, in crystal plasticity, there are a lot of terms which are not very well known. Is what should be the value that we should put there, and hence this kind of information can help us to calibrate crystal plasticity, and this can go through back and forth. So it has to have through some adaptive learning thing there, and that will then help us to understand the deformation mechanism much better. So thank you.
Thank you, Praveen, Professor Praveen Kumar. Wonderful presentation. The session is open for discussion. So any questions, please?
There is one question in the QA box.
Yeah, that's already been asked. It's not meant for, it was meant to Nilesh.
So Professor Satyam, can I ask a question?
Yes, please. Yes, sir.
Praveen, very nice talk. Yeah, you know, what you have shown is very interesting. So I will ask you a philosophical question. You mentioned that, you know, we can use FEM at multiple length scale, right?
No, at a larger length scale. At a smaller length scale, we have to get into crystal plasticity, at least in mechanics point of view.
But
So
at the end of it, you actually showed that there is a very good match between. Means I was really impressed with this titanium. You know, the last example that you showed.
That was with crystal plasticity.
But there was a corresponding FEM also, right? Simulation.
No, not really, not here. The FEM simulation that I showed you was actually for the tin joints. The
tin joints, okay.
And there, essentially, what we saw is, you know, in the tin joints, what we see is, as you can see here, you know, up to 200 or 300 micrometer thick joints, FEM is pretty good. It can give you a good correlation. But once you go to, let's say, solder joints of the thickness of order of 100 micrometers or smaller, then FEM starts to deviate, because then what happens that you start to pick up this, you know, like I will say that, let's say, non-continuum effects of the grain orientation, grain sizes, how many grains do you have?
Right.
And there we have to use crystal plasticity. So we have got initial success there. We have been able to, Anvesha has been able to do some crystal plasticity simulations there. And there essentially we can start to see the effect of, so crystal plasticity can capture both the joint constraint effect plus also the microstructural variations. Right?
Okay.
That's what happens when you go to a smaller length scale, because you have now working with fewer number of grains. And if the system itself is very highly anisotropic, mechanically anisotropic, for example, tin, then I think that crystal plasticity is a way to go. So yeah, crystal plasticity is a way to go. But at a larger sample size, most probably FEM is fine.
So, you know, even in FEM, like I can use anisotropic elasticity as well as anisotropic plasticity. So that is how people have been doing at the bulk length scale.
So what we have seen is that when we go to this, you know, we have been using this Dislo twin model from this Damascus. And that allows us to actually play with the dislocation generation or annihilation rates very nicely.
Okay.
Not just about where we are getting the slip, but also these aspects.
Right.
And that essentially, you know, I wish there was a easier way to, you know, homogenize all those things at a larger length scale, like so that we can bring that to the continuum level, which is FEM. So in FEM, you're right, we can define different grains into different orientation, but then you still have to, you know, kind of like put these dislocation evolution rates into some sort of a, you know, a simplified equation at the end.
Yeah.
Okay, and you will lose out the where are you getting the individual slips? You know, as they will just show you that this is a grain that is having the deformation, but you don't, like, for example, if you see these lines, right, these points, right? So it has a very specific you know, place where the slip originates, right? So these things I am not so sure if we can capture that nicely in the FEM. So FEM look, I love FEM. So I'm not saying that FEM is bad.
Praveen, Professor Praveen, there are one more question from Kalpana, Dr. Kalpana Naik. So Dr. Kalpana Naik, you may ask question now.
Sir, one small basic doubt, sir. Sir, in optical microscope, this is DIC is differential interference contrast imaging. And whatever you are seeing this in SEM, this is you are telling digital image correlation. So how I can think that whatever DIC we are seeing in optical, the same thing is happening in SEM also?
Yeah. So you see the DIC algorithm itself or the software itself doesn't really change whether it's a optical microscope or it's a SEM. It just looks at these contrast points. Now the point is that how do you, you know, Optical microscope can also gives you this contrast point. So is the ACM, right? And then once you have these images which have these contrast points, which have this, the points of ups and downs, then the software remains the same, right? The software, like we are using the VIC2D IC software, and Ali has also used NCore, right? So which is a free software. Now, once you have this, then you put it in the same software. Now, but having said that, there is a version of VIC2D IC, okay, which is especially meant for SEM.
Okay, okay.
And what it does, it allows you to, like I talked to you about this this issue of translation, right? This drift, right?
Yes, sir. Yes, sir.
Yeah. So that particular software of the VIC2D DIC, and I'm so sure that there are many more like that. Okay, allows you to compensate for this translation. Okay. So it has an added feature, but we have not used that added feature because we could optimize it without, to optimize this drift to a lower value. Okay, so it's the same principle. Yeah.
Okay, sir. Thank you. Thank you.
Sure.
Yeah, I think, are there any more questions? Okay, if not, let's thank Professor Praveen Kumar and all other speakers in this session. I think we got, this session got a little stretched. So my apologies to all the participants and the host. So thank you all. And I think it's a very interactive session as well. Thank you. Now, Professor Krishanu Vishwas, it's your turn. Thank you.
So thank you, Professor Satyam, for managing this big session. This is the biggest session actually we had in the whole symposium, 5 talks in 1 session. And I think the time is okay because we have a long lunch break. What makes us happy is that there are interactions among the participants, and this will bring new collaborations. And I could see that happening now, even in this session also. So just let me tell you some new things. So in the 2:30 to 4:30, 4:45 other sessions, we have 5 important industry talks and demos. And maybe one of them will show live demos. That's what I now understand. But some of them are from US, and they have huge time gaps. So they have to wake up early morning, 3 a.m., 4 a.m. to do that. So let's hope they will be able to manage it. So for all the student participants, I think this is something which all of you must not miss. The kind of expertise and the machinery which has been developed over the last 10 years is massive. So please take this opportunity to do that. And in the evening, we have other sessions on, mostly on in-situ TM. So that will conclude actually 14 talks today. 5 we have finished, another 9 talks are remaining. So with this, I request Dr. Chandrasekhar, are you there? Yeah. So you want to add something to that for the industry?
I think, yeah, as you rightly said that, as most of the speaker has been saying since yesterday, that the moment we talk about this in situ microscopy, instrumentation is something which is very different than what we have been using as a microscopist. So it's very crucial that we listen to this company talks, and also they are going to show that how complex it is, what are the things we need to do, or what are the precaution we have to take. So it's very crucial that we attend them, and then followed by as some of the most interesting talk is going to be in the evening. So I hope to see you all throughout the day. We were close to 3 digits. Hopefully in the rest of the session we'll maintain the audience. Thank you. See you all. Krishanu, over to you.
Okay, thank you. We'll have a lunch break, and we'll come back at 2:30.
Thank you.
Thank you, Professor.
Yeah, please, thank you.
Hello.
Hello, Amit. Hello.
Ah.
You have not logged in to the app. You cannot join the panel then. You are using web to join, right?
I am joining through app only. No app. Zoom webinar app. So I should give my meeting ID and password to the Zoom app.
No, I am unable to make you the panelist. That's why.
I got it. Join as a panelist.
Okay, done. Okay. Yeah, you should be in the panel, right?
Yeah, I think this should be okay now, right?
Yes. So first two speakers are already here. David and Jennifer. Hello.
Yes, hello.
Hello, how are you? This is David.
Yeah. So can you hear me, David?
I can hear you just fine, yes.
Yeah, you can try showing your slides. So you can share your screen and try to do that.
Okay, Jen, you've got the slides, so yeah.
Mm-hmm.
So just what we're gonna do, since Jennifer and I are back to back, we've just kind of combined this and we'll just hand off from one to the other if that's okay with you.
Yeah, it's fine, but I'm just requesting you to test whether you can share your screen and slides.
Yeah, she's pulling that up right now.
Okay, good.
Yeah, give me just one moment.
Go ahead.
I'm going to have to quit and log back in. I'll be right back, and then I should be able to share it just fine.
Yeah, please.
Okay, thank you. I'll be right back.
She probably has to set the permissions on her app.
Okay. Yeah. So you are in US now, or you are in Japan?
No, I'm in the US. Jennifer and I are both in the US. It's about 4:40 in the morning, 4:45 in the morning right now.
I know. Sorry about it, but
No.
your surname looks like Nakasi. Is it a Japanese surname or?
Yeah, a lot of people think it's Japanese. It's actually Arabic. It's an Arabic name. But whenever I travel to Japan, many of them think that I'm Japanese. But yeah, but the C kind of gives it away. Since the C is in there, it's not really Japanese. Can you Jennifer's back in? Can you promote her so she can show slides?
I'm doing that. Yes. I have to make her co-host.
Okay, hello. I'm back. Let me try here.
Yeah, but I have to make you co-host. Let me do that. So
can you see them?
Yes.
Perfect.
So both the chats are here. I think we can start in time. We have still 10 minutes to go.
Okay, that sounds good. And is everybody showing video, or are they just showing the slides? Are people showing personal video or just the slides?
Yeah, both. Some are
okay.
Videos, but videos will take more time. That's what I see. It's up to you. You have 1 hour time for both of you. You can.
Oh, I mean video of themselves. Do they have their cameras on?
Okay, you mean to say demo? Okay, yeah.
Oh no, I'm sorry. Video cameras. Are people running the cameras or just the slides?
Oh, I think today there will be one or two like that. Later part. I
No,
think
people are. I'll just. Yeah, people are sharing their screen like in the video mode, so that people can see. If you are okay with
Okay.
that, otherwise it's fine.
No, I'm okay with that. I just want to make sure for bandwidth, people, you're okay with that. Okay.
Yeah, it's working fine. Absolutely no problem.
Thank you.
so. We just talked to David. He's although his surname looks like Japanese, but he's not from Japan. So Jennifer, you are a product manager with Prototype?
I am for our in-situ systems, yes.
Yeah, so you have been working with Prototype for how long?
I have been with Prototype since January of 2018, so about 3.5 years.
Okay, good. Because we have long connection with Prototype, maybe from the last 5-6 years.
Yeah, no, that's great, and I'm hoping that we could meet in person someday. That would be fantastic.
But in India, there are few systems where Prototype holders are used.
There are two systems.
Yeah, two systems. So we have Gatton holders. Mostly Gatton holders are more popular in India. Gatton, but slowly Prototype holders are coming in.
Good.
We're looking forward to not only giving this presentation, but learning quite a bit about, what the community in India needs and how to make in-situ microscopy a more prominent technique in the country. We're pretty excited to learn more about kind of what the needs are in the lab and what kind of research people are doing there.
Yeah. That's what the purpose of this symposium. We want to make people in India to aware of these kind of developments happening across the world. And Chandrasekhar and myself is kind of wanted to do this symposium for this purpose only, so that industry people can speak and they can show the demos and show how how quickly things can be done.
Good, very, very good. And the talks yesterday, everything went well?
Yeah, things are well. The only problem is this, for the online symposium, only problem is the geographical time scale. Okay, so people in the US only can join in the evening of Indian time or in the morning. So today morning, June Law from Rice, he joined, and the time he finished his talk, it was almost 11:30 p.m. in Rice. Okay, so that's the main problem. And in the afternoon only, the Europeans and Japanese Europeans can join in the afternoon, only the evening. Japanese can join in the morning, and Australians also can join in the morning. So this is a difficult problem for online symposium. So that's why you have a very early morning slots, and I understand the difficulty.
Okay. One more thing, David, because you are the co-founder of the Prototype, right?
Yes.
And it will be, and if I saw it right, after your PhD, you started the whole this Prototype and so on. So because we have a lot of research students and community, it will be nice to know how the journey you started. Okay, so that people can understand, it's not just you buy a holder or start doing experiment. It will be nice if you spend some initial time how you went through developing it and what are the challenges you faced and some experience. Okay, that will be nice to have, if you don't mind.
Oh, I'm happy to talk about that. There's a first slide that talks a little bit about our background, and maybe I'll expand on that a little bit in the beginning if you'd like to hear more about how we got started. That sounds great. That sounds great.
Thanks, David.
So let us wait for 5 more minutes, then we will start. The only problem is that's what I told both the chairpersons today, that to manage the time. We have another session is coming up after 5 p.m. after this one, and we have 5 talks in this session also. So please keep in mind that you finish it up within 1 hour. That is the request we have from you.
No worries whatsoever. And like I mentioned, because myself and then Jennifer are back to back, she's driving these slides and I'll start. So my portion is going to be more of an introduction, maybe 15 or 20 minutes, and then Jennifer's will be the rest of it. So we'll just hand the presentation from me straight to her. And then maybe if it's okay with you, do questions at the very end. Is that okay?
Yeah, that is okay.
Perfect. Perfect.
I'm just making a request so that you are aware of it.
We'll watch the time for sure.
Yeah, definitely.
Krishna, I have a couple of questions. This is Shiva here.
Pardon?
Krishna?
Yeah, tell me, Shiva.
Yeah, so I have a couple of questions here. Okay.
Yeah.
What I understood right now is that the first talk, which is going to be shared between Dr. David and Dr. Jennifer, am I right? Between 3:30 to 3:30, am I right?
Yeah.
And the 3:30 to 4:45 is Newman and Perez.
Yeah. That's Newman and Victor Hugo, both are from DEM Solutions and Innovation, so they will also speak the time.
Okay, so the Innovation and the DEMS, okay, both same company or a different company?
Well, they are represented by the same company in India, by DEM Solutions.
Okay.
But they are coming from different companies in US.
Okay.
They will also share the time.
Okay. So that's why I just want to.
And the last person will log in at the late because he may be sleeping now at 3 a.m. or so in California.
Oh, Karki, yeah.
Yeah, Karki. So
okay, yeah, it is going to be very early morning for him.
Yeah. So he will join late. I think that's okay. Chandrasekhar will take care of that. He will make him wake up probably by sending some messages, right, Chandrasekhar?
Okay, got it.
Yeah, that's what we planned. We couldn't actually. The problem was, like I told him, either you sleep very late or wake up very early. So he chose to wake up early. So we have to manage with the time.
So let me just welcome. We are almost there. So this is the second session for the 9th of July. That is the second day, and this session is fully devoted to the industry presentations. We have two chairpersons. First one is my colleague from IIT Kanpur, that's Professor Shivakumar, and he is basically chemical engineer, and he has been looking after the microscopic facility and the facility here, and he himself is doing a lot of research on bio-inspired materials, drugs, and everything. He uses microscopy also a lot. That's about Shiva, and then we have Amit. Amit is a close associate of both of myself and Chandrasekhar. Amit was working with us sometime in Ministry of Science. Now he has joined, then he joined to General Electrics, right, Amit? And after that, he's now with SAVIC and looking after microscopic facility and product development in SAVIC. So both of them will take you through these, presentations. And I just hand over to both Shiva and Amit. They will slowly, the participants will join. They come from lunch. We have seen today morning also started with 50 or 45, and then we went up to 120. So it will gather momentum. So please go ahead. Otherwise, we'll lose a lot of time.
Okay. Thanks, Krishna. Amit, first I will introduce the first two speakers, and then you can introduce the next two. Is it fine with you?
Hello, Amit. We are not able to hear you.
Yeah.
Sure.
Okay, fine. And good afternoon, all. And
please go ahead.
It is a pleasure to introduce the two speakers, those who are going to present from 2:30 to 3:30. Dr. David Nakashi and Jennifer. So I will introduce one by one. Dr. David Nakashi has obtained the bachelor's degree in electrical engineering from Georgia Institute of Technology. Then he moved to NC State for his master's and PhD. After his doctoral degree, he is associated with Alcatel Telecom for 4 years. Currently, he is the CEO and also the co-founder of Protochip. And Jennifer has done her bachelor's and master's from the George Washington University and North Carolina, respectively. Currently, she is also associated with Protochip as the product manager. Prior to Protochip, she served in NC Department of Justice, US Probation Office, and so on. Okay, so many places which is I have seen her team. So now I hand over the dais to David as well as Jennifer, please.
Thank you so much. Can you hear me just fine?
Yes, yeah.
Okay. Well, thank you everybody for joining us today. I'd say this morning or this afternoon, wherever you are, Jennifer and I are here in Raleigh, North Carolina. It's about 5 o'clock in the morning over here. So good morning to those of you in here in the United States and in the Western Hemisphere, and I guess good afternoon to most everybody else. My name is David Nakashi, and I am the CEO and also a co-founder of Protochips. So what I'd like to do is we're going to combine these two talks since we've got two back-to-back, and I'm essentially going to give an introduction to our company and our vision, and in general, how we see the in-situ market. And at that point, maybe approximately 15 or 20 minutes through the presentation, I'll hand it over to Jennifer, who will go into more detail about the applications and products themselves and some of the great work that our customers and collaborators are doing around the world with these products. So on the very next slide, I'll talk just for a second here about our background and our company. And let me kind of walk you through just a little bit about who we are and how we got started. I did a PhD and my bachelor's and my master's all in electrical engineering. So I'm not actually a microscopist by training. And so many people sometimes wonder how we got into the field of electron microscopy. So my background in particular, as well as my co-founder, John Damiano, our expertise is in MEMS and MEMS design and in MEMS characterization. So when we started the company, it was always focused on the in-situ market for TEM, and that was where we got started. And after our graduate work, and much of that graduate work had to do with microfabrication, and in particular, circuit design, analog design, and in MEMS design and MEMS fabrication. So the core competency of the business itself really started in microfabrication of MEMS devices. And I think, as all of you know, that really has become the standard technology for much of in-situ microscopy. MEMS devices have an enormous number of benefits. Obviously, you can put a lot of small things in a small space, which fits into the pole piece gap within the microscope, which is certainly helpful when you're trying to put a lot of technologies and capabilities into the TEM. In addition to that, you're often working with samples that have a very low thermal mass, and the low thermal mass of the MEMS devices also really help reduce drift, in particular at high resolution. And of course, the holders themselves, these are very precisely designed instruments and with very fine features and very fine tolerances. So combining all things together, I think our core competency, like many others in this field, really kind of centered around MEMS design and fabrication and precision vacuum systems. And that's really where the business has focused and where we've really been known. The major in-situ capabilities that we launched through the first few years and we've held on to are in the areas of liquid, gas, and temperature control. And primarily because those focus on some of the most important markets that we've seen in the in-situ microscopy community, which includes batteries and battery development, corrosion, materials and corrosion, catalysis, and of course in heating, anything from ceramics to high temperature materials. You can see this video here on the left, and it looks a little choppy, I think, mostly from bandwidth, but if you were to see this, if you go to our YouTube page, I think this video is posted. It's very smooth, layer by layer growth of a nanowire. This work was done at CNRS/Paris Sud. This incredible work was done with one of our fusion systems. It was in a special TEM that effectively was designed to be a CVD chamber. So you're looking at this solid liquid gas phase type of reaction that shows layer by layer growth initiated through a temperature change using our fusion system. So this is in general the types of applications that we've seen and have worked with our customers and collaborators in the community to advance. Go ahead, Jen, you can change the slide. So taking a step back then, I understand a lot of the conversation earlier and yesterday was about how to get the market for in situ microscopy or the techniques for in situ microscopy in the market in India to advance. And so over the last, I'd say 15 years, we've learned quite a bit. I think the whole industry has, but in particular, we've learned quite a bit about the adoption of in situ and the adoption of these in situ techniques and how they, and how we could accelerate these around the world. And we've noticed a couple of things that I'm sure almost anybody who works within in situ microscopy has become quite familiar with. First of all, not to state the obvious, but the equipment, both the microscope and the TEM, obviously these are very sophisticated pieces of equipment, both TEMs themselves, especially the high-end TEMs, and then in combination with the in situ techniques, liquid, gas, or even some of the MEMS heating holders. So the operation of the TEM, of course, has a learning curve associated with it. But when you combine it with the in situ techniques, you're often doing two things at one time. And for those of you who have experience in situ microscopy, you understand, of course, there's often two different people. Sometimes there's somebody working on the microscope to keep the sample in the field of view and in focus and just operating the instrument itself. Somebody else actually doing the operation of the in situ experiment, controlling the temperature or gas or pressure or flow rates. And doing those two things at one time can actually be fairly complicated and difficult. And so because of that, I think we realize that those things can be barriers to people entering the community or entering the techniques for in situ microscopy, adopting them, and teaching postdocs or students in their lab how to become proficient or experts at it. The second is data management. And of course, cameras are faster and resolutions are higher. Data stacks are quite large. And in an in situ microscopy, which is especially a time resolved type of experiment, if these experiments last for hours, you can be left with very large data sets and stacks of images. And these are often pretty difficult to share with colleagues, with your PI, with students. And so that portion of it also has become an impediment or something difficult to manage. And lastly, data analysis itself. The data analysis is also, as all of you know, challenging in general. I think the tool flow through data analysis can certainly be improved in microscopy in general. But then when you do in situ microscopy, you've got to align your experimental parameters like temperature and pressure and gas and all of the in situ conditions with each and every image that you take. And in many cases, that's a very manual, tedious, and time-consuming set of steps. And so I think in general, what we're trying to say here is that in situ microscopy certainly is a powerful technique. And if you, as you probably saw through many of the presentations yesterday and this morning, there's just some wonderful things you can do and ways you can look at samples and experiments that you wouldn't be able to otherwise. But it does take time. And so we saw that as an impediment in the market, and we worked hard to try and reduce that learning curve and address each of these bullets, which much of this presentation today will be about. So everything we've decided to address our core competency and really add to it. And how do we get past those bullets? We thought certainly advances in the holder designs themselves and in the MEMS devices themselves will continue as they evolve. But we felt we needed a new technology, and we looked towards what a lot of people are studying today, and that's machine vision and artificial intelligence, and how the role of those technologies really could advance and help not just microscopy, but in situ microscopy. So we found that by connecting the sample, the camera or imaging systems, and the microscope, and using machine vision technology, that we would be able to address many of the problems or many of the issues stated on that previous slide. And that really is the heart of what we call Axon. And again, Axon is almost a wrapper. It's a control system for all of our in situ products, as well as it has use outside of the in situ techniques themselves. So at its heart, Axon does two things. It really is a smart automation tool for communication with the TEM. The second thing is it also focuses on organizing data management. So in the first bullet here, smart automation and communication with a TEM really has two major concepts with it. One is stabilizing the image, and the second is synchronizing your data. So with respect to stabilizing the image, you'd mentioned many people in India use the Gatan heating holder. And even with MEMS systems that have such a low thermal mass, at higher and higher and higher magnifications, especially for in situ, drift is still something that has to be managed. You're doing things in an in situ experiment to start some sort of instability in the system, whether it's from the reaction of the sample itself to simply the fact that you're heating something and there's no way you can completely eliminate drift. It's just a property, it's just the laws of physics. And so when things move, it draws your attention toward keeping them in focus and stable, and can certainly reduce the quality of the images and the resolution. And that's something we wanted to address. By stabilizing these images, you can reduce the amount of time that it takes to wait for things to stabilize, so you can catch reactions the moment they occur. Certainly, you make it easier to conduct an in situ experiment or even operate the microscope. You're not necessarily trying to do two things at one time. And like I mentioned previously, when the image is stable, certainly it facilitates capturing higher resolution images. The second part of this, and I think it's just as or more important, is the data synchronization portion of this. So data synchronization really gets to the heart of trying to bring all of this information and aligning it with every image. If you're in a gas cell experiment, for example, you've got flow rates and temperatures and pressures and all of these things happening and often changing at one time. All of those parameters need to go within each image itself, has to be aligned within each image. In Axon synchronicity in particular, which is the module that's used to control the heart, to control all of our in situ experiments, the microscope, and the camera data collection, really works hard to pull information from the camera, the TEM, and the in situ experiment and align and place it within every single image for streamlining analysis. So that takes you to the second bullet, organized data management. So the second part of this is how to take a look at all of that data that has all of this metadata in it and understand and figure out how to find correlations between the experimental parameters and the images. And that comes down to having the right kind of tools at your hands to sort and scrub and filter and view and look at correlations between the temperature and the STEM images, et cetera. So how do you find the data within many, many hundreds of gigabytes, if not terabytes of information quickly and efficiency? Sharing smaller manageable data sets. So how do you cut down to a smaller size to be able to publish and share and let people look at this information for their own? And then finally, plot and look at things like temperature compared with the images. And Axon Studio, which this whole second section is about, is a new tool that we've developed and we just announced last month, and we'll release for use in about 2 to 3 weeks for anybody to download and use. Takes care of that second section. So again, that top section is about Axon Synchronicity, and that bottom section is about Axon Studio. So a couple of quick examples on how this works. Axon Synchronicity, again, primarily is about data stabilization and metadata synchronization. So I don't know if this video is playing. It looks still on my end. Maybe Jen can try and get this to start. What you're looking at here, all right, what you're looking at over here on the right side, this is taken actually with a Gatan heating holder. This is a bulk furnace holder, and you're analyzing a 700 series electropolished stainless steel sample. And if you look over to the left, just traditionally, as you start to heat, in this case, you're starting at about 600 degrees and moving a little bit higher than that. There is an enormous amount of drift, and it does make it quite difficult to get high resolution images. This is on a standard 200 kilovolt TEM. It's just simply because that bulk furnace has a large heating mass associated with it. And as you heat even small amounts, the sample begins to move, which means you have to wait. And in some cases, some of these bulk furnaces, you have to wait for an hour for them to stabilize. If you look over to the image on the right, that's actually, you can see the temperature slowly increasing. and you're able to maintain an atomic level of, not atomic, but a high level of resolution to look at some of the microstructure, nanostructure, and even somewhat atomic structure of that sample, even with a bulk furnace. So what Axon is essentially doing is it's analyzing each image live, frame by frame, and it's adjusting the goniometer, the location of the beam itself, and then also applying a digital image correction, all live and at the same time. So even for very large amounts of drift that move many tens of nanometers or even hundreds of nanometers a minute, it will follow and track this sample by moving and adjusting the stage and the beam position, and even doing digital correction to keep the image stabilized in the region of view. And that's great because in situ microscopy typically lasts for, some of these experiments can last a long time, and the samples can move a long distance, hundreds of nanometers, even microns in some cases. These techniques are also great outside of in situ, in things like inserting your holder and waiting for it to settle, any sort of drift or instabilities from stage movement, changing imaging mode or accelerating voltage, and of course, any other in situ stimuli, not just temperature, but changes in pressure or flow rate or gas composition, which can change the balance of the cell to cause more drift and instabilities. It'll work to hold things still. And when you do that, the most important thing not only is that you're helping obtain a very high resolution image, but you're also making the entire experiment a lot easier to use. So second to this is using axon synchronicity to stabilize the image. It's also using it to align all of the metadata within each image itself. So this is an atmosphere example, and this uses our atmosphere product, and this is a copper catalyst. It's undergoing a Kirkendall effect. You can see you're in an oxidizing environment. And basically during this experiment using our gas cell called atmosphere, you can see here that there's a lot going on. You've got pressure held almost at 1 atmosphere. You've got a stable gas environment. You're changing the temperature from about 150 to 400 degrees. And if you look at the plots, what you're seeing here, the lower one, is the drift rate is somewhere around 20 to 30 nanometers per minute. Not uncommon, of course, while you're heating through a sample. But you can tell the sample itself really basically is staying in the field of view, and that's because Axon's holding it there. But you're also getting a lot of information, the temperature, the pressure, the gas composition, and even the location of the sample. You can see in that 3-dimensional plot is being tracked, and you can see how it's physically moving throughout the field of view, but you actually are physically moving within the TEM itself, although it looks stable in the image. And so what it's also doing is aligning all of this data, the spot size, the magnification, anything related to the TEM, the camera itself, the imaging conditions, and then of course all of this in situ information is all being integrated into each and every image for analysis later on. So that takes us to the data analysis section. So once you have all of this data and these data stacks, what do you need to do to understand kind of finding that needle in a haystack, or where the real information is within your data set? So like I mentioned, we just launched a new product called Axon Studio. Axon Studio is a tool that's primarily used outside of the lab, although you can use it in the lab as well. And it's a way that you can analyze these data stacks that come out of Axon, organize the information, organize it into libraries, sessions, and collections, to label this information so you can mark sections that are important and quickly come back to them, create tags, quickly create plots out of the metadata that's there without having to export to Excel or some other type of software to create some sort of a 2-dimensional or 3-dimensional plot. You can apply filters. So there's a lot of metadata within this. It's not just temperature and pressure, but we're also controlling things and helping with things like focus. So focus scores, you can quickly drop images that are out of focus and combine those that are left into a movie. And again, publishing, being able to actually publish your data, to take this data set, to remove things that are out of focus, for example, or highlight or focus on a section of a certain temperature where a reaction occurs, and to be able to frame average, just that section and to create an MP3 or an AVI movie to share with your colleagues or to put in a presentation. All of these things are possible, and it's a tool that's used to look at both the data set, to scrub it back and forth, and also to quickly be able to generate smaller data sets to share or to use to publish. So I've got a quick movie here on the next slide. It gives you an idea of what this particular solution is. And it's not a large data set. It's about 1,500 images, but it's designed much like an Adobe tool or iMovie, and you can scrub back and forth through this reaction, which Jen will show an example of in her presentation. You can see all of the metadata here over on the right. You can zoom in and out. Those lines become dots, and those dots are individual images. But you see how fast this is and how quickly you can scrub through large amounts of data. It's not shown here, but you can get more information from us. You can quickly add plots. You can see temperatures, you can see pressures, and those can quickly be added to the data set as well. So the last slide I have shows you how all of these pieces fit together before I hand this over here to Jen to talk about the products. And so as you listen to her presentation, I think she'll show how all of these pieces fit together, because one of the biggest questions we get is, why is Protochips working in all of this software? And I hope what I've shown you here is that what we're trying to do is create these tools to make the techniques of in situ microscopy more accessible to more people, to reduce the learning curve, and to increase the quality of the data. And I hope through her presentation, you'll see how this is done. So what you see here is, of course, over on the left, in the TEM lab itself, Fusion, Poseidon, and Atmosphere are our three main in situ products. Those are controlled through software called Clarity, which she'll explain. And all of that feeds into this synchronicity software I just explained to you, which is our machine vision and AI platform, which connects to many components of the TEM to stabilize the images themselves and to collect metadata. It's an expansion. It'll be expanded in the future with various modules, which we will continue to release in the years to come to focus on other applications. And then on the other side of this, of course, is Studio, where the data sets can be imported and then reviewed, filtered, organized, and published either in the lab or more likely back in your office, where you can look at data, analyze the data, and share the data. That's not just the image stacks, but of course, all of the metadata itself in a pretty quick, easy fashion. So that's how I think we can hold questions maybe here for the end when she's done, and that might make more sense from, I guess, when you see how all of this together. So Jen, I think the next slide is a transition to you. As an introduction, Jennifer is our product manager for our in situ system. She's got 3 years of experience, a chemist by training. She knows these applications quite well, and I think she's going to walk you through some of the most interesting ones. So take it away.
Thank you very much. Can you hear me okay?
I certainly can.
Okay, great. So yes, I'm going to talk about our in situ products here that we offer at Protochips, and I'll do brief introductions to the product itself and focus mainly on what our customers have been doing and what they've been publishing and been successful with in different application areas to inspire you. And then we can always provide brochures or talk to you separately later if you've got more technical questions about the product itself. But we've got 3 main in situ product lines: Atmosphere, Fusion, and Poseidon. And they range, like David mentioned earlier, Atmosphere does gaseous and pressurized environments within the TEM. Poseidon does liquid environments as well as electrochemistry and heated liquid environments within the TEM. And Fusion is more of a traditional, what we call an open cell or a vacuum exposed heating and electrical characterization system. And on the right-hand side, you can see a large handful of the different application areas that they all overlap in. And there's even more than this as well. And so I'll kind of show you that based on each product itself. But we'll start with the Atmosphere system, which is our environmental reaction cell for in situ TEM, introducing gaseous and pressurized environments. Excuse me. And some of the main application areas that we see and the biggest areas of research that we see with Atmosphere fall in this list, automotive catalysts, petrochemical catalysts, industrial catalysts as well. In addition, catalyst synthesis, so the step before the operation of the catalyst, Lots of catalysis, as you can see. The system really fits nicely into that research area and is meant to complement, some of the bulk techniques that people are doing to look at catalysts and improve upon them. But in addition to catalysis, corrosion of steels and alloys, especially with our ability to introduce water vapor in a very reproducible and controllable manner, high temperature coatings that protect, things like engine turbines, also are of interest in atmosphere. And there's a lot of other kind of niche areas too, semiconductor growth, and really anything where your sample is exposed to an environment, in air, in humidity, and you want to see how it interacts over time. And I think you're all here because you know how important in situ TEM could potentially be to your research, and so why would you use it for something like catalysis? And this really, this analogy kind of fits for almost all materials that you're looking at in the TEM in situ conditions. But when you're doing bulk techniques or running catalyst through a desktop packed bed reactor type of setup, and running mass spectrometry on the outlet gases, what you're looking at is an aggregate of each individual nanoparticle's reaction. Catalyst, the smaller the better, right? And so TEM is perfect for visualizing them because of how small they can be. 10 nanometers and less, ideally the smaller. But when you're doing these desktop techniques, what you're looking at is an aggregate of millions of reactions occurring at the same time. And when you're trying to improve upon the catalyst activity, efficiency, specificity, or so, you're going to have to dig down a little bit further to understand, well, how do I change this big picture? What are the colors I need to change this big picture, and shades, and what's going to look the best? And so when you go into the TEM and do in situ types of experiments, you're getting a much more localized analysis of the particles, and you're able to watch them morph and change, and you can correlate that to its activity and specificity. And you're seeing each individual reaction occur. And once you see which types of changes cause which types of activity, well, now you know the key. I gotta synthesize this so that the morphology doesn't create these facets like this, because that seems to bring the efficiency down 30%. And so, this is why in situ TEM is fantastic for catalysis, and most materials in general. The foundation of the world is based on atoms and what they're doing and how they're interacting with each other and reacting with each other. And when you understand that foundation, then you can make grand steps to try and make materials more robust, more cost efficient, better at their jobs. And so here is kind of the system itself, the atmosphere system. It's not just a holder. It's an entire gas handling system. You have the option of adding a mass spectrometer, the holder, all working together to get you quantitative and reproducible results that you feel comfortable publishing and speaking at conferences at. And so you get this custom-made leak-tight gas handling system here, where you can mix gases, you can adjust flow rates, you can introduce vapors, again, at a very reproducible and quantitative manner. And you're doing it at room temperature too. And so we've got, technology in the system to prevent condensation from ever occurring. We've got a very ultra quiet mass spectrometer on the outlet side of the holder that doesn't interfere or introduce additional vibrations to your imaging. So you can use your high-end microscopes alongside the mass spectrometer without any interference. We also have our self-aligning environmental TEM holder. And here's kind of a quick glance of how that's, how you even get your sample in the microscope. You've got a single hermetically sealing gasket. Oh, I apologize if that's choppy, but a single hermetically sealing gasket that goes in the bottom. And then you're going to use two MEMS devices to kind of sandwich your sample. The MEMS devices are what's used to apply the heat to the system. And then when you apply the lid and torque down your screws and add pressure, the combination of the chips, the gasket, and the lid together form a hermetic seal so that you can safely introduce the holder into the microscope. And again, the entire manifold is proactively monitoring gas pressures to ensure there's no leaks if any leaks were to occur, the whole system shuts down and without you needing to push a button. So it's keeping an eye on that for you. And then our chips are optimized for things like EDS analysis. And of course, we've got our Clarity software that works in combination with the Axon platform that David talked about before. But again, I'm not going to go into too much technical detail on the product itself. I want to show you what can be done with it. And we're happy to talk with you again so that if you need more technical details on the product itself. So some of the work that our customers have been doing, this is one of our favorites to show, but Dr. Xiaoxing Pan at UC Irvine in the United States is looking at automotive catalysts and the strong metal support interactions that are occurring between the catalyst particle itself and its support, and looking at how that essentially poisons the catalyst or deactivates the catalyst over time. Here we're testing in some different, very relevant conditions. The atmosphere system is set up so that you can introduce even the most complex mixtures without the need of trying to calibrate the system to any specific gases that you're using. It's agnostic to the gases. So you can create any mixtures you want and run your experiments at up to 1 atmosphere of pressure, go up to 1000 degrees Celsius. So you can create the most realistic environment possible. And here, Dr. Pan's group was able to watch the interaction of the support. Here you can see the oxide growth on this palladium catalyst material here. The support is starting to cover the catalyst particle, which essentially deactivates it and prevents it from doing its job. They're trying to understand which conditions can they use to essentially disintegrate this oxide layer and regenerate the catalyst so that it gets back to its operating conditions in situ. And maybe this could be used in the future in catalytic converters. The same group is also looking at single atom catalysts. This is a hot topic again because the smaller the catalyst, the better, because your surface area to volume ratio is ideal. There's no wasted catalyst material in there if you're using a single atom to perform the experiment. And so here they're looking at different activation conditions or pre-treatment conditions, because they notice when you pre-treat the catalyst differently, it's got a different activity level. And so here, they started with a baseline oxidative environment, and then there are 2 different pre-treatment environments, one a mild pre-treatment and one a harsh pre-treatment. And this is just at different temperatures under reducing environments. And they notice a shift in the catalyst and mobility of the catalyst on the support, along with a few other things that they were able to use to kind of hypothesize as to why they're seeing this change in activity when they use these different pre-treatment conditions. But you can see this is a single platinum atom that they were able to resolve within the gas cell at full atmospheric pressure under temperature. And then Fischer-Tropsch catalysts are absolutely of interest for the gas and oil field. And we've got our customer group at IPCMS in Strasbourg, France, looking at these really unique cobalt-based catalysts with these kind of urchin-shaped arms. And here they're just really looking at some different types of conditions that this catalyst would typically be exposed to. So they've got it under syngas, they've got it under carbon monoxide, they've got it under oxidative and reducing conditions, and just trying to look at the ways that the catalyst degrades. Sometimes voids are formed, sometimes, you've got carbonization that's formed, and sometimes they were able to even regenerate the catalyst a little bit, under certain conditions here. And so they're just trying to understand the different pathways to failure so that they can, determine if this type of catalyst would be useful in the field. And if so, how can they improve upon it to make it stronger? And it's really not just about the images, though. You need more to go alongside the images to tell the full story. Without the activity of the catalyst and being able to monitor that, then your images are only telling half of what the audience needs to know. And so we've developed the first of its kind mass spectrometer that's meant to work alongside of a TEM, meaning that it's not going to introduce vibrations and it's not going to interfere with your imaging resolution. And it's the only one of its kind, and it's due to the unique design of our manifold that we were able to do that. But here you see an example, and unfortunately, since this isn't published just yet, I can't show you the images that correspond with it, but hopefully soon. But at IPCMS in Strasbourg, France, here they're looking again at a Fischer-Tropsch catalyst of some sort, a nickel-based catalyst, and they're watching the methanation of carbon dioxide. So here's the reaction they're looking at primarily. Your reactants are in green and red, your products are in yellow and blue. And you can see here as they adjust the temperature, you see quite a change in catalyst activity that's occurring. You know, and at these higher temperatures here, you see huge jumps in activity. So you're getting more conversion than you were at a lower temperature. And so correlating this with the images allows them to decide which types of morphologies, you know, are ideal for, you know, under certain conditions for catalyst, for gas conversion. They're also monitoring the carbon monoxide intermediate here that you can see in purple. That obviously follows a similar trend, but we also, of course, want to reduce the amount of carbon monoxide produced. So we're looking at the specificity of the catalyst as well under these conditions. So putting this together, your mass spectrometry results with high resolution images, you know, that's what tells the full story, especially as you compare that to benchtop style experiments and correlate it with other types of techniques that are used to tell the full story of that catalyst material. Then when you combine atmosphere with the Axon platform that David was talking about, you get a whole new level of information that you didn't have before. For instance, here, we're looking at the reduction of iron oxide. So iron oxide is a difficult material to reduce down to metallic iron. In this video, I'm going to show you, we don't have it fully reduced down to metallic in here. This was just kind of the first step. But the leak tight system, the leak tight nature of our system, so no outside air, water infiltrates during your experiment, allows us to do this type of work. But the purpose here to show you, I'm about to play this video, but first I want to prepare you. This piece of data here is called match correlation. It's generated by the Axon platform that David was talking about before, and it's unique to Axon. It generates this as it's going through and helping to keep images in focus and keep them stabilized. But it can also be used to help you quickly identify when dynamics start occurring. So if you've got hundreds of terabytes of data, you pull up this match correlation in Axon Studio and you look for the peaks. You look for the peaks. This is where things started moving. And so here you can see for this particular example, I'm going to show you right here at about 430 degrees Celsius, you see a peak. This is where we would expect dynamics to begin. So I'll play the video. You can see the temperature ramp right here. And you'll watch these facets of iron oxide, you know, changing and producing here right at about 430 degrees, if it's going to move smoothly for me. But that's where you see the growth start to occurring of these different facets and platelets here. And you could have just pulled thousands of images up in Studio and pulled up the match correlation for this experiment and looked for the peaks and found it immediately. And then created a video specific, just like we created this video here through Axon Studio, specific to just this small area and eliminate all of everything else that's standing still and not doing anything dynamic. Maybe you're just preparing the field of view, etc. I apologize that it's not as smooth as I would like it, but we're happy to share this slide with you too as well, if you want to look at it more closely. And Axon Studio also obviously can be used, like David said, for downsampling, frame averaging, producing representative high resolution images that you want to use in publications to share with colleagues, you know, and just producing videos and such makes that so much easier. So I'm going to move, let me keep an eye on my time here. I might have to talk a little faster. I'll move into our liquid cell system, Poseidon Select, which allows in situ liquid imaging, heating, and electrochemistry within the TEM. And unlike atmosphere, which seemed to have a pretty focused group of research areas in catalysis, Poseidon has a wide breadth of applications, anywhere from nanomaterial characterization, you know, and just looking at things like, you know, from the pharmaceutical areas, cosmetics, paints, you know, things like that that are supported in liquid media, to looking at materials related to corrosion of steels and alloys again, batteries, lithium ion, sodium ion batteries, catalysts again, fuel cell catalysts in particular, biomineralization, with our ability to mix liquids, pharmaceuticals, biological materials as well. I mean, it's just anything that is in a liquid media in its, quote unquote, natural state or everyday state, has the potential to be observed in the Poseidon system. And much like we were talking about why in situ TEM for catalysis, why would you even want to try and introduce a liquid into your TEM? And, there's some really compelling reasons, and it's become a very safe technique over the years. In traditionally TEM, since it's in vacuum, your conventional samples are prepared by drying them, embedding them in a resin, freezing them. But is this really representative of what you're looking at? Not usually. Again, this is kind of the overarching concept for in situ in the first place, is looking at your material in vacuum, representative of your material in its natural state. And so when you're looking at your material in liquid, as opposed to these traditional preparation techniques, you're getting a much more realistic view of how your sample is acting in the real world. And so our Poseidon system is a modular system. The holder, which I'll show you on the next slide, you've got the option of adding capability over time as your research changes. You don't have to make the decision up front. Do I need heating? Do I need electrochemistry? Am I ever going to need that? You can buy our base system, just do liquid imaging in a static or a flow environment. And you can always upgrade it later to one of the other capabilities, as your lab changes, your research changes, as your funding changes. But the way you introduce the sample is going to look very familiar to you. The form factor of our Poseidon holder is just like our atmosphere holder. And so you have the same self-aligning holder assembly, where as you're putting it together, the windows that the electron beam are shining through align right on their own. You've got one, again, single gasket to reduce the amount of leak points that you potentially could create as you're assembling and before you leak check in the holder, or leak check before going into the TEM. But it's meant to be simple so that you're not spending your time with extra tools and gadgets trying to align everything. You're able to assemble, leak check, get into your TEM and get some work done. And you do have the ability to do static experiments. Like I mentioned, you don't have to flow liquid, but you can. And if you do, you have the opportunity to flow 2 individual liquids that can mix together right here, just outside of the viewing area, so that if the mixing is what initiates your reaction, like in different types of nanoparticle synthesis types of areas, you're going to have the best opportunity here to see that reaction initiation, the seeding and the growth of your nanoparticles or nanomaterial there. So let's go into some just different examples of what our customers are looking at. There's so many. We've got a bibliography that we're happy to share with you if you want to scan the hundreds of papers that are out there. But we've got customers looking at different biological materials. There's a lot of work to be done in the life sciences area still, but there's been a lot of leaders in that area that are, inserting things like viruses, proteins, cells, whole cells, even liposomes. And we offer a range of different MEMS devices to try and accommodate for your sample size. You can make that space in between those 2 MEMS devices as small as, you could put the chips right together and let your sample create the space. You can have 50 nanometers, 150, 500, 1 micron, 5 microns. The goal is flexibility for you. There's always going to be a solution to maximize your imaging resolution and work with your sample size. Here's an example of from the biomineralization area, looking at these microemulsions that start to precipitate out calcium carbonate once a specific trigger is introduced. And here in particular, you've got these micelles that are floating in this isooctane solution. Once you introduce ethanol, though, it causes destabilization of these micelles, and then you see the precipitation of the calcium carbonate. And I think it's kind of difficult to see here, but there's the ethanol front being introduced from the second inlet port of our system here. And what they did is kind of adjust the flow rates on their pumps to kind of adjust concentration as it mixes. And once the ethanol is introduced, you then immediately get destabilization of these micelles. They break down and break apart, and you get the precipitation of calcium carbonate here. Fuel cell catalyst was something I mentioned before. And here, authors at Shanghai Jiaotong University paired with UC Irvine are looking at these really unique platinum palladium square shaped core shell particles and trying to understand, again, the different degradation pathways that the particle may take in order to develop something more robust. Let me back it up. And each particle, they're looking at a few different defects in the particles. You've got a cube with corner defects, terrace defects, and then you've got one with no defects. And basically they're watching the galvanic etching of the particles to try and determine which pathways degrade the fastest, how do they degrade, in what order are they degrading, and using this type of information, to try and make a much more robust particle. Here they saw, in bulk experiments that, when they incorporate this particle into a fuel cell, only 12 to 36% of the catalytic activity is preserved under operational conditions. And so here they were trying to understand why that is. And they noticed these defects, they noticed these different degradation pathways, and now they can work on generating something a little bit more robust to the conditions. Of course, battery research is highly of interest with Poseidon used with our electrochemistry set. Excuse me, here we're looking at Nigel Browning, Lila Meddy's work of, they're watching essentially a lithium ion battery, the capacity of it fading over time. And here what they're looking at, this is a platinum working electrode from one of our MEMS devices, and they're trying to understand this solid electrolyte interface on the electrode and understand what's leading to battery damage, short circuits, fires. If you recall, some lithium batteries not too long ago having some issues, what leads to that? And so here they're cycling the voltage, and once you see it, you can watch it kind of track it here. Once you see it go into the negative direction, you're going to see the deposition of lithium dendrites coming out of solution. And then once you go back into the positive direction, you're going to see the redissolution of some of the lithium back into solution. And the fact that you did not redissolve all of it, you've got these dendrites that stick around. And as you go into cycle 2 of charging and discharging, here we've moved the field of view out just a little bit so you could see a little bit more. But again, we're running the same cycle. And as you hit in the negative direction, you get deposition again on top of what was already there. And again, only a little bit of redissolution of lithium back into the electrolyte. As these dendrites build more and more over time as you're cycling, you eventually get things that touch, you get short circuits, you get fires, and the battery life is quite diminished by this. And so here they're trying to understand the dynamics. When does this start occurring? How many cycles, and what can I do to help redissolve this? Is there a way that I can cause better, more effective dissolution of the lithium over time? Fuel cell catalysts. Let me see where we are here. I have to talk faster. Fuel cell catalysts. This example was just a particular commercial catalyst for fuel cells, Tanaka TEC 10B50E. What was interesting about these is that they're very small, 3 nanometers being looked at in liquid. And they're trying again to understand how the surface area, the active surface area, depletes over time. Here they did some tests to make sure that the beam wasn't interacting with their electrochemical experiments. They got great reproducibility here. You can see some testing. They did testing over about 500 CV cycles. They've got the beam on and off here, and they're able to watch the cathodic shift as the size of the nanoparticles starts to increase and your surface area to volume ratio actually starts to change. And what was most interesting about this is that, using filtering techniques, the resolution here was pushed down below 1 nanometer. Again, these were very small 3 nanometer catalyst particles, and it correlated back very nicely to some ex situ data that they had collected here. Looking at the corrosion of steels and alloys, this is from the University of Manchester, where they were looking at this manganese sulfide inclusion in, I believe it was stainless steel 304. Yeah, 304 stainless steel. And they're watching it dissolve over time. So they flowed in 24 hours worth of time, water through the cell, and did EDS, at the beginning of their experiment in situ. And then at the end of their experiment in situ, they did not have to remove any of the liquid from the cell in order to do EDS. And what else was interesting about this sample here was that it's not nanoparticles, it's not catalyst particles, it's actually a fib lamella. And we've recently released a new e-chip, very specific for electrochemistry to be done on fib lamella, to ensure that you can deposit your lamella in a very precise manner so that the MEMS device is not damaged, your time at the fib is not wasted. And we've got lots of guides that kind of help you do that as well. But our special fib e-chip for electrochemistry was released, I think, in about 6 months to a year ago. And she used, here in Manchester, they used kind of a prototype version of this here. But again, they did some testing with the beam on and off to feel comfortable that, the beam wasn't going to interfere with their experiments the way they had everything set. And this compared back very nicely to bulk scale results. And finally, combining Poseidon Select with the Axon platform that David mentioned earlier, again, you get a new level of depth of data. Here we're watching just a basic example of gold dendrite growth onto these nanoparticles here. First, it's beam induced, and then it's temperature induced to accelerate it. And what I really want to point out here, you've got the stabilization, of course, and the metadata integration, but Axon is also integrating into the metadata all of the dynamic parameters used to calculate dose. Dose is so important to track, especially with liquid cell experiments where radiolysis products are easily produced and can damage your sample. If you want reproducibility in liquid cell, tracking dose, recording dose, electron flux, cumulative dose of your experiment is critical. And so Axon Synchronicity is actually embedding all of the data that you would need to do these calculations for every image, so that it's in Excel, a couple of formulas, and you're done for every single image in your data stack. We've got a technical note if you're interested to learn a little bit more. And I'll probably move pretty quickly through Fusion Select here. This is our heating and electrical characterization system for TEM, not a closed cell like you were seeing with Atmosphere and Poseidon. This is just open to the vacuum. The application areas, again, for this, very, very wide, lots of fundamental material science research being done here as well. Nanoelectronics, and then semiconductors in addition, metallurgy, pretty much anything you want to see how they change under temperature, do an electrical characterization experiment if you've got something to see in the TEM as well. What's interesting about our system versus the rest on the market is that it's modular. And so again, you don't have to make the decision up front if you need electrical characterization, electrothermal capabilities, if you even need double tilt, but it's a little bit pricey for your budget at the moment, that's okay. You can start with a base system, single tilt with heating. You can always upgrade to double tilt or electrical characterization at a later point in time without needing to buy a new holder, without having to send the holder back to us. And so this is really great when you've got limited budget. You need a little bit of data to kind of inspire some more budget to come along, and then you can upgrade without needing to buy a whole new system or trade in your system or anything like that. And the premier stability, superior stability of our system, allows for really nice high resolution imaging. Of course, it's compatible and optimized for any EDS detector that you may have. And we've got for our heating experiments several different supports on the MEMS devices for your sample so that you can choose a support that's not going to interact and will optimize your resolution, including our most popular, which is holy carbon, a holy carbon support on our heating devices. maximizes resolution while supporting most nanoparticles. And if your particles interact with carbon, we also, of course, have a silicon nitride option, and then a through-hole option, which means it has no film. You put things like lamella, things that can span wider distances, lamella, thin films, some nanowires as well. So we got a lot of flexibility. Flexibility is a common theme for us. We also are strong proponents of supporting those who want to do experiments on fib lamella. Lamella can be much more challenging, of course, than just drop casting nanoparticles. And we want to make sure that your time spent at the fib preparing the sample is not wasted. We've got special fib optimized E-chips for electrical characterization that we've produced that could make the process much more like your typical half grid deposition. If you're depositing on a half grid, there's no special angles you have to create in the fib. You know, there's no short circuits that you're going to create. It's much faster than the typical membrane-based deposition here. So we're really strong proponents of supporting fib lamella deposition and research through all of our products. We've got guides and chips specific to all of those. And just a couple examples real fast. You know, from the heating side of things, you know, hafnium oxide nanorods here for device miniaturization, electronic devices. And here they're understanding the phase transformations, you know, of course, at atomic resolution, nice stability from the system over the course of a heating ramp. The and I can share, please reach out if you want any of the citations for any of these. We can make sure you can get the paper and read it more closely. But here's an example where they're using the electrothermal capabilities of our system, simultaneous electrical characterization and heating, where they're looking at carbon monoxide sensor materials. They're decorated these tin oxide nanowires with these iron palladium nanocubes, and they're watching how the resistance changes in an ETEM as carbon monoxide is introduced, mixed with oxygen. And so they're monitoring the resistance changes and making sure that if carbon monoxide is present, they've got a way for the sensor to trigger you know, when it's used in the real world. And they're also taking a look at the voids or the defects that are produced, you know, under typical operation here. And finally, from the electronic side, you know, looking at graphene and observing structural changes and effects of high current densities as they're flowing through the material here. And Fusion can also be paired with the Axon platform. And what's great about the Axon platform in particular with this example is that this is our demo sample, and Axon is recording the whole time you have it on. You don't have to think about when you're going to initiate a capture of an image. Oh, something great is happening. I should have hit start. You know, you don't have to think about it. It's always recording. And so as we did this experiment with our demo sample that we do all the time to show customers the capability of the system, we had never seen the graphitization of the carbon of our support occurring over here in the corner. It was really cool to see, as you can see, the carbon growing atom by atom, just in this sample that we've seen all the time. But we were able to go back and look closer into the different corners of the images, and, you know, because everything was recorded and saved for us. I think I made it. So in summary, you know, obviously TEM studies, both traditional and in situ, critical to the development of novel materials. And here at Protochips, you know, we want in situ to be accessible by the masses. We want to make sure that everybody has access to it, that people aren't afraid of it, and that you're able to get good results and publish in high-end journals. And we just want the experience to be great for everybody that tries it out. And so we're here trying to make in situ TEM, you know, much more accessible to the masses. Okay, and that's everything I have. Thank you so much.
Great, thanks, Jen.
Thank you so much, Dr. David and Jennifer. And now the floor is open for questions.
May I ask?
Yeah, please.
Okay. David and Jennifer, fantastic talk. So one question, where are we in terms of getting HR STEM along with the liquid cell imaging?
high resolution STEM with liquid imaging, is that possible?
Yeah, like, are we able to resolve align nanoparticles in liquid cell and try to see what happens to composition? May not be liquid, even gas. Are we able to do something like that?
Yeah, so we had definitely in gas and liquid, things become more challenging when you're trying to deal with radiolysis products and such. But we've got chips that are designed for both liquid and gas so that your sample can go on the top chip during your addition of stimuli so that you can do STEM imaging, definitely high resolution, atomic resolution STEM imaging. One of the first cases I showed for the atmosphere system was that. And so, but for liquid, you just have to be more careful. It's gonna be much more dependent on your sample, how much it can sustain as far as the radiolysis products that are produced as you go into higher magnifications. There's a lot of variables to consider with liquid cell, but it is absolutely possible to do STEM imaging during electrochemistry, during heating. And it's just, there's gonna be a lot to think about as far as just not changing the chemistry of your sample and its interactions due to the magnification and the dose and the flux that's coming in. Does that make sense? So this is an example. This is STEM imaging here from Dr. Pan at UC Irvine. They've always had great results. You know, it's going to depend, of course, on your microscope too, the resolution that you can achieve. But as far as that, you know, the gas cell, the 2 nitride windows, the cell, that's not going to hold you back necessarily if you've got the proper equipment to reach that type of resolution. I don't know if David, you want to add anything, but you're welcome to.
No, that's a great summary. I think we learned early on with the closed cell systems, that was one of the first questions is how they differentiate from systems like dedicated ETEMs. And we learned quickly, like many in this field, that if the nitride windows themselves, which are amorphous or thin enough, and the probe is certainly in the right conditions, that achieving these bright field STEM images are certainly, and high resolution STEM is certainly very, very achievable in a closed cell system, especially at the gas cells, and even combined with EDS techniques like EDS maps. So that's also certainly possible, and there's publications on that too.
Thank you. Next, Mr. Pawan.
Can you hear me?
Pawan?
Can you hear me? Yeah, sorry.
Yeah.
So my question, could you give a bit more details about this E-chip that you have, where you don't need to, you know, you make electrical contacts, but not really with a lot of sample preparation?
So let me find a better image here, a little bit bigger. So the E-chip, as far as preparation of your sample onto the E-chip, you know, we've got 6 application scientists around the world that can help support you with your preparation, from drop casting to different types of physical vapor deposition techniques like sputtering and E-beam evaporation and such, to fib lamella deposition. You know, our apps team will absolutely help support you based on the sample type that you want to deposit on the chips. As far as assembling the holder, each of our in-situ systems requires at minimum 1 MEMS device. So the vacuum system requires 1 MEMS device, and then these closed cell systems for liquid and gas require 2. So you're gonna place your sample in between the 2 chips, and the gap that's created here is created by a spacer on the chip itself. And so for liquid cell, we've got a range of different spacers for you to choose from so that you can optimize resolution along with, you know, based on your sample size. The gas cell has a single spacer size at 5 microns. And when I was talking earlier about assembly with minimal, you know, tools and gadgets that you need, I just mean as you put the holder together, the gasket in first, the first MEMS device, the second MEMS device with your sample on it, and then you put the lid on, everything is aligned. So your electron beam is flowing through. Let me see if I can get this to stop. You've got a silicon, You've got a silicon nitride window in both chips, in both of them, one here, and then one in the top chip. And you have to make sure those 2 windows line up with each other. Your beam is not going to travel through and you're not going to see anything. And so the way our holder is designed, a special pocket for the small chip, these guides here on the sides, You did see the electrical contacts here on the back of the holder, but you don't have to use a chip with electrical contacts. You don't have to. For liquid cell, you can just have 2 chips with no contacts if you want.
Yeah,
but
yeah.
everything lines up as you're assembling it, so you don't
Correct.
have to worry about those windows.
Yeah, I understand this, but I didn't stop you. This was not because this was interesting too. But I'm more interested in the fib preparation on
I'm so sorry.
electrical chips that you're talking about.
I'm so sorry.
No, that's okay. This was also good.
No, so we've got these specialized chips for fib electrical characterization of different lamella. There is no heating membrane on these. And you can see this is essentially the shape of it here. What it has that's unique to it is this special notch down the middle. So you've got your electrical contacts on either side of this notch. And this notch here, you're going to deposit your lamella across this. And what's great about that is that when you do your attachment with gallium or something along those lines, and you have overspray, you're not going to create a short circuit here. With a membrane-based chip, you're more likely to do something like that. If you wanted to put a lamella on a heating chip, for instance, or one of our electrical chips with a membrane, we've got techniques to kind of help you minimize that overspray. But if you're just doing electrical characterization, these are the perfect chips. We've got a special fib stub that they stand vertically in. And so that your deposition process is very similar to your traditional techniques when you're using a half grid. You're depositing across this gap here, so you're not going to get any short circuits. The workflow is going to be very familiar to you. And that way you can feel confident that the time you're spending in the fib, you're getting your fib on the chip, that it's going to be a successful deposition. You're not going to damage the chip. You're not going to damage your lamella. You can thin from both sides. And so it's meant to make that workflow, which was challenging over the years for our customers, much more straightforward.
Okay, great. All right, thank you.
I'm so sorry. I didn't catch that at first.
Sorry. One more question, I think, from Dr. Ashutosh. Ashutosh, can you unmute yourself and ask the question?
Yeah, can you hear me?
Yeah, please.
Yes.
Yeah, the same questions what Pawan asked. So this is again the E-chip, this lamella preparations. So here in what you are showing the facility, basically you directly put on the lamella, you cut from the sample and put directly on the lamella without making any angle for the polishing things. So how you make the electrotransparent on the E-chip itself, right?
Yeah, you transfer with the micromanipulator onto the E-chip directly. We have a guide, a step-by-step guide that kind of shows you exactly the steps to take to do this successfully. But yes, you're going straight from your bulk sample to the chip itself. There's nowhere in between, and you can do the final thinning on the chip.
Oh, so this is the same things we do for our dense also. So there is anything new on it, right? So generally we do the same thing when you attach for the electrical contacts, and you do polishing from both sides by tilting the samples like plus minus 2 or 3 degree. So this is the same thing here also, right?
Well, we have no silicon nitride membrane here. So there's no membrane that can be damaged, and there's no membrane to catch overspray as you're doing the deposition. This is all, let's see where my mouse is. This is all just silicon chips. So there's no membrane. So you're taking that out of the equation with the potential breakage of that. But you also have no membrane to catch overspray as well. The gap here is probably about 15 microns. And so it's quite a bit of space to make sure that you're not getting any short circuits along the way. This also sits vertically in our fib stub as opposed to at a 45-degree angle. So when you're sitting vertically, it becomes, the workflow for this becomes very much like when you sit at a TEM half grid, standing up and doing your deposition onto that. And so people don't have to learn, our customers don't have to learn a brand new workflow with kind of nuanced angles and such in the fib. So it's a lot easier.
Okay, thank you.
You're welcome.
We can take one final question from Chandra. Due to time constraints.
Sorry, I couldn't resist asking this question. See, most of these in-situ experiments are very much material specific. Okay, so when we are doing experiments, every experiment is unique. Now, most of the things need a lot of optimization, and this question is more to David. Suppose we get some of these holder in India, and we need to do things, and we need some, live help and so on. how protochip can do, if you have some plan.
Yeah, that's actually a really good question. So I think there's two aspects to that. The first one is help within the company or directly from ourselves. So we've got both application engineers and we also have installation technicians in basically all major areas of the world. So we have a team in China that's fairly close to the time zone with India, and so certainly providing help and support. It doesn't have to be directly back to the United States. We of course also have an office in Europe as well, but we've got a great team of applications engineers, over a dozen of them actually, and each one of them specializes in a different area, application area, and different product. So if it's support with any of the electrical work, we've got Remy. If it's support for liquid work, we've got Dr. Madeline Duke. So we have people around, but not only for expertise, but also in each major region of the world. The second thing, though, I should mention, which is just as important, if not more important, is, of course, we can't be experts in all of these applications. Nobody can. And so one of the other things that we really work hard to try and do is connect our users together. Before COVID, we were running a regular series of user meetings where we would pull our users together in different parts of the world, in Asia or in Europe or in the United States, to try and share data and information and techniques with each other. We're looking to do that more virtually now, but one of the other tools we use is we have an online success community where you can look for knowledge articles on any of these techniques, post questions, and get answers back as well. So I think those are probably the major ways to do this from us, is interfacing with our experts either digitally or directly. We're all over the world. In addition to that, kind of utilizing some of the techniques that we have in place to bring our users together to try and talk and collaborate with each other on something that's particularly specific. Does that help?
Thank you so much.
Yeah, sure. I think that last part's important, and conferences like this are critical. I think it's great. And the more we can connect each other together to help and support each other, I think the faster the techniques and the community will grow.
Right, because see, we have been doing this experiment. If you are in US, it's fairly easy because you have a chip, you got to do something done, you just ship it up, get it done, and come. But when it comes to different country, shipping and handling takes forever, and finally, the logistic, is a challenge, and especially if there are not too many users in the country, it become even harder, right? So yeah, we can talk more detail in future, in subsequent meetings, and then
yeah, I'd love to. I know we're out of time, and I'd love to discuss that. So certainly increasing footprint is a key part of that as well. But that's certainly a great question. Absolutely.
Thank you. Thank you, David.
Yeah. So now it's time to thank David and Jennifer for a wonderful talk, and it's a very good product which is you have it. I hope Indian community will get benefited by your talk.
If I Dr. Shivkumar, Dattu has a question, I think, to David. What kind of camera is needed for imaging? So he just posted in the chat.
Oh, is it okay?
Okay, very quickly, I'll just mention, you're welcome, by the way, for more specific information to reach out to Simon Ma, or to Jennifer. But very briefly, any type of imaging system that is embedded within GMS or TIA, and a 64-bit version of GMS or TIA is going to be compatible with Axon. So if you're talking specifically about Axon, it's any camera that can be embedded within GMS, the 64-bit versions of GMS 2 and 3, or within TIA. Those are going to be the ones that are compatible with Axon. Obviously, with respect to In-situ in general, anything that's running on the microscope, but I think you mean Axon specifically.
Yeah. Thanks, David and Jennifer. Now I'm going to give over to Amit.
Thank you, Dr. Shivakumar. So I am Amit here, and I will be chairing the this rest of this session. And I first thank to organizer Professor Kishanur Biswas and Professor Kambhaskar Tiwari for giving me this opportunity. And as we are running short already by 45 minutes, and we don't have much time So, need to be in speed up from here. And for the next slot, actually, this 45-minute slots should be shared by two speakers again. So the first I should invite Dr. Jan Newman, and he is CEO and co-founder of Nanovision, also owner of Optic Instrument. He has earned his PhD degree from Brno University of Technology and master from the same university. So without
Yes, hello everybody, can you hear me?
wasting much time in this short introduction, I should invite Dr. as we are running short. So I request you if you can finish in 15 minutes, then we can have 2-3 minutes for the question and answer session, so that next speaker can take over from there for another 20 minutes or so in this slot. So is that okay, Dr. Newman?
Sorry, I did not understand. So we will meet in 15 minutes?
So time slot is given 20 minutes for you.
Yeah. Okay, perfect.
So
I will
give you a reminder after 15 minutes. So
okay, perfect.
You can
yeah.
finish it in 20 minutes time. Is that okay?
Yes, is that perfect? Thank you.
See the lot of questions that coming. We can take up a few questions.
Yeah, perfect. Thank you very much. I will share my screen. So I hope that everything is working. Can you see it?
Yes.
Okay, perfect. Hello, everybody. Thank you very much for a kind introduction. My name is Jan Neumann and I'm from the company Nanovision. And what I would like to talk about is about the combination of AFM inside the SEM, and more specifically about the correlative probe and electron microscopy. So right now I will not talk about the TEM, but the SEM. So thank you very much for the Summer Instrument Company, who is our partner for Indian region. Let me briefly introduce our company. So we are located in the Europe, we call it heart of the Europe in the Czech Republic. In Brno, we are a spin-off company from the university. And Brno is quite well known for the university tradition, but in the electron microscopy specifically is known as a center of electron microscopy. About 30% of the scanning electron microscopes are produced in Brno, because companies like Thermo Fisher Scientific and Tescan company or DeLong Instruments has a main production plants in Brno. So we say we have an electron microscopy in the DNA. What I would like to introduce is our product. It's a light scope. It's an atomic force microscope, which we take and put inside the electron microscope, as you can see on the image, and we can perform then 3D correlative analysis of various samples. So what we are saying that we are merging the forces of AFM and the SEM. And now I would bit of describe why to combine atomic force microscopy with the electron microscopy. There are several reasons. One of them is that each of the microscopes see something different, because atomic force microscopy, probably as you are aware, is based on the interaction of very sharp tip with the sample. And so what we are doing during the analysis, we are actually touching or almost touching the sample. On the other hand, scanning electron microscopy is based on the interaction of focus beam of electrons with the sample. So in the other hand, what we are doing, we are mainly looking at the sample. So bringing both touching and looking the sense is quite important and quite strong. What are the advantages? That each of the techniques like atomic force microscopy and secondary scanning electron microscopy, they can do a bit of different analysis. So we take the best from both of them, and AFM will provide you very high resolution 3D topography. You can analyze mechanical, electrical, or magnetic properties at the nanoscale. On the other hand, we utilize the SEM for very fast and precise 2D imaging, but you can also do the chemical analysis do the surface modification using the focus ion beam. And bringing the light scope inside your SEM, we are enabling to get from the both of them. So this is what I will try to show how we do it and what you can expect on such an in-situ add-on to your SEM. Just briefly, how whole setup works. So what you see on the left side is an electron microscope, and inside you see our light scope. So we mount the AFM head to the stage of the electron microscope, and then you just plug the feed-throughs, cables. We have a control unit outside, and you have a software. Software is actually operated via the web browser, so you don't have to install anything, and this is really straightforward. So I would say the usage is as a different or another accessories for the electron microscopy. To give you the brief introduction, I think the fastest way is just to show you the promo video to introduce the light scope in more details, so enjoy it.
The growing need to characterize and analyze structures in the nanometer range and the complexity of such measurements with various instruments create a demand for automated solutions and advanced correlative analysis. That is why we have developed LightScope, a unique compact atomic force microscope designed for plug-and-play integration into scanning electron microscopes. With LightScope, you are able to merge the forces of the two of the most used techniques for sample analysis on the nanoscale. Measuring with LightScope is intuitive and simple, yet precise and time-efficient. Its integration into the SEM prevents sensitive samples from contamination or oxidation, as the measuring is done in the same place and under the same conditions. LightScope enables precise localization of the region of interest and AFM tip navigation. It extends the capabilities of SEM by measuring a sub-nanometer topography, together with mechanical, electrical, and magnetic properties of the sample. LightScope incorporates a unique imaging technique called correlative probe and electron microscopy, shortly CPEM, enabling simultaneous acquisition of AFM and SEM data. LightScope and the CPEM technology allow sample analysis in a way that was difficult or impossible by the two imaging technologies separately. Together, they bring new possibilities for advanced correlative imaging in a variety of scientific and industrial fields such as material sciences, nanostructures, semiconductors or solar cells industry, life sciences, and many more, defining their own category of the correlative microscopy.
So there was a brief introduction of the product, and actually I think you could see how we use it and how we put it inside the SEM. And now I would like to highlight some points and also show you some results. So with the LightScope, we are tackling the several issues. So one of them is that the difficulties to do the complex sample analysis at the nanoscale level. The second, and this is actually the most important, I think, for this symposium, is ability to do in-situ sample analysis. And the third one is that we try to help with the difficulties with precise localization of the region of interest. Simply, if you have a specific particle, specific area, which you want to analyze by AFM and SEM, so this is where we go. Our vision is to provide scientific information about the samples which are otherwise unable to acquire, or it's extremely complicated. So if I will talk about the complex sample analysis, I will show you and I will discuss the technique, the CPEM, which is multi-dimensional correlative imaging, which enables simultaneous acquisition of AFM and SEM data, and I will show you some results. So if you imagine molybdenum carbide sample, this is how these are such a flakes, and this is how you observe it by the normal SEM. What you can do with the LightScope and with the correlative imaging, that you can simultaneously acquire also the additional data like mechanical properties, topography, conductivity, or use EDX for the chemical to get the chemical composition. So it's very time efficient, and it's quite unique to get all the data together, because within the tens of minutes, you can get the analyzed by the SEM, but also on the AFM from the exactly the same area. And then you can nicely correlate and correlate all information and characteristics together. So this is our approach for complex sample analysis at nanoscale. The second important topic is the in-situ analysis, because we place the AFM inside your SEM, so you can analyze the sample at the same time, in the same place, and under the same conditions. So you prevent your sample to any contaminations or changes during the possible sample transfer. So again, this is the scheme when you have an AFM, and you can use a SEM, several detectors. You can use a focused ion beam, or for example, gas injection systems. I'm quite proud that our scientific ambassador in this field is Mark Willinger from the ETH Zurich, who called the light scope the Swiss Army knife inside your SEM, because it enables you to do quite a lot of in-situ analysis measurements. One example for in-situ analysis, so this is a sample, it's a iron nickel, when customers do the magnetic nanopatterning, because they are using the focused ion beam to irradiate this thin film and change the paramagnetic properties from the FCC structure to ferromagnetic to the BCC structure. And because we have a simultaneously AFM installed, we can immediately look and compare how the changes reveal in the topography. So since this is maintained simultaneously, we can also check and analyze all of these contrast which we see in the electron microscopy. So by the end of the day, we see them also in the topography, which is half of the nanometer step between the FCC and BCC. And together we can merge both images together. So then you can directly correlate how the topography is really related to the contrast in the electron microscopy images. Yes, so there is a lot of benefits. So it's an in situ. You can use a focused ion beam to induce the transformation. Then you can immediately perform the AFM measurements. The third area where we see the highest added value of the AFM inside the SEM is a precise localization of the region of interest, because you can use the electron microscope to navigate your AFM tip exactly to the position where you want to perform AFM analysis. Because you know, normally if you have AFM outside your electron microscope, you never can achieve such a resolution of imaging. So the navigation is extremely difficult. So on this video, you might see how we navigate the AFM tip to specific nanowire, and then, for example, in this case, we maintain the mechanical testing and mechanical analysis of such a protein nanowires. I will show you another example in this topic. We have a tungsten diselenide flake, which are lying on silicon nanopillars. So normally this is how the sample looks like. So you can see some flakes, and to be honest, it's not that straightforward and simple to find the exactly nice flake of graphene which you want to analyze. This is why I use the SEM. We select the graphene which you want, and then you come with the tip. You can perform the analysis together. You can make the measurements, the analysis of the height, and by the end of the day, you can combine both informations together. So you have a 3D topography from the AFM, and you put the color mask representing the signals from the electron microscope, and here you see individual layers of tungsten diselenide, now how they are lying and following the nanopillars. And the shape in this case for the application is extremely important, and this is why it's needed to have both these combined informations together. What we are bringing to electron microscopy community with our AFM is not just the topography. So we can measure, analyze variety of material mechanic properties like topography I just mentioned, but you can measure surface roughness, elasticity properties, or the hardness using the different modes. You can analyze electrical properties of your sample, inside your SEM. So you can measure conductivity map using conductive AFM, or you can measure local surface potential using KPFM technique. You can also perform analysis of magnetic properties inside your SEM using MFM, or analyzing piezoelectric domain imaging using PFM technique. So all of these we are bringing inside the electron microscope and then enable to analyze all of these properties. I just want to show you once more the performance and high resolution capabilities of high resolution of AFM. So this is an example of silicon carbide when the height of the step is 0.75 nanometers, and this is how we are able to analyze in our AFM with the error of in the range of 50 picometers, and this is the surface roughness which you can measure. And also, if you look at the real sample, so this is a coccolite sample, how we are able to analyze and measure the topography and also in X and Y direction structures. So this is quite high performance and in order to analyze the things in the nanoscale. So now I will talk about the correlative microscopy, because this is one of points, a trend to combine techniques together. And this is what we do, right, with the AFM and the SEM. So traditionally, correlative microscopy is a technique when you analyze your sample by two different imaging modes, and then you try to combine the images. Traditionally, it's just the overlay. So I have some examples combining Raman together with SEM. So you have a SEM image, Raman image, independently acquired, and then people try to overlay and connect it together. Similar to the correlative light and electron microscopy, which is very well established in the life science community. So you have a SEM image, optical image from optical microscope, and then try to correlate things together. It's very powerful and step forward, but nevertheless, there are still several issues in this traditional approach, because it's extremely time consuming to use two different instruments and to deal mainly with to localize the same region of interest. There is a problem with the data correlation, etc. So what we have introduced is a technique CPEM, correlative probe and electron microscopy, which is based on completely different bases. And we utilize the advantage that we have an AFM probe together with electron beam in situ together. And then we start to scan with a sample, which means the probe and electron beam are in the constant offset. And then we just start to acquire simultaneously electron microscopy images and AFM images. So then if we want to compare, to correlate them, it's very straightforward. We just remove the offset because all the rest is done exactly on the same spot. So using the AFM, we take the very precise topography of your image. Then we just place on the top as a color mask the image from the electron microscope, the image from the electron microscope, and this is what we get: 3D image with the information from the electron microscopy, and then we can directly compare the differences between SEM and AFM. We can do more. We can do simultaneously acquire more data, more channels, which means we can correlate more properties together. Just to highlight the differences, this is what if you do AFM, and this is when you do the CPEM image of your, this is a silicon carbide sample with the graphene on it. So you see the graphene, and electron microscope will give you much more information than only the AFM. And so this is what we do. As I mentioned that we are able to collect several informations together. This is just the view how we do that. So we just take the channels from the electron microscope, connect it to our electron unit and the software. And as you can see on this video, we can simultaneously acquire AFM topography, signals from secondary electron, backscattered electron. We can get local elasticity, and all of them is acquired simultaneously from the same place. So then the correlation is really straightforward. And so this is the approach which we push, because this is a true correlative imaging technique, and even more it's in situ. So we have several application areas. Mainly it's a material science. When I was showing some 2D material examples, steel, alloys, batteries, ceramic, etc. different nanostructures when you are using focus ion beam, or if you have a TEM lamellas, and if you want to know the surface roughness or electrical properties on your TEM lamellas, this is the way what you can do. We can use it for a different semiconductor or life science application. I will just show you a few examples. One of them is from the battery research, which we did together with BASF. And so we were analyzing the
Dr. Newman.
Yes.
Please try to wrap it up because already 20 minutes over.
Oh, 20 minutes is over. Okay, so we are able to simultaneously analyze SEM, AFM, and conductivity, correlate everything to the, put it to the EDX with the EDX map. We can do the similar with the 2D materials when fantastic results will reveal. You can have a topography. And so what I just wanted to show you that the compact AFM inside the SEM is powerful. You can use it for plenty of in-situ application. We have a CPAM technology for correlative imaging and for the wide range of application. Thank you very much for your questions. Please do not hesitate to ask now or contact us later, or our partner, Samar Instrument and Sanjay, and all of us will be happy to support you and help you with your application. Thank you very much.
Yeah. Thank you, Dr. Newman. So it was very interesting talk, especially the combination of SEM and AFM. It opens up many things, and so probably I feel that even choosing right area in SEM for AFM, that's a very great thing to do. AFM takes a lot of time to choose your right area, and that is through AFM scanning. It takes time. So I think we can allow a couple of questions here. So if you have many, then probably always you can contact Dr. Newman. So is there any question here to ask for you? Okay, so I think Dr. Newman.
Yes, hello. Okay, for some reason I cannot hear you.
Leave your contact ID or anybody from your organization in the chat box. You with us?
Yeah, I didn't hear you for a while. Yeah, I will leave the contacts in the checkbox, and
yes,
definitely we will be happy to discuss on separate issue because I understand there is we are in lack of time. Thank you very much.
Okay, yeah, thank you. Thank you once again. So next speaker, I welcome Dr. Hugo Perez. He is a CTO from Dell Solution, and he is working in this organization for last 6 years. And he has many degrees in his name. So he has earned his doctorate degree from Delft University of Technology. He has MBA from Cambria, and then he has masters in nanotechnology and bioengineering. Sorry. So I think there is many to tell about him. So without wasting time, I should invite here Dr. Hugo Perez to take the stage. And please again to communicate that try to finish it within 25 minutes of the stipulated time given. So then we can have a few questions at the end to address if time permits.
Thank you very much. Can you see my screen and can you hear me?
Yes, please, very clear.
Perfect. Well, first of all, thank you very much for inviting me to be part of this forum. It's an absolute pleasure. So yeah, within my presentation, instead of fully focusing on all the different product lines that we have within Dell Solutions, I'd like to focus the talk much more into our environmental systems. Here you see a quick picture of the different product lines that we have, but as I mentioned, for the sake of this talk, we'll be focusing on our solutions for in-situ gas and in-situ liquid solutions. So let's kick it off with the stream system, which is a system for liquid TEM experiments. Now, if you have had some experience doing liquid phase microscopy, one of the things that you probably would know is that there are all sort of challenges that the community has been historically facing, right? To begin with, the unwanted effect of the electron beams. We know that the moment the electron beam hits the liquid, there's going to be a radiolysis process that will be triggered, leading to the formation of all sort of chemical radicals that will affect your sample, can affect the pH, and can also, for example, produce unwanted bubbles. If bubbles are forming in your liquid in your region of interest, it's also extremely difficult to get rid of them. And the border between the gas and the liquid, the surface tension there, could be also detrimental to your sample. So it's really tricky to deal with bubbles. The liquid thickness on its own is always a big headache for people, because we know that inside of your cell, there's going to be a liquid with a given pressure, but outside is vacuum. So unavoidably, the membranes, the electron transparent membranes, they will have the tendency to bulge, increasing your liquid thickness. And of course, the thicker your liquid layer is, the more difficult it will become to achieve high resolution in the imaging. You're not going to be able to do meaningful EELs, electron diffraction, EDS, namely because you will be above the threshold for beam broadening to start happening, right? So overall, the fluidic control that you can have within your cell is also critical, because you don't want to be relying purely on diffusion purposes. So it's going to be very important that you can really control, for example, mass transport, so that you can also control the kinetics of your reaction. So all of these things that historically they have led to a very low success rate for people trying to do experiments in liquid. And of course, things that affect your experimental flexibility, like cross-contamination and clogging, that at the end of the day also affect your reproducibility. So all these issues, we have now addressed them, and we can now solve them with our stream system. Now, the stream system is a plug and play concept, where you can see here the main components of the system as such. The system allows you to do liquid heating, for example, for life science applications. You can do liquid biasing for electrochemistry. So I will walk you through the different components, but let me start with the holder, because that plays a big role. So what you see here, this is not the stream system. This is our old liquid holder, which is referred to as the ocean. Now, the reason why I bring this up is because what you see here is this flower-shaped pocket structure, right? Where you see that there's a top and a bottom chip, and you see that there's an inlet and an outlet on this pocket structure. This is a concept that is commonly referred within the community as a bathtub design. Now, the problem with these bathtub designs, which is the concept that pretty much all systems out there are relying on, is the fact that when you introduce liquid, there will always be first a tendency to fill in this bathtub before the liquid goes inside of your chips. The reason is obvious. There's a much lower fluidic resistance for that to happen. So that means that only once the pocket is filled, then by diffusion, the liquid will start going inside until it reaches your sample or your region of interest. But that's diffusion. That means that you have no control whatsoever on the flow rate, on the pressure, on the direction of the flow. Here you see the nanoparticles there, for the most of it, bypassing your region of interest. So this leads to many of the issues that I was explaining before. Now, one thing that we have done to address all this is adjusting our architecture in the way that you see it now. So the first important thing to remember or to pay attention to is the fact that on our MEMS device, and this is a patent we've got, we have on-chip inlet and outlet, which are surrounded by this spacer. The spacer creates a well-defined microfluidic channel, and the top chip sits on the surface of these spacers to sort of provide the roof. So what we do is when we introduce a liquid via the inlet and outlet of the tip itself, aligned with the ones of the chip, we force the liquid to go from inlet to outlet via this region of interest. We can independently control the pressure at the inlet, independently control the pressure at the outlet, so we can control the absolute pressure over this fluidic channel and therefore gain this pressure-driven flow. But very importantly, not only we have the possibility to control the flow in that way, but if I refer back to the schematic, since we are controlling the absolute pressure of the liquid, then that means that we can control the bulging of the membranes, and therefore we can control the liquid thickness, which will play a huge role to enable high resolution images later on. So all in all, basically what we have is a system that looks like this. So we have the holder, where in the tip of the holder, that's where we place the nanocell, as we call it. The nanocell being directly aligned with the tip and with the inlet and the outlet, sorry, on the tip. If we have a closer look at the nanocell itself, which consists as well on two chips, on the top chip, you will see that we have a groove where we place an O-ring for safety purposes to make sure that there's no leakage into your column. And on the bottom chip, that's where we have the inlet, the outlet, surrounded by the spacers. That chip is the one that contains either the electrodes to perform liquid biasing experiments or the microheater for liquid heating. We can independently control, once again, the pressure at the inlet and the pressure at the outlet, leading to this absolute pressure control for a pressure-driven flow, which in real life looks like this. Now, what you will see is that we can go from static conditions to dynamic flows. We can go from very low flow rates to very fast flow rates, but you can see that we have complete control on the fluidics inside of your cell. So we have a very high accuracy in the level of control. And that means that we can also control mass transport, which means that we can control the kinetics of your reaction. So this is a very unique capability that only our system can offer. And basically what we can also do with it, thanks to the level of control that we have, is we can also, for example, purge the liquid by introducing bubbles made of inert gas. So the interesting thing here is that if you do this, you can further help yourself, aside of the control that we have on the bulging of the membranes. You can start purging with inert gases in case you have an air-sensitive electrolyte, for example, to go to even thinner liquid layers so that you can achieve even higher resolutions. And sometimes, of course, there's the unwanted bubbles, the ones formed, for example, by hydrolysis processes. And even if that happens, because of the flow control, we can flush the bubbles away so that you don't have to deal with them. Or as I will show you later on, we can also dissolve them. So if we focus a bit more on the flow control, I was mentioning that what we can do is to control mass transport. And that's exactly what you will see here, where we do some cyclic voltammetry experiments, right? So you see the CV curve, and you will see that the moment we start playing with the flow, increasing it, decreasing it, you will immediately see the effect on the CV curve. I will just fast forward a little bit, and you will see that depending on the change in flow that you have, you will immediately induce an effect on the CV curve because of the mass transport effects that we are controlling during your experiment. Now, another nice thing about the system itself is that it has a modular design, which means that you can disassemble the holder whenever you want. That helps you to replace the inner tubing to prevent cross-contamination, prevent clogging. The tip itself, you can put it in a sonicator so you can do thorough washing. So this modularity will help you not only to ensure that you will always have clean experiments, but the fact that you can exchange the tip means that you can, for example, think of having spare tips for dedicated experiments, or it will give you the possibility to do upgrades later on. So continuing with this control, the benefits of the liquid flow control. So one typical thing that people are interested in is in knowing how fast is my liquid going to reach the nanocell. Now, in our case, we can do this very quickly. So you will see here, I'll fast forward. You will see the change in contrast. There you go. So that's the moment when the liquid comes in, and you can see there it's happening at around 30 something seconds. And that's something that is very reproducible. So here you will see a different experiment when once again, you will see that at around, again, 30 seconds, that's when the liquid comes in. So we have a system that is very reproducible, that in typically 30 seconds or faster, your liquid will be there. And then you can start fully controlling all the parameters during your experiment, right? Now, another nice thing about this flow control is, for example, to reduce the beam effects. We were mentioning that one thing that happens is that the moment the beam hits the liquid, you will have this beam-induced deposition, for example. So this is what you will see in this video. Here we flow copper sulfate, so there's a lot of copper ions. The flow is on, but you will see that the moment we switch off the flow, there will be an excess of copper ions, and it will immediately induce the deposition of some particles, as you will see. You see it's immediate. And the moment we switch on the flow, you will see that we can start flushing it away. So this shows you once again the control that we have of the flow directly on the window. So I'll fast forward so you can see that this is also quite reproducible. So flow is on. The moment we switch off the flow, again, the particle deposition happens. And the moment we switch it on, we can flush it away. So again, this helps you to make sure that you can avoid these beam-induced deposition problems, that you can keep your solution fresh, so same concentration, so that you can have a quick reset of your starting conditions, let's say. Now, the other nice thing that the system allows you to do is not only we can control the flow, but we can control the pressure, right? Earlier I was showing you that you can flush bubbles away if they happen, but the other thing that we can do is to dissolve the bubbles. And this is a very unique capability as well, because you might be scared of increasing the flow rate if you want to flush away a bubble, because you might end up flushing away your own sample. So if that's your fear, what you can do is to play with the pressure. We know that liquid is incompressible, but gas is compressible. So if we follow the ideal gas law, you would know that by increasing the pressure, you would decrease the volume of your bubble. And that's exactly what we can do. So here's an experiment to show that. Here's a different one to show that it is quite reproducible, where by increasing the pressure, we can start decreasing the volume of the bubble until it completely goes away. So again, this will help you in increasing the success rate. So there's all sort of benefits that you can start seeing with that, right? So the first one, of course, is if you start controlling your liquid to that extent, not only the flow, but also the liquid thickness, since we can control the bulging of the membranes or effectively purge the liquid, one of the things that you can do is enable high resolution imaging. So here what you see is a copper dendrite that we electrochemically grew. And you can see that we could nicely see the fringes. So for a resolution of 2.1 angstroms in liquid, there's a liquid thickness of around 100 nanometers. And of course, with these kind of liquid layers, you will always be below the beam broadening threshold. And that means that you can do meaningful analytical TM studies. So here you see EDS for the same sample. You see the copper signal of the dendrite, the platinum of the electrode. By now we have different materials that we can offer regarding the electrodes for electrochemistry. We can offer platinum, titanium nitride, classic carbon. We can do meaningful yields, which is also something that you would typically want to do. And of course, we can do meaningful electron diffraction in liquid, right? So with this, hopefully it'll give you a good idea of the type of capabilities that the system offers. So this is a quick example just to show you a bit of everything, right? So what you see here is this is the electrode. We start introducing copper sulfate once again. So pay attention to this. We first go or flow it with a very high flow rate. So there's a lot of copper ions. Therefore, you go into this electroplating mode. And the moment we go to a low flow rate, you start limiting the amount of copper ions. So you limit the mass transport, and that means that you go into a dendrite growth mode. So this is a nice example that shows the effects of controlling mass transport on the morphological changes that you see there. And if we go from negative to positive potential, you see that it becomes immediately reversible, showing you the reproducibility, the stability of the system, et cetera, et cetera. So with this, I will move now to our other environmental system, which is the climate system for gas experiments, where much as the previous one, well, the holder is pretty much the same. Everything is digitally controlled. But then, of course, we have this big guy over here, which is our gas supply system. Now, what you see here is in the bottom box, that's where you can put your gas bottles. Inside, we have some mass flow controllers and a mixing valve. So digitally, you can define the gas composition that you want. And that is something that you will be able to change on the go, on the fly, live mixing. That's something unique to our system. The gas composition that you've decided will travel through a tubing that is inside of this arm, reaching this little box where there are some pressure flow controllers to bring it as close as possible to your holder, right? Everything can be connected to a mass spectrometer. So the first thing here is, again, to highlight this unique capability that our system has for real-time gas mixing. So what you see here, it's a catalytic nanoparticle where, of course, if you're doing catalysis, you really want to make sure that you really understand what are the effects of changing the gas conditions, namely the gas composition, for your catalytic performance, right? So that's exactly what you can do with our system. So here you see an example where the catalytic nanoparticle is in reducing environment. At any point in time, you can change it to oxidizing environment. You see the effects in the morphology. And whenever you want, you change it back to reducing environment so that you can really understand the performance level of your particle, right? When changing from one gas to the other one, in our system, it's just a matter of a few seconds before the new gas comes in. And few seconds, I mean, typically in the worst case scenario, it goes up to 15 seconds, 1.5. So it's usually faster than that. And here you see for that same example that one of the things that you can do is in situ electron diffraction, which is comparable to doing in situ XRD, but on a single particle level, right? Now, the system as such allows you to work in two types of modes, let's say. The benchtop setup, where in the box of our gas supply system, there's a tube where you can insert the holder disconnected to a turbomolecular pump that mimics the vacuum performance of your TM. So then with our software, you can start defining your experimental profile, all the conditions that you want to have. You can monitor everything. And once you have defined that, then you can bring it into your TEM, press play, and then automate your experiment, right? Of course, regardless of the fact that we are introducing high pressures, we have a fantastic performance when it comes to resolution. So here you see the TM performance, where you can see 55 picometers in resolution. Here's STEM performance. Keep in mind that we are the only system out there in the market that can go to pressures as high as 2 bar. And then the other nice thing that the system allows you is to start doing all sort of correlative studies, right? So not only you will be able to see morphological changes, of course, but you can link this to product analysis. As I mentioned, you can hook up the system to a mass spec, so you can really monitor what is happening with partial pressures of the gases that you have in there as compared to the morphological changes. But what's even more unique is also the possibility to do real calorimetry, nanocalorimetry. Now, this is a very unique thing to our system as well, because our MEMS device has been designed in such way that we have a really, really small thermal mass, the smallest thermal mass that you can find out there. So that means that with such a small thermal mass, in combination with the unique design that we have, where we have these 4 contacts to do 4-point proof measurement, we create a closed loop feedback system. So we make sure that whenever there's any tiny change in temperature dissipation, we can immediately monitor that little change and start doing colorimetry. So you can really figure out if you're having exothermic or endothermic reactions, right? And that's something that you can see in this example, where we use palladium nanoparticles to perform the oxidation of methane. And you can see that you can start nicely correlating the partial pressure, in this case of CO2, with the temperature, the heating power, so that you can really be absolutely on top of everything. And this calorimetry capability, as I said, is something very unique to our system, with that level of sensitivity, which is crucial. Now, aside of the fact that you might be interested in going to extreme conditions, like 2 bar pressure, we have people that bring it up to even 1200 degrees in temperature. The performance, the lifetime performance, the EELS performance is really good. It's really high. Here you see an example of molybdenum oxide carbonization process, where the example ran for about 18 hours. We never saw any problem with the nanoreactor. It never broke. Nothing happened. You see here the performance of EELS. Regardless that we're going to such high conditions in terms of pressure, for example, and temperature, the EDS performance is also great. We can go well above 900 degrees when doing EDS, precisely, once again, because we have an extremely small thermal mass. That means that the amount of photons that are emitted during the thermal radiation will be much lower as compared to other systems out there. And that means that the EDS detector gets saturated with our system at a higher temperature. Of course, in order to achieve high resolution EDS, it's important to have very high stability in terms of gas flow and thermal stability, and that's precisely what our system is capable of doing. And once again, one very important thing about the calorimetry capability is for time delay calibration. Now, what you see here is something that is intrinsic to every single system that is out there when you do gas experiments, which is you will always suffer a delay from the gas going from your gas supply system all the way to the reactor, from the reactor to the mass spec. And ideally, you would like to avoid this kind of offsets, this time delay, right? So that's where the importance of achieving proper synchronization comes into play if you really want to properly correlate things, right? But in our case, with our nanoreactors, since we have this capability to do nanocalorimetry, well, we can basically judge any change that happens there because we can measure the heat transfers. So with the calorimetry, in combination with our software, we basically give you the opportunity to calibrate for that time delay. So as you can see, this starts opening a lot of possibilities in your correlative studies, because as I mentioned, you will be able to correlate morphological changes with calorimetry data, with product analysis, all while you are changing at any point in time the gas composition, the gas conditions. And on top of all this, we can also offer the possibility to introduce vapor, right? Now, this is something also very unique in the sense that the vaporizer is an add-on that you insert at the very last stage of the gas supply system. So in this little box where I mentioned, we have the pressure and flow controllers. So the vaporizer allows you to control humidity from 0 to 100. But the important thing here is that you can control that humidity in a completely independent way from gas pressure, temperature, and flow. You don't have to there's no trade-off between these variables. You can be completely independent, and that's a very unique thing. The other thing is that because the vapor is introduced at the very last stage, there's no risk of contaminating the lines, because the water vapor will never see all the lines in between. And that means that you can avoid all these lengthy baking and cleaning processes. Keeping it, yes.
Yeah, sorry for interruption. Just try to wrap it up in 5 minutes.
Yeah. I just have 2 more slides actually. And also because of the very low volumes that we're dealing with, very low gas volumes, you can safely deal with explosive mixtures. So once again, we have some customers that are going for explosive mixtures. They go to these very high pressures, up to 2 bar. They go over 1,000 degrees. And you can completely work in a safe condition. So this ends up increasing your application space, right? So to finalize it, I will just show you a particular example that I really like from the results that some of our customers have done with this system, which is doing basically obtaining the morphological changes or creating a 3D reconstruction as a function of gas environments. So basically what has been done is, they can start analyzing a nanoparticle. And as you change the gas conditions, you can really figure out on a 3D way what have been the consequences of these environmental changes on your particle. So that you can really start having much more understanding of the behavior of the particle as such. And really start correlating in a deeper way all these things. So with this, I would like to finalize, not before thanking you, of course, for your attention. And of course, in India, for any queries, please feel free to contact my colleague Sanjay of Samar Instruments. He will be the right person for you to approach there. So thank you very much. And of course, any question, I'll be happy to answer.
Yeah. Thank you, Dr. Hoover. So it was really very fascinating to see, this kind of holder. And I see that one example where we have shown that 2 bar pressure of methane and hydrogen. So that's really, interesting to see. And so we probably, there is no question in the question and answer box. So probably.
Hello?
We type arguments at the end. We can, you can have anybody having any question. You can directly, I think, yes, contact, everybody's contact of him, or you can just put there in the chat box also. You can directly contact. Okay. So I'm sorry because next session, by this time this session will be ending. Next session will start at the same time. There is no break. That's the reason I'm telling. Okay. So sorry. So I welcome the next speaker, Dr. Kim Curry. So Dr. Kim Curry is an application scientist in Hummingbird Scientific, and he has received his PhD degree from University of Maryland. And his research interests include the materials for energy application and development of in-situ TM tools and techniques for the material research. So I welcome Dr. Kim Curry to for this presentation. Please, I think we need to finish it in half an hour time. So at the same time, the next session will start, and if you can finish early, we can try to accommodate a couple of questions. So please go ahead, Dr. Kim Curry. I can see your slide. Yeah, it's all right. Hello. Actually, there is
you are muted.
Can you hear me all right now?
Yeah.
Okay, great. Okay, thanks for inviting, and thanks everyone for joining. It's a little early here in the West Coast of the United States, so I might feel a little sleepy, so please forgive me. So in this presentation, what I'll do is I'll walk through some of our in-situ holders that we have developed over the years, and we are still working on with some of our customers and collaborators in the academia. Like I said, we are in the west coast of the United States, in Washington State, near Seattle. This is, we are running in the 16th year, and we specialize in different kinds of holders for TEM, SEM, and even extra systems. So apart from all the standard holders we have in the portfolio, we also like to collaborate with our customers, academic partners, and build all kind of new in-situ holders. So that's where we specialize in. We do everything in-house, from designing to manufacturing, to even we have our own microfab division. So everything is done in-house. And we also have our own TEM lab. We have Joule microscope. We do all the holder testing here. We do demos, and we also work in some projects with our customers. And in next month, we are also getting another TEM. So we'll have at least 2 TEMs in our facility for that purpose. Our holders are almost all around the world, different kinds of holders, most institutions. Since this seminar, this symposium is focused on in-situ, I'd like to show this slide from Peter Crozier from Arizona State. This is a beautiful slide where it shows what in-situ really means, what Faranga really means, and this will give you an overview of what can be done inside the TEM. In most cases, in generally, people what do they do is they make a sample and image in TEM and do structure analysis. But apart from that, there are several things you can do. You can apply stimulus, you can bias your sample, you can even shine light, you can heat your samples, and you can even create environmental condition, for example, flowing liquids and gas into the system and looking into more operandi situation. So this is where we come, and we try to build all kinds of in-situ holders for anything you can think of inside the TEM. And we have portfolio of holders for various in-situ purposes for different stimuli. We have environmental holders, we have heating, cooling, magnetizing, even air-free transfer holders. And we have done this not only in TEM, we also work with our ACM customers and extra customers and build holders, in-situ holders for them. So in this talk, what I'll do is I will take electrochemistry as an application example and show how different holders can work uniquely to create a comprehensive data set in the end. So in the series of these holders, the first I would like to discuss is this biasing manipulator holder. So this holder is useful, especially when you are looking from the building block level, from nanostructure level, individual nanostructure level. For example, if you want to see some nanoparticles or nanowires in action, or you want to characterize them, you want to manipulate them, you want to do some mechanical, electrical testing. So this is the holder that you would want. And as you can see in the screen, it has this pointed probe. It's a mobile probe. It can go in all 3 directions, X, Y, and Z. You can control both in coarse motion and force in fine motion. And the unique thing about this system is when you bring this probe, you can have this, well, you might not see it very carefully, but this is a half-cut TEM grid. And you can have your sample here, and you can bring in this probe and make a contact with your sample inside the TEM and do all kinds of characterization, electrical characterization, mechanical and things like that. So here you'll see how this probe is approached. You have this mobile probe, and you have this sample on the other end, and you can take this mobile probe both in coarse motion, of course, and also when you are almost into the point where you are making a contact, you can do very precise fine motion. And when you make this contact, the system is so stable that you can even you see fringes from your probe. So this is the probe, and you see fringes, and this is the sample. So this is when your probe is making a contact with your sample. As for the example, I had promised that I would provide example of electrochemistry. One of the, I guess, the most common example of using this holder is studying batteries. People like to create nano batteries inside the TEM and look at individual electrode materials that are used in batteries and see how these materials react and how a structure changes or how chemical changes in real time. So here is an example where you see you have a lithium probe. The lithium can be attached to this probe, and you have nanowires and nanoparticles on the other end, and you bring in contact and you apply some kind of bias and drive lithium. For example, in this case, this is lithium battery. So you drive lithium ion into the system. For example, this is the particle here. You drive lithium, and this particle will increase in size and decrease as you lithiate and delithiate. So these are some of the things that you can see in real time. And the next in the series is the biasing holder. Biasing holder is useful when you are talking about from the device level, not the individual structure, but you build devices. And also you can use the biasing holder to heat or sample, depending on what stimulus you want to apply. As you can see here, this is an example where you have high resolution image of two particles. When you heat, will coalesce, and I'd like to go a little fast here into coalesce, and you can see that in real time at high resolution, and when you can hit it. In terms of electrochemistry, what you can do is, in this case, you have you can build a device and make contact with. You can do either wire bonding or things like that. And here is an example where you can see graphene in action when you intercalate this graphene with lithium. So you're basically intercalating the system with lithium, and you can see the folding of graphene layers, which means there is some kind of intercalation going on into the system. And in the series, we also have this holder called tomography holder. This is useful in the case where you want not only see things, but also you want to analyze your sample in 3D. So what you can do is you can have your sample that you just perform an in-situ experiment with, for example, in the grid, and you can take a series of 2D images at different angles and tilt series, and you can collect these 2D images and later on reconstruct into 3D images like shown here, right? You can take 2D images here and reconstruct into 3D images. And this allows you to not only look at the morphology point of view, but you can also see all kinds of other structural part of the sample. For example, if you are into the fuel cells, you want to see how the porosity of your sample would look like and things like that. And this can be done with varieties of tip. We have from pointed tip to tip that can attach grid to even chips. And people in the battery community have been particularly interested, for example, I said fuel cells, because they also are interested in looking at the porosity of their samples, and they want to see it from all 3D and part. So you can take 2D images of these particles and reconstruct them into 3D images and evaluate your sample itself. So this can be done postmortem. And this can be done with the in-situ samples when they are performed. And this is another holder, what we call year-free transfer holder. This is useful, especially when you are studying batteries and any year-sensitive samples. Some of the samples are so year-sensitive, you have to be careful when you transfer from inert environment to the TEM. For example, if you have, for example, battery samples, which are very highly oxidizing in the atmosphere, you want to be able to get that sample from the glow box, inert environment glow box, and into some system and take into the TEM without exposing in the air. So this holder does that. So as you can see from here, this could be TEM grid base, or you can have chips on it, and you can load your sample inside the glow box, and you enclose this tip. And you can create a vacuum around the tip, or you can have inert environment around the tip, whatever you want. And then you can take this holder into the TEM, insert it, and then open this tip, open this shutter, and then you can have your sample in the beam. So if you have a MEMS system, for example, if you have a chip, you can even bias the sample once the sample is transferred. So you can do in-situ analysis also. For example, if you have battery samples, you can run battery cycling. This is an example where it shows what happens when you transfer samples that are sensitive to air and moisture. So this is when you do a transfer properly with a year-free transfer holder, and this is when the same sample is transferred without using proper transfer holder. A simple, a standard holder. As you can see, there are lots of degradation around the sample, and in this case, no degradation or no oxidation. oxidations. And one of the things, if you are interested in, for example, batteries or even quantum science, is you want to have your sample that can go to cryogenic temperatures. Batteries, in the sense that people are interested in saying, if you can cycle batteries at cold temperature and warm temperature, and you want to be able to see batteries cycling at various temperatures. So this is so we have this cryo biasing holder where you can not only cool your sample to liquid nitrogen temperature, you can also bias the sample at that temperature and take images. So here is beautiful lattice images at -167 degrees, almost to liquid nitrogen temperature. And here's an example of a device at that temperature. As you can see here, you can make these devices. In this case, it's a nanowire device. It's a battery nanowire with different components here, from cathode to anode to, you have all kinds of electrolytes. So you basically bias through the sample, and you can, for example, you can see dendrites growing in real time. And dendrites are very difficult to image in the beam. So what you can do is, once you grow dendrites in situ, you can cool the sample to liquid nitrogen temperature and get high resolution image of dendrites itself, which are, in normal sense, would be very highly beam sensitive. So these are some of the things you can do with the cryobiasing. I did not show the example of quantum science here because I'm mostly related to electrochemistry, but you can also look into quantum science with this holder. And we also have this holder, a liquid holder, gas holder, which normally would fall in the environmental system. This is more on the operandi system, where you flow liquid and gas into the TEM chamber in real time and analyze your sample. And I'd like to especially focus on the electrochemistry part, because what we have been doing is doing electrochemistry in TEM is tricky, because traditional electrochemistry, first of all, the traditional electrochemistry have hard time believing anything that happens in TEM, especially with electrochemistry. So in order to convince them that this is realistic and then happen in the dark environment, like they make a cell outside, you have to be able to quantify what you observe in TEM is a representative of what you would see in a dark environment in a cell, in a traditional cell. So what we have done is we have been trying to be more quantitative on the liquid cellular chemistry part of the TEM, and we have tried to incorporate, not only rely on chip-based electrode system for electrochemistry, but also have realistic, for example, reference electrodes that industry people would use. And the intent is to have a stable reference electrode, and that will not change over the course of reactions when you perform at least more cycles. Maybe you will be fine for a couple of cycles, but once you start doing 4 or 5 cycles, your reference electrode will start to change, your inherent electrode potential will start to change, and your quantitative data will not be represented. It will basically become more pseudo. So this is, and we have built this new system where you can incorporate actual reference electrodes and be more quantitative on the electrochemistry side of it. Here is an example of a simple copper deposition experiment, which is pretty standard. As you can see here, when you are in the reduction peak, you will see copper deposition. Once you're in the oxidation peak, that copper is gone. And you can repeat that for many cycles, and they perfectly align with what you would expect in a dark environment of the cell. Not only that, we also have this holder where with the same liquid cell system, but you can shine light onto it. So we call it optical liquid system. So you can not only do electrochemistry, you can also do photoelectrochemistry inside the TE. As I said, we are not only focused on TM, we also do lots of X-ray microscopy. And here is an example where you can build the same system, electrochemical system, in any X-ray system in the world. We build custom systems. So, if you are interested in this area, let us know. And here's an example done by Stanford group where they look at individual battery particles. In this case, it's lithium iron phosphate, and they observe what happens when lithium is intercalated into the battery material and deintercalated from the system, and try to build a map around it and see, how different particles, size dependent reactions and things like that. With that, I think I may have finished my time also. So if you have any questions, so these are some of the holders I presented here, but there are other holders that we have and are in making. And if you have any other ideas, thoughts, please contact me and we can discuss and potentially collaborate and make this institute holder happen and make possible. With that, to take questions.
Sure, yeah. Thank you, Dr. Kim. So it was a very good presentation.
Thanks.
So I have a small question, Kim.
Mm-hmm.
In your liquid cell, hello, Amit?
Yeah, please go ahead. Yeah, I can hear you, but your sound is a bit low. Your voice is a bit low.
Okay, I'm now audible?
Yeah, it's better now.
Okay, so in your liquid cell holders, the reaction, right? You're showing some reaction. Hello, can you go back to the slide?
Okay.
Yeah. Okay. Yeah. So what actually will happen, just I saw the other presentation from Dense, okay? For the cyclic voltammetry study on case of copper sulfate. So if the copper basically deposits on the electrode, on the electrodes, okay, and it will make very strong electrical connector. Will it not make the holder giving wrong signals as far as deposition of copper is concerned?
You mean it will short the electrodes?
No, it will not short. It will, yeah, copper is highly conducting. Yeah. So how do you manage that?
Well, these electrodes are separated, right? They are not connected. And deposition only happens on one electrode. So that's also the input key part. You don't want your deposition happening everywhere, right? So you want, when this happens, for example, in this case, let me stop here. So in this case, when you have this electrode in the reduction case, then you have copper deposition on the working electrode, for example, right? So there is a deposition back and forth between working and counter. There are two electrodes, and when you have deposition on one electrode, there is stripping happening on the other electrode. So it's a simultaneous process, right? So when the copper is stripped from this electrode, you will have deposition happening on the other electrode. So it's a simultaneous electrochemical process, and you want that to happen in a very cleaner way. You don't want some residue left in one electrode, because for example, if you are in this oxidation peak, you want everything gone. You don't want anything left here.
Yeah.
So that's the cleaner system.
So
is that
in case of
did I answer the question?
In case of electrolytes which has ions difficult to reduce, okay, this thing might be okay, but in case of ions which are easy to reduce, there will be always a problem of deposition happening on one of the electrodes, right? You cannot avoid it. You are going to have it as you apply the voltage,
right?
So this variation will how can it be controlled in a one device? Suppose you have copper, then you have iron, or then you can have zinc, different kinds of reduction abilities. So this will vary, right? So how it will be?
It will vary because things that are in bulk will not translate into these nanosystems, right? So you cannot, have exact condition in the bulk, and so there is some kind of optimization going on, because as you can see here, the copper deposition is very thinner, right? It's not making a film or anything like that, because we have a lower concentration of copper, for example, right? So optimization would come into place when you are doing TEM, when you are trying to make a product or something. So, but I guess the point I was trying to make here is making something is good, but you also want to be able to relate that what you are doing, right? For example, if you are depositing copper, what does that mean? That at what point that deposition is happening, and at what point you are stripping it, right? So I guess in short, you would have to optimize it based on your experiment.
Okay, thank you.
Yeah.
Okay, so is there any more question? Okay, I think there is no more question, so we can wrap up this session. And thank you.
Amit, his voice is discontinuous.
Dr. Tikati, and thanks all the speakers here for giving. Hello.
Yeah, go ahead. Your voice was discontinuous. That's what I said. Hello.
Am I audible?
Yeah, go ahead, Amit.
Yeah. So thanks all the speakers, and it was a very good session. As I think before this session, post that session, that I think Dr. Chandrasekhar, Professor Chandrasekhar, he was saying that the instrumentation is an integral part of In-situ. And this field is really, it's not matured enough, and so there are a lot of activity and lot of different thinking from different directions. We can see that as well as we saw some application of artificial intelligence. That is one of the really good sector when everybody is every sector it is happening. Then why not for In-situ microscopy, especially we know that there are a lot of challenges here. So thank you everyone, thank you organizer, thank you Krishanu, and thank you Chandrasekhar. So you can have some closing remarks for this session.
Okay, thank you, Shiva and Amit, for nicely managing the time. And because this was a very unique session in which the industry personnel have to, showcase their products and explain the results. So I think we have probably have done that nicely. So thanks again to both of you. And so this session is closed now, and we have hardly 2 to 3 minutes left for the next session. So I invite Professor Ravi Shankar to. I think he's in the dais, right? Professor Ravi Shankar, you are.
Yes, I'm here, Krishanu.
Yeah. So you can come on camera also if you want. And,
okay, sure.
Yes. So Professor Ravi Shankar needs no introduction. He is one of those electron microscopists who has been using in-situ microscopy for long. And actually he had several holders in the microscopic facility. He is in charge of the advanced facility for microscopy and microanalysis at Institute of Science. And he has been the member and the different positions of Electron Microscopy Society of India. So he will take care of the last session. We have 4 speakers, and I think 2 have already joined. Sairam is joining, and I am in touch with Thomas. So he has some meeting. He will join soon. So we can start, Ravi, now.
Okay, thanks very much, Krishanu. And first of all, my thanks to the organizers, Krishanu and Chandrasekhar Tiwari, for putting together this really, really wonderful symposium. I've really thoroughly enjoyed it. I've been around throughout for all these sessions. It's been really enjoyable. The panel discussion, everything, all the speakers, everything was enjoyable and very well organized. Thank you once again. So it gives me great pleasure to chair this last technical session of this symposium. And 4 outstanding young researchers will be presenting their work. We'll start off with Dr. Ashutosh Rath. Ashutosh is a senior scientist at IIT Bhubaneswar. He got his PhD from IOP Bhubaneswar, and subsequently he was a postdoctoral researcher in Paul Weil's group at the University of Wisconsin, and then in the Stephen Paneco group at Singapore. Ashutosh has been a very prolific researcher, has over 40 publications to his credit, and has been doing lots of very nice in-situ work. Look forward to your talk, Ashutosh.
Thank you, sir, for the introduction. So is my slide visible?
Yes, it is visible, Ashutosh. You can hear you also.
Okay, that's great. Okay, so first of all, I would like to thank the organizers in the EMSI for these invitations. So, today I'll just talk about mostly the in-situ real-time study and about the diffusions at nanoscale. So before that, like some of the works, what I am going to show a little bit is from this ARM machines, the FEI sample preparations, and from USA, there's some FEI Titan with the FIB from JAS. And most of the in-situ heating experiments have been done at IOP. Even recently, I will show some results. It's going on still. This is from Institute of Physics Bhubaneswar, and we're using the ZOZM normal TM and FIB Neon 40 for sample preparations. And this is our new TM. It is still under installations. It's a field emission type HR pole piece. So hopefully it will be ready by within 2 months after this lockdown system. Okay, so outline of the talk. So we'll discuss, like, because this topic is basically on the diffusions. So we'll discuss what is surface interfaces, and then I'll emphasize on what are some examples, like why interface is very important. Then we'll discuss about the in-situ observations. Then I'll talk about what are the challenges in the sample preparations, and then we'll discuss some materials and results. Then I'll finally summarize. Okay, so whenever you talk about any devices, whether it is electronics, photonics, or spintronics, so every time we need materials and their combinations or the heterostructures, and they have a lot of interfaces. So the main challenges in the last 35 years or so, people are trying to enable the materials, and they use different type of characterizations, and from that our microscopy is very important to find out from an atomic scale, because we are talking about nanoscale devices, so we should control through in the atomic level. So now why the surface interface is very important. Yeah, so when you talk about thin solid film based devices, we have two interfaces basically. Film vacuum interface is called the surface, and there is a solid interfaces. So a lot of things happening in this one. Even if we have nowadays we have a lot of high end growth machines are there, so that we can grow very accurately. Still, there are a lot of parameters that affect the device performances, with the defects, roughness, strain, reconstructions, and the diffusions, all what I'm going to discuss today. So it's very important to understand and control the surface and interface to get the maximum benefits from the devices what we are planning for. So with this, basically, I'll emphasize mostly on the buried interfaces. Here particularly, I'll show some surface diffusions, but we'll also discuss on the interfaces. So to emphasize on how interface is very important, I'll just give two examples, then we'll go to the in-situ studies. So this is one of the Heusler's on gallium arsenide interfaces, heterostructures for spin valve applications. So this is basically how we have prepared using MB, which is a different type of initiation layer of manganese, silicon, gold, and manganese. And this is how it looks like. This is the spin injector, and we will detect the spin detection unit. This is the gallium arsenide channels we use. This is how it looks like the stem images. This is basically for this Heusler CO2 MNSI, it's called CMS. Basically, it's very important because it has a L12 crystal structures, L21 crystal structures. So it gives 100% spin polarizations theoretically. So this is what we grow the samples using MB. So we have a L21 crystal structure with some beautiful phases there, and we prepare very nicely all the parameters, the very clean surface interfaces also. But still, we are not able to get 100% spin polarizations. So what is the reason behind that? So for that, we study the stem atomic resolved yields mapping on this all these three interfaces, these samples, and what we found that for all these initiations layers, we always get a manganese silicon interfaces here. But what happened actually, because it's the ferromagnet and this is the channeling gas, this is the spin channel materials. What we found that there is some manganese diffused from to the gallium arsenide. So this is very traditional, old problem. People generally report this manganese going into the gallium arsenide. But what we found, because we are able to calculate the exact atomic positions by combining the stem images, yields mapping, and the Trojan funnel lattice simulations, atomic simulations. So what we found is not only the manganese, there is also the out diffusion of arsenic from the gallium arsenide. So when there is both is happening, manganese in diffusion, arsenic out diffusions, what happened? So even the layers are good, everything is epitaxial. Only two atomic layers can see here actually there is only 2 atomic layers have a manganese arsenic like structures formed. So it's basically a antiferromagnetic structures that basically kills all these spin polarizations, and this is how it affects the device performance. The point here I want to emphasize that how the diffusions at the atomic scale and it affects the whole device performance even if everything is perfect. Another example, let's just quick example, that we try to grow using MB system, all our MB system. We grow the 3D ferromagnetic COFEB on 2D TMDs, all this MOSC2. So basically you clean the silicon carbide and we grow automatically graphene on it. If you do in the UHP chamber, you get a monolayer, 2 monolayer graphene here. And we make a very clean our clean interfaces. So what we found that because of this hybrid interfaces, there is a reorientation of spin and we are getting a perpendicular magnetic anisotropy. And the very important point about is very important for the MRAMs. And the important part is this interfacial ferromagnetic this PMA, this perpendicular magnetic anisotropy basically depends and we can enhance or tune it with the ratio, with the COFE ratio and the thickness of the COFEB. What we found from yields scan, there is some diffusion of boron there. So because of this diffusions and there is some variations in the compositions, this also affects this property, which also affect the devices at MRAMs. So this is basically all 2 examples where I want to emphasize that how diffusions, particularly the interface diffusions, are very important. Now let's go to the in-situ observations. So we always talk about like imaging, whether it's a diffraction or as a hard of stem imaging, everything. So when you talk about these dynamic studies at the interfaces, particularly metal semiconductor, so there are several questions are there, even the kinetic questions are there, is still not answered. So here basically I'll mostly focus on the in-situ microscope thermal effects. So in addition to this, what will happen? So what are the extra information we can get if you incorporate the time? So we have a space, we can image the system, but what happens if you incorporate the time? So both space time should be there in the system, so that what extra information you can get. So now come to the types of in-situ experiments. It's already discussed by several speakers. So the dynamical changes happens by changing temperature, whether it's a low temperature or the high temperatures, or some stress or instability of materials, or depending on the beam and on the environment, depending on the electrochemical experiments or in some gas environment like that. And when we talk about the E-beam radiations, I'll show some carbon nanotubes on this one. So even if it's so straightforward because we are using the same beam for imaging and modifying the specimen, but still it's very difficult to say whether it is a problem with the affected by E-beam only or there's some temperatures. Okay. So now come to the main point. Like if it is a liquid samples or nanoparticle by white chemical, then this light is very cool. But when it is a thin film or bulk samples, then it's very difficult. Like particularly for the in-situ microscopy studies, there are several challenges in sample preparations. So we basically use the conventional method nowadays, and the FIB is very popular nowadays. So we prepare this cross section, particularly for the interfacial samples. We prepare this cross section samples using glue. So I don't know exactly now what is happening because I am nowadays preparing mostly using FIB. But epoxy creates a lot of problem for the stability of these in-situ experiments. And so similarly, we can do conventional method. We can do also FIB. People do wet polishing, this waste polishing also. So for conventionally also we can prepare planar sample using FIB. So I have to make a protocol using FIB, so we can prepare also planar samples. But yeah, the epoxy basically affect this type of in-situ study, in particular in the cross-section mode. So that's I told. So there are several factors also there: contaminations, amorphizations, roughnesses, topographical variations, and implantations. But anyway, FIB is very good. I just give an example from our clinical groups who have done some octahedral studies on these interfaces. You can see prepared very nice lamella. You can see very nicely all these ABF and RF images. So we can go up to below 20 nanometer. We can prepare the FIB samples, lamella. So that's very great about the FIB. So that basically we use. We can do even for. I'll come to that. So this is basically FIB is already discussed by several speakers on the FIB. So how it basically we use different current and low energy current, different currents for preparation of samples and lift out things. This is how it looks like through the In-situ detectors, how the transparency. So okay, this is already discussed. So and we use generally 5 kb or lower than 5 kb for polishing to avoid to clean the amorphizations and the gallium implantation. Some people use lower milling rate of argon also to clean the whole samples to make it fully electrotransparent clean. Now, so particular for, as I mentioned already, because in FIB it is very site specific and there is small volume preparations. So so there is less chance of contaminations because the contaminant cannot migrate more to the electrotransparent area. There is also a disadvantages. You can see this is a clean FIB samples. This disadvantage is that there is some amorphizations which can be tackled. Implantations little bit there. Like for germanium type materials, they will get a void because of the ion beam. This one, and there is a called cutting effect. You can see this is very is a common problem in FIB, and this is very like it's very important when you go for a mechanical in-situ studies, like particularly indentation and these things. So that's why it's very challenging actually when you go for this mechanical property studies, because these effects are always there. So you have to prepare a very nice protocol using FIB for your samples. So okay, so this is basically the holders we use, the furnace type holder, resistive heating type, we use for our in-situ studies. Mostly prepare conventional polishing and FIB electron method. Okay, so I just before I tell about this, how it's very important and challenging in the indentation, particularly for the materials. Pico indentation I'm just showing here. So this is just a pico indentation on the carbon irradiated silicon carbide. So this is very important silicon carbide for the also light water reactors. But when there is some irradiations, there is some swelling, and that basically generates stress, and there is a lot of microcracking. This basically release of fusion products. Happened, it's long back. So it's very important to do study by indenting on the microstructure and see the evolutions of microstructures with the indentations. So what is the important point is that, so this is a sample of carbon irradiated sample on silicon carbide. You can see this is the end of range where we can see that a lot of defects are formed. This is the little magnified images. You can see there are a lot of black spots, contrast are there of 175 nanometer. So the idea is like we want to indent exactly on the defects, and parallelly we should see at what distances this we are basically indenting the defects. That's basically it's very important for this type of studies. So for this, preparing a FIB sample is very challenging actually, because yours particularly this surface should be very flat so that there should not be any errors in indentations while you do the indent procedure. So yeah, this is basically as I mentioned, this is the challenges to get a geometry where we can image the microstructure at cross-sectional view and calculate the distance from silicon carbide surface and do the indentations. And FIB induced defect formations, this one is always there. And we should have a mechanical stability of the sample on the copper grid, what we are preparing for this basically FIB grid, and make sure that the indentation surface is flat. And the whole FIB protocol should be reproducible for this one, because it's very important, because we have to do a lot of indentation, and once we do indentation, the sample is gone. Okay, so this is basically where we have to put the sample, and this is the tip. It looks like in the low mag images. So this is how we prepare the samples. The good part is like in the FIB, what we do, this is the grid start, and what we prepare, this is the samples we prepare here, but we gradually decrease the thickness from here to here to here to this one. So that will give basically a mechanical support with the grid, so that when you do indent, there should not be any bending or other things, at least mechanical, because it is fixed with the platinum. So that is very important. This is the new, it's good protocol that you can prepare this gradual thickness decreasing from both sides, so that the experiment should be easy. So this is just to show like how it's very important for this type of in-situ pico introduction experiments. This is some preliminary results. Yeah, so this is some preliminary results we saw. Sorry, the video is not working, I think. Okay, I don't know why it is not going. Okay, this video is somehow not working. Okay, so if you do the indentation, so this is basically the images from indentation suite. So you can so this type of you can do this indentation like this on this clean flat surfaces. This is just the preliminary results that we are going just to show that how it's important for the samples to prepare the samples for particular in-situ experiments. Now come to some of my old works which I have done. I don't know why it is. Okay, so this is just some gold silicon system long back we have done in 2010-12. So this is to system having a gold and silicon without oxide, and it's a clean system is inside the MBU prepare, and this is the thermal evaporated system. And so we have to study like what is happening with annealing, what happened to the system of this thin film interfaces in the particular the surface, and to the high temperatures. And we use different orientation of silicon substrate 100 and 110 to see what are how it affects the structures. So this is basically how, so inside the TM, we heat the whole 2 nanometer vacuum structures, and with the temperatures, it changes the shape transformations. You can see that how it becomes, and we see the chart of this whole process. You see that 5-10 degrees Celsius, percent of having particle is almost 80%, and it is almost constant after that. And the whole sample becomes rectangular structures from this one. And we do also the in-situ diffractions with the temperatures. We also vary 300 this diffraction studies. And what we found that around the same 510 we are getting a gold silicon phase, and above that we are getting various phases of gold silicon up to 600 you can see. But this is the crucial 510 degrees Celsius because here we are getting a maximum percentage particle become convert to the say transform, and there is a compositional changes here. So why this in-situ experiment is very important? Based on this experiment, what we do, because now we know that if you want gold to use as a catalyst, for the germanium, like for epitaxial germanium grow. So what we do, we use these recipes and these informations to grow inside the UHB chamber the germanium nanostructures. I'm not showing the data, just I'm mentioning that what we found that after before 510 degree there is no formation of germanium nanowire, but when there is a 510 degrees Celsius, this structures act as a catalyst to grow epitaxial germanium nanostructures. And the good point is because before that this is pure gold. So basically the gold not as acting as a catalyst for the germanium growth, but as a gold silicon act as a catalyst for the growth. So the message is basically because of these in-situ experiments, we know now at what temperature my shape has changed of my gold and the gold silicon formation. So that recipe we use for the further studies of the germanium growth. Okay. Similarly for the oxides, we get the structures not that much great, but you can see the videos like sorry, it's not, yeah, you can see like how nanoparticle basically you can see there is several covalences of nanoparticles. You can see is the process is totally different actually. So even if this particle is, where is this particle is, the nearest particle is there, there are some nearest particles are there, but they're not going into the system. So they follow a different mechanism of forming this type of square structures. So this information you can get from this type of institute studies. Now come to another system of oxides on silicon 100. You can see when you heat it inside high vacuum, you see the whole substrates become like this. From this one, it's covered with the micro rods. You can see the in-situ real-time videos on this. That whole film becomes a micro rod. You can see how the micro rod forms, and this is the extracted frames from the images from the video. And this is basically, we propose the liquid solid growth mechanism, how the gold silicon layer form the liquid front, and there's the growth of this micro rods. And this is basically the whole rods is of AU7 SI phase, what we found is as published in 2009. So this is basically the importance of our real-time studies. Now come to the carbon nanotubes. It's already discussed some people. So this is basically a iron carbide filled carbon nanotubes. You can see this, both sides is a hollow one, and we do this this electron beam irradiations for a few minutes at 590 degrees Celsius. But we found that how there's a safe transformations on this one inside the carbon nanotubes. So if there is a cut in the carbon nanotubes, it's a vacuum actually. So with the same ion beam electron beam irradiations, it goes out from the tube and making a shape here. So that's why people use this E-beam for the cutting of carbon nanotubes. That's why how it works. And another is, this is the high, if you try to go to the high resolutions, see, we can see like, this is a 5-minute video, you can see like how the iron Fe3C is, has a mass transport is going on inside this one. You can see the videos and how this affect the carbon nanotube walls, and you will see that it will stuck here. So this is also very challenging experiments after several attempts. This is how it looks like from a, so you can see there's axial sliding rate of almost 1 angstrom per second. And we can see that this is here, it terminates. So here you can see this is the wall, it's terminating, and it contact with the side, the carbon nanotube wall, and here and here. So this is like some of the studies, and the whole process, this is not, it's in a metallic metal. So this is in a solid form basically. Okay, so this is one. It's all about what I have done long before. So this is now recently I'm working on the gold gallium arsenide system. So whatever I have shown is mostly the surface diffusions, but this is where I want to go study what happened to this system in the interfacial, because now we are able to prepare a 5E sample. So this is basically a 16 nanometer gold on gallium arsenide. You can see it looks like an SEM and a TM. And this is the normal as deposited system. This is a polycrystalline gold. And this is how the cross-sectional samples prepare. This is a platinum for the capping layer in a 5E. And this is how it looks cross-sectionally. And there is some oxide layers of 3 to 4 nanometer native oxide layers are there. How it looks, this is a high resolution one. So polycrystalline gold and gallium arsenide. And when you heat the system, the whole system at 475 degrees Celsius, the whole substrate, this is the substrate, whole substrate covers with the, you can see the micron size rods. So that's very on the gallium arsenide basically, and this oxide is there. So, and basically this is very reported reactions has happened. It's react with this one to form solid, and gallium arsenide goes out. So at this 475 degrees Celsius, and if you do selected a diffraction on the rod, single rod, you can see there is a liquid phase formation. You can see the diffuse ring. So it's on a liquid alloys formation, some gold gallium alloy forms. I'm not sure the compositions yet. Still work is going on. So what we do, just to check like what is there at the interface, because now we can see that surface is covered with a micro rod, like some surface diffusion is covered with a micro rod, but what is really happening at the interface? So that's basically the idea. And you can see this is the video. You can see like how when it's reached at the 475 degrees Celsius, now the whole interface, this interface is basically, there's some diffusions of gold into the gallium arsenide. You can see it's going on. It's within a, I think within a few seconds, I think. So it's very interesting to see like how mass transport is going on in the interfaces. Both surface and interface differences are going on here. So this is very interesting work. So I tried to repeat this experiment 2-3 times, and it's happening this like this only. So this is very interesting for the interfacial diffusions. Like very few reports are there that are doing like, it's nano scale only. It's not atomic scale. You can see from 0 second to 30, all these frames. See within a 25 seconds it forms almost this type of structures, and which basically what I say. This is the rod, and interfacially how it looks like this. So the rod is like this. So when you do some normal analysis, I've not done the details. So this is basically the rods along, because it's a gallium arsenide, has a different symmetry along 110 and 1/0 directions. So you can see like this particular rod, it looks like this. This suppose it's a gold gallium arsenide interfaces, and it's diffused like this. What I saw this one. Okay. So if you calculate some, this is the A, basically the width, how it looks like the width, this one. And this is, I have just tried to calculate like how it follow the trend of these diffusions inside the depth. So let's make a similar trend as follows. But still we are working on these issues like how, what is really happening and why this type of things are formed. So, and this is very thick gold. We are planning to do a thin gold, the next experiments. Now TM is not working. So we are planning to grow thin gold, and also we are planning to go deposit like without oxides. So just to see like how this thicknesses oxides is basically affecting the diffusions. And then we'll go for an atomic scale. If you can deposit lower gold, then you can go for an atomic scale study of this type of interfacial diffusions in future. So yeah, this experiment is still going on. We're working on these studies. Yeah, this is all about like the important point is like we're trying to correlate the surface and interface phenomena so that we can overall cover the kinetic questions about these reactions. It's very important because we'll use the metallization for gallium arsenide based devices. We tried this with the copper, but for the copper it did not work. So it's happened with the gold only. So we have not tried the other metals. For this one, we'll eventually do this in future. Yeah, this is all about. This is swapping from Professor Steve Pennycook and Professor Paul Wells and Satyam from IIT Kanpur and Mohammed from Bangalore. Thank you.
Thanks very much, Ashutosh, for finishing well on time. Yeah. Paper is open for questions. Are there any questions?
Yeah, I have one question.
Go ahead.
Yes, and the last example which you showed, in which gold is diffusing into the gallium arsenide.
Yeah.
Okay. So the gold layer has between gold and gallium arsenide, there's oxide present between them, right?
Yeah, around 2 to 3 nanometer. It's native oxide actually.
That is the native oxide of gallium.
Yeah, some I think it's a gallium oxide. Some native oxide of gallium oxide. I'm not checked this one.
So was it porous? Because gold was diffusing very fast into the gallium arsenide layer. So I mean, say this oxide is not acting as a barrier for this diffusion.
No. Here it is not acting as a barrier actually. Basically here, what I understand, basically this gold along with this oxide is try to etch the gallium arsenide because this making like some kind of groove type or pit type things looks like. But to avoid the pit formations, we did not heat the gallium arsenide before the gold deposition. So to avoid the pit formations, I have checked this part also. But still there is some reactions happening. So some gold induced, some etching is going on and gold going into the system because this is one gallium arsenide 100. So 1 bar 0 and 1 0. They have a different this like this. Then maybe that the 1 plane will be down to the gallium arsenide, right? Who is a minimum energy plane. So that may attract the gold to come into the system very fast. This is very preliminary results. We're working on it. So it's very difficult to comment.
And when you do this thing for a little longer, when you allow the gold to diffuse much deeper into the gallium arsenide, you finally form the gallium gold compound, right?
Yeah, it's forming some gold. Still we are studying. Try to analyze this one. It's making some gold gallium compound.
Yeah, that's basically that is as far as the gold gallium phase diagram maybe. This compound is very stable. It looks like, and they're forming like. So did you look at any of the thermodynamics things at the nanoscale?
No, not yet. This is just some results where the starting just because of lockdown I'm not able to do things. So we eventually do that.
Yeah, that's why you are doing this conference so that people can think now more.
Yeah. Because there's several questions arises from this one. It's good that we can see these interfacial diffusions dramatically going into, but it's not like that. We don't know also any other factors so that the gold can go deep into that. It will stop there and stabilize, and there is no much changes. There is some damages started after if you do more heating, but it stopped there. There's no much further going into the system. So that's also another observations. And also it did not happen with the copper. We try with the copper. We try with the clean gallium arsenide. It did not work. Our next step is to do some reconstructions on the gallium arsenide and add gold to see. So there are several points need to be studied. Then only we can say something about this reactions at the interfaces.
Okay, so Ahin has a question. Hi, Ahin. Go ahead.
Hey Ashutosh, nice work. In the manganese maps in the gallium arsenide and manganese diffusion, is there any insights or shifts in the manganese oxidation states from the yields? I believe it was done in a corrected microscope. So you had a subatomic level probe or maybe atomic level probe.
Yeah. It's atomic level probe. So what is your question actually?
What is the oxidation state of the manganese in the interfacial layer, and is it a manganese arsenide phase that forms for a couple of layers, or it is just atomic diffusion and that's all?
This is atomic diffusion is from only 2 atomic layer of manganese arsenide. Only 2 atomic layer.
Okay.
Yeah, it's not like
all right. Okay. And one more thing is fantastic thing with the in-situ in the gallium arsenide gold diffusion. Was it possible to do simple diffraction on the gold based wherever the gold diffused in, and to see whether it's a phase or it's a gold gallium phase or not?
So from this interface, we can do that one. From planar also we can do, like I have also tried on the when the heating was going on the planar mode, I check on the single micro rod. It shows a diffuse ring. So some liquid structures are there, liquid type. So definitely.
Okay, so it is at the heated temperature. It's not yet crystallized, but if you actually. Okay, all right, yeah, I get that. And it might be good to, if you have a nano beam there in your microscope, you can actually put a nano beam diffraction kind of a thing if you have stem in the machine in which you are carrying out. Is there a stem in the machine?
No. This is I have done this is here only. This work is here. So
yeah, it might be good to plug in the holder into a stem machine and then do a little bit of nano diffraction on that.
Exactly.
What are the phases that's present in different places? Yeah, nice work.
Exactly. Yeah, thank you.
Thanks, Ashutosh. Yeah.
Thank you.
Okay.
Thank you.
Abhay Gautam, go ahead.
Yeah, thank you. Very nice work, Dr. Ashutosh. Just to follow up on that gold diffusion process. So was it clear whether the gold is diffusing inside the material, or was it's coming out on the surface and basically segregating there?
Actually, if you see the planar one and the cross section both together, there is some because they say thick layer, 16 nanometers is very thick actually. It's almost there's a lot of high coverage. So there is definitely some surface diffusions or subsurface interactions going on along with the interfaces. So both basically contribute to the formation of this micro and this what this.
But is the gold encapsulated inside the material, or is it sitting on the surface? Was that?
Yeah. So if you see from SCM, still some golds are on the top. From TM also, and still something inside also. So that is that's why I try to correlate the surface and interfaces. Yes, some gold is on the top also.
Thanks a lot. Yeah,
thank you.
Really nice work. Yeah.
Okay. So thank you. Any other questions for Dr. Ashutosh? We still have a couple of minutes. Okay. Okay, if there are no more questions, thanks very much, Ashutosh, for very, very nice work and presentation.
Thank you, sir.
On behalf of organizers, I'd like to thank you for taking your time and presenting and sharing your work with all of us. Thank you.
Thank you, sir. I'll just stop sharing. Thank you.
Stop sharing, yeah. Okay, next, Vishwanath is there? Okay. Vishwanath?
Yes, sir.
Okay. So it gives me great pleasure to introduce Dr. Vishwanath Balakrishnan. He is the chair of School of Engineering at IIT Mandi. Vishwanath did his PhD from IISc and was a postdoc at Harvard and MIT before joining as a faculty at IIT Mandi. He has been carrying out some very interesting work on 2D materials and in-situ related things. Vishwanath, over to you.
Yes, yeah. Thanks, Professor Ravi Shankar. And also let me thank organizers, especially Kishanu and Chandra. So like I believe my screen is visible. I'm sitting in a probably not in a probably brighter side. So I'm switching off my video.
Yeah, screen is visible.
And I hope it is moving as well.
Yeah.
Okay. So the topic is I have chosen after like getting a mail from Kishanu. I thought probably it's a good time to relook at some of the old work that I have done. In-situ electron microscopy for probing vapor phase growth and also the phase transition induced actuation. This probably reminds me about the good old stories we have been told during our school days. right? You are prepared for writing an essay about the tree, but in question paper you are asked to write about the cow, right? We all know how the story further goes. So mostly the recent work that we have been doing at IIT Mandi is In-situ, including microscopy and spectroscopy. But I would like to just emphasize some of the previous work that I have done during my postdoc, In-situ work at BNL as well as at Harvard. I see there is a good connection. We are able to actually use that finding for carrying out some of the recent work. So I'll try to justify the topic by talking about some of the old work and probably in the end show the recent results that we are actually built based on the in-situ microscopy findings. There are two problems I would like to address. The first one is the carbon nanotube forest growth. Of course, not even a contemporary. Before there are many people who have seen the carbon nanotube growth inside the electron microscope, including environmental TEM. But there are some questions about.
Vishwanath, your volume is slightly low. Can you come closer to the microphone, please?
Okay, I see. Okay, probably maybe I'll raise my voice as well.
Yeah, this is fine. This is fine. Okay.
All right. So although the basic mechanism of carbon nanotube growth have been explored by many researchers, we would like to ask one particular question, especially when you try to grow carbon nanotube in a vertical geometry, like we call vertically aligned CNT forest. So there, like what exactly happens starting from the nucleation, growth kinetics, what exactly drives the vertical alignment or the self-organization? There were some debates. We thought probably we should be able to address that by looking at the in-situ CNT growth aspect. Of course, thanks to Eric, I have been like to BNL 3 times. I used to drive from Boston to BNL and a very productive time, 6-7 days. Every time when I went there, there was either the chemistry of material or ACS nano and so on. And the second problem is about the phase transformation. Of course, growth, nucleation growth also part of the phase transformation. I would like to specifically talk about, can we use simple heating holder and transmission electron microscope, not just to capture the phase transformation by looking at the electron diffraction, and also, is it possible to capture the actual cantilever deflection or the actuation that is coming out of the phase transformation? It's a very simple, good old method, but for some reason not really employed for capturing the cantilever deflection inside the transmission electron microscope. I would like to touch upon these two problems. Just to the brief idea, of course, it is done at BNL. We use the silicon nitride TM grid with a buffer layer of Al2O3, RF sputtered 10 nanometer. On top of that, we usually put like a less than 2 nanometer of DC sputtered iron as a catalyst particle. Then, of course, it is slightly different than the regular holders many already talked about. In this case, we're essentially using the TEM itself as a reactor. So typically we put around 40 milliliter or 50 milliliter oxygen, hydrogen, and so on. In addition to hydrogen, we also need to have the acetylene for the carbon precursor. So it's really like a fun to have, the growth. Of course, out of many trials, sometimes we get a very good growth. Sometimes we end up not getting it due to many issues, of course, all of us familiar. So the question is, again, I would like to again ask the same question, not just capturing the CNT growth. We want to starting from the deweighting process. We have the few nanometer of iron particle. How the iron nanoparticle, of course, there are also some possibility of forming iron oxide. So during the heating process, essentially it essentially goes from Fe3 plus to 2 plus. Then because of the hydrogen and vacuum, there is a reduction taking place. There is also deweighting, then fine particle formation. And eventually we have once we put the acetylene, we try to look at the yield spectra. We of course capture the electron diffraction pattern just to confirm whatever I said, how the conversion happens from the oxides to the metallic nanoparticle. After that, we also looked at the carbon incorporation inside the iron particle. Of course, there is also possibility of forming Fe3C. We also confirmed that Fe3 phase during the in-situ TEM study. For accommodating the actual carbon, we try to look at the carbon KH around 281 electron volt, and the integrated the intensity. Essentially, there are two possibilities. Around 281 to 283, we have a 1s pi star, and around above 290 to 300, we have a sigma star as well. In this case, carefully we looked at the 1s pi star peak. So as a function of time, how much of carbon is getting incorporated? There are some open questions. Exactly the carbon we are probing is from the Fe3C, or also there is a possibility of carbon moving around in the atmosphere as well. With that, keeping that open question, we try to at least say that there is a chance of the particle dynamically undergoing a restructuring, because at high temperature, the phase may change, microstructure, the morphology may change, and also the adhesion, otherwise the absorption energy of carbon onto the carbon catalyst particle also might change. So looking at this dynamics, we checked what is the best possibility we can understand the growth kinetics as well as the incubation time. And more importantly, at the later stage, when the carbon nanotube collectively grows, what essentially controls the alignment. Probably this is just a snapshot recorded at different time scales. I know as small as like a few seconds to 30 minutes we are recorded. Some of them we use the regular camera, some of them use the K2 camera, where we have 400 frames per second. So ultimately we end up coming with 14 or sometime 18 terabytes of data. It's a big difficulty in analyzing the data. So this just shows that there is a carbon nanotube growth. Of course, the carbon nanotube growth is not happening from all the catalyst particle. Some catalyst particle, lucky catalyst particle, are able to capture the carbon and essentially like a contribute for the CNT growth. Then we also asked why all the catalyst particles are active. There are already known in the literature, Fe3C is active, gamma Fe is active, whereas the Hege phase, I think it is a Fe5C2, that phase is inactive. And we found that for some reason, some particle which essentially has this kind of encapsulation, graphitic encapsulation, they don't grow. We do not really know why some of them choose to have the encapsulation and some of them continue to grow. Typically, we have seen like it takes maybe like a 30-40 seconds. In first 30-40 seconds, they have to decide whether they are going to have a graphitic encapsulation or they can continue to form a cap and lift off, contributing for the carbon nanotube growth. So the pictures, whatever I'm showing you, unless otherwise I mentioned, all of them are recorded either 650 degrees Celsius or 750 degrees Celsius. Again, the base pressure may be initially 10⁻⁶ star, but after pumping, putting the hydrogen, after that acetylene, we are working with around, we have a 40 to 50 milliliter of either hydrogen, usually like 40 milliliter of hydrogen and 10 milliliter of acetylene we usually use. So this is again a snapshot showing from my initial stage to around like 5-6 minutes. We see a dense growth. The bottom image probably conveys the message. We start from almost just a fine nanoparticles of iron. Then probably in 5-6 minutes, you have a dense CNT growth. At some point, there is no point in recording further because you see a dark patches. The CNTs are grown so in a thick manner, the transparency is essentially lost. So we try to look at the carbon nanotube growth and also the alignment. Let me take one by one. The first one is the incubation time. We looked at around 45 CNT growth, the initial stage. I think out of 455 in total number. And we found that, of course, typically it takes starting from few seconds to maybe like a few tens of seconds for CNT to initially like nucleate. And also there is a variation in the incubation time. As you can see in the figure B, the incubation time is not same. The incubation time, though we are trying to see whether size effect is there or not, but we are not able to directly correlate only with the size. If I just like to make it a bimodal distribution, slightly larger particle seems to have a relatively smaller incubation time, which means we are not able to explain only with the size, the variation in the incubation time. As I said earlier, it dynamically size the microstructure, the morphology, and also the carbon, whatever the incorporation, the adsorption energy, all of them essentially like contributing for the variation in the incubation time. We also looked at the growth number of CNT as a function of time, and also the growth kinetics. Again, the growth kinetics is something like between like 1.5 to around 6 nanometer per second. Based on a slight changes in the growth condition, the kinetics may vary. Then we again carefully asked what essentially controls the self-organization, especially leading to the vertically aligned carbon nanotube, which has a lot of application in a conventional ex-situ CVD experiment. So you can see in this particular movie, like here the iron nanoparticle, we slightly deposited thicker one. And also after deweighting, you can see the iron particles are not really dense. It's a relatively a sparse population of iron particle to start with. And also the reason already I cited, some of them decide to grow and some of them form a encapsulation, graphitic encapsulation. Altogether, there is no dense growth. Almost like every CNT has a relatively, like a social distancing is maintained here. In that case, what we see is, I'll try to play the movie. The carbon nanotubes grows. They kind of try to, wobble around, try to look for a company or the neighbor, but there is no immediate neighbor to support. There is no mechanical or van der Waals interaction to support. So essentially, like they move around, rotate based on the nature of the growth velocity itself, probably driving them, and also the restructuring of the particle also changing. In totality, there is no oriented growth that is taking place when you have a sparse population of CNT trying to nucleate and grow. Then we also have another situation where relatively we have a dense population of a catalyst particle, and also many of the CNTs also start growing. In this case, you can see the circle, the dotted circles. There, if you look at some of them essentially showing the circular cross section. When I see a circular cross section, it means it's trying to stand vertically. It may not be exactly 90 degree, at least 40, anywhere between 45 to 70 degree. There is some alignment happening, which means there is a sufficient number of neighbors, allowing them to form bundles, eventually getting a support from each other, leading towards some organized growth. So that is what plotted here. The number of aligned CNT as a function of time seems to be increasing when you have a relatively dense population of catalyst particle and CNTs. We also looked at the temperature effect, low temperature 550. Sometime your reduction itself may not be complete, and hence we have a relatively low density of CNT. Very high temperature at 750 and higher, we have a coarsening taking place, which also not good for the CNT growth. Intermediate temperature of 650, seems to be working fine, wherein we have a fine particle in a dense manner, contributing for the vertical alignment. You can again see like many of them showing the vertical, the circular cross section. So again, at the end, like you have a really like a thick CNT forming almost like a carpet. So this is I think probably interesting movie. I think the ACS Nano, whatever the data we could get, many of them we could actually capture from this particular video. So you can, if you look at carefully, like some of the carbon nanotubes, you can see the circular cross section. So we try to like analyze how the whatever the circular cross section. I'm not showing the details here, putting the specific edge reduction and so on. We try to count the number of CNTs that is trying to align vertically, taking the circular cross section and so on. And so this is just shows that when we have a dense population, there is a high chance of getting the dense growth. We also want to know what essentially like drives this dense growth. Then we thought of doing the cross-sectional TEM. So again, the same geometry, but in this case, instead of looking at planar view, we are looking at the carbon nanotube that are growing out of the edge. In that case, we can see the cross-section. So like I'm just like trying to focus on the figure C, where we can see there are two carbon nanotubes. one essentially probably growing relatively faster compared to the other one. So one is growing faster, the another one is actually growing slower. When they try to interact, meet each other, there will be a tension as well as compression, right? The one that is trying to grow faster will try to pull the other one as well, whereas the one that is trying to grow slower would essentially stop the motion of the other one. So there is clearly a mechanical competition between the carbon nanotubes that are growing with the different kinetics or growth rates. We also see, because of the mechanical interaction, there are formation of kinks, and also there is a formation of buckling that is arising due to the compression. In fact, we have done some more work taking this kind of images, employing the Euler's theory and so on, and trying to quantify what is the kind of forces involved during the in-situ CNT growth. So in the end, we are able to understand the vertically aligned growth essentially comes due to like 2-3 reasons. One is the dense population of the fine particle, probably nucleating relatively high number of CNTs, plus the CNTs that are growing, they have enough numbers or neighbors, they can mechanically interact. Earlier, there are reports from Cambridge and so on. They try to correlate only with the van der Waals forces. But in this case, we believe it is not just the van der Waals forces. In addition to that, there is also mechanical forces, in fact, aids the self-organized growth of CNTs. The another work, again, we have done at the, of course, the ex situ work we have carried out at MIT, and the in-situ work carried out at the BNL. In this case, again, the CNT growth we are looking at, but the substrate is different. We all know that stainless steel also can be potentially a good catalyst because it contains iron. It can be typically used for growing the CNTs, which has many different applications, including energy storage, and so on. The question was, when we tried the stainless steel substrate and do the growth, typically we see around 70% of enhancement in the yield when we do pre-treatment. So typically there are 2 different pre-treatments are done for stainless steel. Otherwise, the stainless steel you can see is like a very smooth surface, which is shown in the figure A. If you do like with essentially acid treatment, around I think 35% of HCl and so on, you essentially try to rust the stainless steel. You'll form a lot of iron oxide. Then you take it to high temperature with the hydrogen, reduce the iron oxide back to the iron. It will form a fine nanoparticle, which eventually will contribute for the CNT growth. The second way of doing the activation is subjecting the stainless steel to high temperature in the oxygen atmosphere. You essentially form in a vapor phase clearly iron oxide. Then again do the restructuring and the reduction. Once you make the surface ready with the catalyst, of course you will get the carbon nanotubes. So these are like the A and B figures, the 70 times of difference between pre-treated and untreated. So we want to understand what exactly happens during the pre-treatment. So we have chosen the again environmental TEM instead of going for the acid treatment. We have done the vapor phase oxidation at high temperature. So probably like I'll quickly try to cover. Initial stage, you see essentially like of course we'll have in yields we'll see a chromium as well as iron. Then once you do around 500 degrees Celsius, you put the oxygen again around 40 millitorr. In addition to iron chromium, you definitely see oxygen. We also by electron diffraction and yields we could confirm there is a formation of Fe3O4. Then after Fe3O4, again there are also interesting thing. It's like a core shell structure. The Fe3O4, when you try to like further reduce it, there's a thermal mismatch. There is a stress involved. The iron oxide layer essentially will undergo a kind of a breaking and forming small particle. With the involvement of hydrogen, they will essentially reduce and form an iron particle. So you can see in the bottom figure, I have shown the like there are few figures that is showing the carbon nanotube growth. In this case, as such, the carbon nanotube growth is not that interesting because it is already well known. We are mainly capturing the effect of pre-treatment on the carbon nanotube growth. So for example, the yields in the bottom figure, you can see after putting the oxygen, then hydrogen, you can clearly see the oxygen is actually gone. So the surface is completely like a reduced and formed a fine particle with iron and nickel. In fact, both iron and nickel can contribute for the CNT growth. So what we understand from the in-situ TEM, starting from the film restructuring, oxide formation, and the particle formation, deweighting, then the carbon accumulation, again captured with the help of yields. Finally, like when we have conditions right with the density, size, and so on, due to the van der Waals as well as the mechanical interaction, there is a self-organization. So this is the kind of a overall understanding that we developed by doing the in-situ experiments. And now like we are able to use this effectively at IIT Mandi. We are not the first one. There are several groups throughout the world. We are able to grow at least like up to maximum of 2 millimeter tall vertically aligned carbon nanotube forest, which can be very useful for many different applications. We can have a super hydrophobic surfaces, and we can also modify by TaO2 coating and so on to make it super hydrophilic. I just want to show you how this kind of a vertically aligned carbon nanotube can be used for energy application. The second case, we are also able to grow CNT on a stainless steel mesh, the up to even 1 meter length stainless steel mesh, even flexible, we are able to grow. We have successfully demonstrated energy storage mainly for supercapacitor application. Literally, in principle, the window stainless steel, whatever we are seeing, that can be potentially used for energy storage and many other applications when it is correctly integrated with the carbon nanotubes and other active materials. Again, as I said, this is a large scale nowadays. Like with the roll of stainless steel, we are able to put it in our CVD. We are able to grow large scale. Again, the same whatever the methods we learned, the pre-treatment is the key. We are able to use the pre-treatment that we captured from the in-situ TEM, and we are able to successfully manufacture such carbon nanotubes on a large scale. And also on silicon substrate, not only vertically aligned carbon nanotubes, we are also able to do a pattern growth. You can see here vertically aligned this kind of walls and also beautiful pillars. Probably I'll may have to wait for another opportunity to talk about those works, including how the mechanical actuation, compression can be done on those pillars and so on. I think I have a very less time, probably in 3-4 minutes, probably I'll try to cover the second topic. The second topic is about capturing the phase transformation. Instead of having a static sample, imagine we have a sample in a cantilever geometry, and the cantilever is undergoing a phase transformation, in this case VO2, that undergoes structural phase transformation from monoclinic to tetragonal. So we all know that during the phase transformation, like a shape memory alloys, there may be a volume change. In this case, there is a shrinkage. Accordingly, there will be a thin film stress, which can actually make the cantilever to go up or down. So in this case, instead of having a static sample, as you heat during the phase transformation, if the cantilever is moving up, automatically we know that the sample will not be in focus. Now, can we use the defocus to actually capture the deflection of the cantilever? So that is what exactly we have done. I will skip some of these basic details about the phase transformation. In fact, we have done both the electrical stress measurement from wafer curvature measurement and also looked at the electron diffraction pattern. The question is, there are many other methods, including simple optical method and SEM, to measure the cantilever deflection. But those cases, typically the cantilever length will be like hundreds of microns. But when you have a really like a very small cantilever, it may be just 50 nanometer or 100 nanometer, can we use the TEM to capture the deflection by using the defocus method? Of course, we all know about the Fresnel contrast. When the sample is over-focused, we'll have a dark fringe. Under-focused, we'll have bright fringe. So that is exactly going to happen during the heating. So I'm looking at this particular cantilever. The cantilever is made by the focused ion beam. We are a relatively thick cantilever, I would say. We are looking at the cantilever edge. As you heat, initially like at 25 degrees Celsius, maybe slightly under focus, you see a bright fringe. But as you increase further and further, the bright fringes are increasing, right? So which means the cantilever is essentially bending downwards. That is what making your under focus condition. But what is interesting is exactly at the phase transformation or slightly before the phase transition temperature, you start seeing the frontal contrast is suddenly changing reverse. Instead of developing a bright contrast, it is developing a dark fringes. Clearly, the cantilever is bending now like a upwards. So this is what like captured in the line profile, just the line profile to quantify the frontal contrast as a function of temperature. So that is what I'm showing you here. Clearly, as a function of temperature, you will have the sample again and again going out of focus, but iteratively we can bring it back to defocus condition and note down the what is the defocus. So every rise of temperature, there is going to be a different set of defocus. Ultimately, by doing this iteratively, we can get the defocus as a function of temperature. So when you do that with the cantilever base and cantilever tip, if you take the difference, in principle, it is possible to get the cantilever deflection as a function of temperature. So again, we try to see this with respect to, I think my battery is down. I hope I'm not abruptly disappearing. All right. So like we also compared this with the wafer curvature methods that is typically used to measure the thin film stress using the modified Stoney equation.
Your volume is very low, Shanath.
Okay, okay.
Yeah, now better, yeah.
So we validated with the Stoney's equation with the wafer curvature. In principle, from the cantilever deflection, we are able to even measure the actual transformation or the actuation stress, which is also matching. And finally, it is not even a big cantilever. Even if you have just a 10 nanometer wide and a 50 or 100 nanometer length, of course, frontal contrast is going to work. It is possible to capture that. That is what I have shown here on VO2 deposited on the aluminum and so on. So I think in terms of building the story further, we are looking at the phase transformation even now, looking at the mechanics using nano indentation and optical microscopy, how the phase transformation, the metallic and insulating domains can be visualized even by the optical contrast. We are able to capture the mechanics as well as the actuation. And I think this is another like a optical microscope image. You can see clearly how the phase transformation contrast is changing. We are also able to measure the friction. I'm just trying to show how the phase transformation actuation can be useful for many different applications. For cantilever, in this case, we could clearly capture the friction switching across the phase transformation. We are done with the help of nano indentation as well as with the friction force microscope. So last one slide, I think such a phase transformation can be really explored for the 2D materials. They do have a variety of allotropic phases, extremely sensitive material. We are able to capture the phase transformation by looking at the confocal fluorescence contrast. So how like a simple allied techniques, Raman and spectroscopy also can be useful. It'll be really interesting to see such a phase transformation in atomic level, the phenomena using dynamic microscope. So here, like these are some of the interesting possibilities I would like to highlight. Though we are doing In-situ at this stage, there are also some interesting work that we are doing in collaboration with others. Hopefully, I may have to wait for next EMSI to show some of these results. So just like to summarize, of course, the environmental team is powerful for capturing the gas phase reaction, not only just to see, in fact, to capture and quantify the incubation times, growth kinetics, and also the vertical alignment. Especially for stainless steel, the yields experiment also really provided how not just the microstructural changes, in fact, the compositional changes also helps to increase the yield by 70%. And finally, the VO2 phase transformation, it is not just the structural change, which is known for several decades. Even the actuation, the thin film stress can be measured using the simple TEM with the heating holder. So I'll stop here and I'll be happy if there are questions I can try to answer. Thank you very much.
Thanks very much, Vishnath, for finishing right on time. Questions for Vishnath? Any questions? I had a question. I was wondering about the use of the focus for defocus. How accurate is that to measure your?
Very accurate. In fact, like a defocus, I'm mentioning here like 628.5 nanometer. Even if we don't count the decimal point, a defocus of even like a few nanometer, we can clearly see the fringe change, especially when you do the line profile analysis. In fact, we also tried to change the height. Instead of probing the defocus, we try to monitor the height, Z height change as a function of temperature.
Right.
That probably, in my opinion, not accurate.
And there was a huge backlash in the hysteresis in the mechanics. Okay. So there's no problem of your. There's no hysteresis problems possibly, right?
Yeah. So in fact, like the experiments we have done with the heating, cooling, Gatan holder, of course, we don't have a very precise control, at least at that time. So we had a difficulty in quantifying with the cooling because it abruptly sometimes changes the temperature. And because of the phase transformation, the sample really goes off. So the heating is relatively, we found, having a more control.
Okay. Ohin had a question. Ohin, go ahead.
Hey, Vishwanath. I had a question about this VO2 focusing. When you heat your stuff, is there a volume change in the material itself? That might affect your focus as well.
Right. So exactly, like during the heating, it's an interesting question. So in fact, I discussed with Franz Papin. If you look at here, the phase transformation starts somewhere around about like say 65 or so. But even in the insulating region, starting from 30 to 60, there is a slope. Same way, like above 90 also there is a slope, which means in principle, we should be able to measure thermal expansion coefficient by only looking at it. Only thing is we need a more like a systematic data. When I discussed with Franz Papin, he said it is a good idea, but we have to calibrate. The temperature, like if I remember correctly, the Franz Papin's comment, the temperature window I have was only 30 to 60. Very small window. Maybe if you do it for 100 or 200 degrees Celsius, then you are right. Even the thermal expansion can be captured.
Okay. Yep.
Yeah, I have. Do we have that kind of sensitivity because this is in the these expansions are fairly small, right? And I don't know. Maybe it's possible. Okay.
Yeah. So calibration.
Okay. What is the and what is the crystallinity of this material at the edges? You know, like if you can do, for example, with the modern stem holders and stuff, if you could look at such kind of stuff, and if expansion is happening and stuff, like what is the crystallinity at the edges? Like these are single crystalline stuff?
No, this is a polycrystalline sample deposited on the silicon substrate. But we do have the other experiment, the last one I was trying to show. These are like a single crystal samples, beautiful platelets and fibers. I think for the kind of study that you are suggesting, the single crystalline samples would be more suitable.
Yeah. Thanks, Vishwanath. Nice, very nice.
Are there any other questions? Okay. If there are no other questions, let me thank Vishwanath once again for a very nice presentation. On behalf of the organizers, I'd like to thank you, Vishwanath, for taking your time and sharing your work with us.
Thank you, sir. Thank you and also the organizer. Thank you very much.
Thank you. Okay. So we move to the next. Let me just open program. Okay, gives me Sairam is here.
Yes. Hello, Professor. Yeah, I'm here.
Okay, great. Gives me great pleasure to welcome Dr. Sairam Krishnamalladi. He is from the Material Science and Metallurgical Engineering Department at IIT Hyderabad. Sairam carried out his PhD work from the Delft University of Technology, and he was responsible for development and testing a wide range of in-situ holders, and many of them which actually became commercial holders. Sairam, welcome, and we're looking forward to your talk.
Yeah, thank you, Professor Ravi Shankar. Thank you, Professor Krishanu and Chandrasekhar, for organizing this wonderful workshop and having me as an invited speaker here. It brings me great pleasure to see that the in-situ microscopy community also is growing quite significantly in India too. And I think the opportunities are plenty. In today's presentation, I'd like to talk a little bit about some of the challenges we face with in-situ microscopy, particularly when you're trying to use the MEMS-based devices. I'm trying to work on developing some MEMS-based liquid cells here at IIT Hyderabad. Initially, we're trying to carry out some liquid cell microscopy studies using graphene liquid cells. So I have a PhD and a master's student working on that right now. I'll try to show some of the preliminary results we have using graphene liquid cells and in-situ heating experiments we've carried out here. So, all right. So very briefly, just going back on where did it all start, on how did we come across this in-situ microscopy and what was the approach we used to develop the in-situ holders and all. I'll give you some brief description about in-situ MEMS holders that we developed back in Delft during my term as a PhD and a postdoc with Professor Henny Sandbergen. And then I had the opportunity to work with Professor Rafael Lenin-Borkowski, and we kind of worked on something very interesting using liquids and MEMS-based chips. So I'll give you some examples of in-situ heating in heat treatment of a classic known system, aluminum copper alloys, where we see the growth of the GP zones and the strengthening precipitates. And then a work that I've been carrying out here at IIT Hyderabad, where we've seen heating and silver copper thin films, where our interest is to look at spinodal decomposition and hopefully use these thin films for some kind of surface plasmon resonance applications. And then an area of my current interest, and hopefully for the next couple of years, where we may succeed in developing some kind of liquid cells. I have a PhD student working on this. We are trying to carry out not just in-situ imaging using conventional or STEM techniques, but we are also trying to employ phase contrast imaging to retrieve some additional information apart from what do you get from the regular amplitude contrast images. So with this brief background, let me just introduce you on how do we do imaging and in-situ TEM imaging inside a microscope. So in conventional TEM, we know that you prepare the specimens, you do the analysis post-mortem. Here is an example where we have carried out STEM and energy filtered TEM analysis to look at the dissolution and reprecipitation in nuclear glasses. So these are borosilicate based glasses which are used for storing nuclear wastes. What is interesting here is in these amorphous glasses, you kind of grow phyllosilicates, which are dendrites of silicon rich, you can call them like pillars or hair-like structures. You don't see them very clearly in the FTEM maps here, but these are essentially enriched in silicon and depleted in boron. And the growth of these phyllosilicates or the fibers of silicon nanodendrites, it happens through a dissolution and reprecipitation process. So essentially, we are quite exposed to corrosion of metals, but corrosion of glasses is one interesting area where you can also look at mechanisms that happen on the nanoscale, which lead to the degradation of glasses. Now, this was a study which we combined STEM, HAADF, and energy filtered TEM along with atom probe tomography, and we noticed that there is atomic thick layers of silicon enriched pillars as well as boron depleted pillars, which lead to the degradation of these glasses. So here, imaging is under static conditions. The examination is post-mortem, the way we carry out conventional TEM studies. Now, if you want to carry out real-time TEM studies, like the previous speaker just showed, you can approach this either by modifying the microscope column, where around the heart of the microscope, which is the objective lens, you can introduce a differential pumping aperture. When you have a differential pumping aperture, you can actually break the ultra-high vacuum around the pole piece of the microscope. And with the help of a differential pumping aperture, you can reach pressures as high as 10 millibar around the pole piece where your specimen holder is. If you have a holder which can be heated, you can actually have some kind of a reactive environment here. Typically, you use oxygen, argon, nitrogen, and some mildly reactive gases in which you can carry out in-situ environmental TEM studies. Now, this is a method which is very reliable. However, the pressures you can reach are limited. You can reach at the most 10 to 20 millibar. So this is one approach which is rather expensive. If you're modifying a microscope column, you can imagine the cost involved. So the other approach is you can use specialized TEM holders. Now, in-situ microscopy has gained interest over the last 20 odd years. But if you look at the origins of in-situ microscopy, right from the early 70s, there have been people working in the United States, in England, in Germany, as well as Japan, where people have tried to modify TEM holders. And then the idea is, if you would like to encapsulate your specimen with some kind of a reactive mixture, whether it is a liquid or a gas, the initial approaches in the mid-70s was, you can take the standard TEM grids, you can cover them with a polyacrylonitrile or cellulose kind of a membrane, which are not too thick, so you can have them relatively electron transparent, and you can have a specimen and a reactive gas mixture here, and you can seal it together with the help of an O-ring. This whole assembly goes into the TEM holder, and then you can carry out imaging in situ liquids or gases. So these were the first ideas where people tried to develop in situ microscopy techniques. Now, with the advent of aberration corrected microscopes, where the pole piece gaps have increased significantly. So for example, when you were looking at the ultra high resolution pole piece, the maximum permissible gap between the pole pieces was of the order of 2.3 millimeters or so. And then when you got the aberration corrected microscope, most of the modern day TEMs, the intermediate voltage ones, you have a pole piece gap of around 5 to 5.5 millimeters. And then even improved microscopes now, I'm aware of a couple of new developments where you could have pole piece gap as high as 11 millimeters. So with the increasing pole piece gap, with the improved stable electron optics, you can modify and you can introduce TEM holders which allow a range of external stimulus into the microscope. One such approach is using MEMS devices. So the idea is, if you have a silicon nitride membrane and if you have a silicon chip, what you can do is you can either have a single chip on which you have some kind of a platinum spiral here. So this is an example. If you look at the image on the right here, this is the bottom window which we use in what is called as a nanoreactor. You have a platinum spiral here. You have very small electron transparent windows here. If you place a specimen through resistive heating, you can use, you can heat the specimen very accurately from room temperature up to temperatures as high as 800 or even 1300 degrees centigrade, depending on the type of the heating spiral you use, and you can carry out a range of experiments. If you seal this with the top chip, you can have something like an environmental cell. So these were the initial prototypes, the images that you see here. These holders are now available as the dense solutions wildfire or climate holder. I exactly do not know the names, but anyhow, these were the initial prototypes that we developed back in the day. So the idea is you have a 10 millimeter bottom chip and an 8 millimeter top chip. You seal them both together. You have a specimen in between, and you can have a gas inlet or an outlet, or you can adapt this for a liquid also. And then you can carry out a range of in situ experiments. If you have a smaller chip like this, which is, I think, 4.5 millimeter in length, cross 5 millimeter in width, you can actually apply double tilt on this. So you can use this kind of a chip for double tilt heating experiments. So if you zoom into these windows, on the bottom half, you have a platinum spiral like this. These black circles that you see are electron transparent windows, which are silicon nitride membranes of around 15 to 20 nanometers thick. This bright white thing you see here is a FIB specimen. This is an aluminum alloy on which I'll show you some of the heat treatment examples in the upcoming slides. And if you cover this with the top chip, which also has an inverted pattern of this, and you align the top and the bottom chip together using an alignment tool, you can seal the assembly together, and you have a holder which has an inlet and an outlet. You can essentially pass a liquid or a gas inside and then carry out different kinds of environmental TEM experiments. So with this idea, I'll show you the first example of in situ heat treatment in aluminum copper alloys. So aluminum alloys, as we all know, gain enormous strength, and they have a very good strength to weight ratio, and they have excellent passivation. All these make them prime candidates for automotive and aerospace industries. The reason why they get the strength is due to the formation of these nanopillar-like precipitates. If you're looking at aluminum copper alloys, these are copper-rich precipitates. If you're looking at the 6000 series aluminum silicon-rich alloys, these are silicon pillar-rich precipitates. So the idea is we were trying to create a supersaturated solid solution, and we were trying to carry out the aging treatments inside the TEM and follow if we can see how these precipitates grow, if there is any preferential nucleation, and what sort of changes happen on the atomic scale. So with this goal in mind, we've carried out experiments initially using an FEI Titan cube with a probe and image corrector. We also were equipped with a XFEG source and a ChemiStem detector so that you could carry out in-situ EDS analysis also. And we used a high tilt holder. So the idea is, if your width of the holder is smaller than the pole piece gap, you can actually achieve a very high tilt, which allows you to carry out electron tomography also. It can be tomography in bright field TEM mode or in STEM mode. Obviously, for the improved contrast reasons, we prefer carrying out tomography in STEM mode, and I'll show you the results in the upcoming slides. So the first movie that you'll see here is a fib specimen of aluminum 2024 alloy quenched in a supersaturated state. And then we prepared a TEM specimen, and we carried out heating at 225 degrees centigrade for about 800 seconds or so. And what you notice is the growth of these pillar-like silicon and magnesium-rich precipitates. And the idea is, if you look at these, these are copper and magnesium-rich precipitates. I apologize, silicon is for the 7000 series. So when you look at these precipitates, you have streaks which are along the cube axis of the aluminum matrix. So if you look at these two precipitates, they are oriented along the 001 or 010 orientation of the aluminum matrix. And the third one is going outwards across the thickness of the specimen. So if you carry out STEM tomography on these samples, what you can do is you notice that these precipitates that have grown, they actually extend through the thickness of the sample. And if you carefully look at the images, typically the biggest problem that people had initially with carrying out these sort of heat treatment experiments was surface precipitation. Because of homogeneous nucleation on the surface, you tend to have these spherical precipitates. But what is interesting to note here is the precipitates, which are these needle-like, are sticking throughout the thickness of the sample. This behavior is very close to what you observe in bulk specimens. And again, I'll explain why in the next slide. So if you look at the evolution of the precipitates, if you look at the movie, and when you record the tomogram, you are tilting the sample at various orientations. And as you can see here, there are three families of precipitates indicated by the red, blue, and the green arrows here. The green and the blue arrows are precipitates along the cube axis, which are more or less along the plane of the specimen. And the red ones are kind of sticking out of the plane of the specimen. If you tilt it at a particular angle and you look at these red precipitates, if you see them, they nucleate slightly earlier than the green and the blue precipitates. And the reason being, these precipitates nucleate on the dislocation loops. As you can see here, the precipitates which are sitting on this, which are indicated by the red arrows, are all connected by some kind of a dislocation network here. So as it is expected, dislocations are preferential slides for nucleation. And if you follow the kinetics of this nucleation, the length of the precipitate varies linearly with respect to the square root of time. So if you determine the dimensionless growth parameter, and if you compare this, these parameters match relatively well with the knowledge we have from diffusion and bulk samples, and this follows reasonably well. The kinetics of the precipitation here is well in agreement, and the nature of the precipitation is well in agreement with what you see in the bulk samples. Now the question is, when people have been trying to do these in-situ experiments for over 50 odd years, why or how did we succeed in showing these kind of needle-like precipitation growth? I'll answer that. Before I answer that, we've also carried out in-situ heat treatment using high-resolution STEM. When you carry out heat treatment for about 24 odd hours, I'll show you the movie and the snapshots very soon. The specimen here is oriented along the 001 zone axis. And what you see here are pillars of copper-rich precipitates. The tetragonal copper-rich theta prime type precipitates is what you see here. We see the growth of very initial stage of precipitates, which are parallel planes of copper, which match with what we call as the GP zones from the traditional aluminum precipitation that we know. And then we've seen a kind of a growth sequence. If you see after the first half an hour of heating at 160 degrees centigrade, we see faint copper-rich plates here, which are more or less coherent with the matrix. And then as you heat them for 5 hours, they start becoming semi-coherent, and then they kind of grow further and they reach the so-called equilibrium theta aluminum to copper kind of composition. So as you see here, as the precipitate is growing, one interesting thing that you need to see here, people have also done this in comparison with bulk samples. There is a signature for each precipitate. As you can see here, there are planes of copper which remain intact. So these are 3 parallel planes of copper, and the precipitate only grows by adding the copper atoms across the thickness of the specimen. Of course, the length grows in the vertical direction, but in the horizontal direction, the growth is restricted. You can attribute this to the lattice mismatch and the mismatch strains here. But anyhow, the idea is, if you look at the same kind of precipitates which grow in 7000 series or 6000 series alloys, when it is silicon-rich precipitates, you have a pillar of silicon, unlike you have these parallel copper plates in copper-rich precipitates. So what you see here is, through in-situ heating, you look at some of the very early stages of precipitation, and you can come up with kinetic models for what kind of transformations are happening. We've done some studies in combination with density functional theory calculations, and we propose some kind of a model where we've seen the evolution of precipitation from the so-called, we call it pre-theta 1. We are still not calling them as GP zones here, but some kind of copper plates, parallel copper plates, which are evolving gradually to tetragonal theta prime kind of precipitates. So going back to the question, why does it work? If you look at this image here in the background, these were one of the first attempts that we tried to image using TEM mode. And as anybody wishes to prepare TEM specimens for high resolution studies, I was motivated to prepare very thin specimens. And when you prepare very thin specimen, and when the precipitation process inside these thin specimens is dominated by surface phenomena, you see lots of surface diffusion happens, and these spherical precipitates start forming on the specimen. And the other thing is the mode of imaging. If you notice, I've actually carried out the so-called low magnification STEM annular dark field images in STEM mode. So the idea is, I really need not orient my specimen at one particular orientation to look at these precipitates, because the cone of STEM probe is interacting with a specimen. So if you look at the thickness, the interaction volume is kind of a cone, and you're collecting all the diffracted beams here. You kind of highlight all the precipitates which are at multiple orientations, and then you can see them more clearly. The other reason is controlled heating. And then the whole specimen is at the same temperature, and the specimen thickness is slightly higher. Unlike the thin specimens, which are of the order of 50 nanometers or lower, we intentionally went for slightly thicker specimens. And the other reason is the entire specimen is more or less at the uniform thickness. So you place this specimen at one of the central windows, the heat transfer and the heat distribution across the whole specimen is more or less homogeneous, and the specimen thickness is also uniform. These parameters kind of help you simulate conditions that are very close to what you expect in a bulk sample, and that is why you see this bulk-like diffusion precipitation kinetics. So if you look at the conventional heating holders, the ones that were used in the early 80s and 90s, the famous ones are the Gatan holders and There are also the standard FEI and Joule holders where you have these 3 millimeter disc. You have a pretty large furnace in the holder, which needs to be cooled. So you have to control the drift of the specimen, the thermal drift, and also the heat transfer, the volume from which is heated, and the power that is dissipated is of the order of a few watts. If you look at a MEMS-based heater, the heated area is only 200 square micron area. And if you look at the heat that is dissipated is of the order of a few milliwatts. So what happens is the heat dissipation is much better when your volume of heating is very small. So this reduces the thermal drift. And additionally, the entire specimen, if you look at the small window here, we've actually carried out imaging using a thermal infrared camera, and also we've done simulations using COMSOL to see how the heat distribution here is. Because the heat distribution is quite uniform and the entire specimen thickness is maintained more or less at a uniform temperature, you have more controlled heating. So if you look at these, localized heating, excellent drift stability, these kind of help you obtain high resolution STEM images for a period of over 24 hours. So all these combined together can actually give you an opportunity to carry out some beautiful TEM imaging, STEM imaging, and then you can draw some very nice insights into how these growth mechanisms are happening and what sort of transformations are happening on an atomic scale. So the other reason is, why does it work? If you look at the mean diffusion length in this particular alloy in 2024, if you look at all the elements that are present, and if you look at the mean diffusion length, the slowest diffusing element is copper. So this determines the rate of formation and growth of precipitates. And within the temperature ranges that we are heating, if you look at the diffusion length, it is of the order of 160 nanometers. So half mean diffusion length is approximately around 80 nanometers. So if you're interested in carrying out some kind of in-situ heating experiments, please bear in mind that if you know which element determines the kinetics of the phenomenon you're interested in seeing, and if you make a specimen thicker than that particular diffusion length, the phenomenon that you observe in situ would be very close to what you can expect from a bulk sample. So these are a few tips that I would suggest for anybody who's interested in carrying out in situ heating experiments. So moving on, what do we do here at IIT Hyderabad? This is an ongoing project with a colleague of mine, Dr. Shaurya Dattagupta and Dr. Shashwata Bhattacharya. So our interest is to grow silver copper thin films by sputtering, and then if you heat them to a certain temperature, we know that silver copper from the phase diagram, it has a tendency to show spinodal decomposition within a certain composition range. So these are 50-50 films. And if you start heating them, we wanted to see whether or not these films show kind of spinodal decomposition. So the idea is we coated these aluminum copper thin films about 40 nanometers thick on this dense solution heater chip, and we carried out heating from room temperature up to 400 in various steps using various combinations. And what we notice here is the mode of imaging is STEM high angle annular dark field. We tried to minimize the diffraction contrast. So whatever contrast variations you see here can actually be related to the elements that are changing here. And additionally, we've also carried out two-dimensional phase field modeling with help of Dr. Shashwata Bhattacharya. And we've carried out composition analysis to see what sort of phase separation is happening. So as you start heating at a heating rate of about 10 degrees per minute, you can notice that after you heat it up to a temperature of about 200 to 210 degrees centigrade, there is some kind of separation happening here. Now, the very first thought that comes to mind is, how do I prove that this is actually not nucleation, but some kind of decomposition? I'll answer that very shortly. So what we notice is, as you keep heating up to 400 degrees centigrade, the dark features that you see here are the heavier element, which is silver, and the dark feature that you see here is the lighter element, which is copper, because this is high angle annular dark field mode. And the brighter features you see here are silver enriched. So we carried out a 2D phase field model, and what we expect for a 50-50 composition is this kind of a intertwined network that you classically observe in a spinodal decomposition. In this particular case, although it is not this kind of an intertwined network, what we see from the snapshots here is at the early stage of nucleation or phase separation, I'm sorry, I'll not call it nucleation, at the early stage of phase separation, because these darker features start appearing everywhere across the sample, and as you see, they grow relatively fast. We've also carried out composition analysis at these particular temperatures. We are kind of inclined to assume that this is some kind of spinodal decomposition because this is in the same range. However, before I draw that conclusion, one must bear in mind that these are thin films, and we are actually carrying out some other simulation studies to consider the thickness and the grain boundary effect, and hopefully come up with a model that appropriately fits here. One thing that we need to check here is at this early stage, and if we look at the growth kinetics, if we see that there is no nucleation but directly a phase separation, we can point out that this is kind of spinodal decomposition. So we are trying to carry out experiments around this temperature range of around 210 degrees centigrade in STEM mode, and then see gradually how the structure evolves at this temperature range. We've also carried out EDX mapping at these various temperatures. What we notice is till about 200 degrees centigrade, we do not see any phase separations, and it more or less looks homogeneously distributed with copper and silver. But from 200 onwards, as you hold the specimen at that particular temperature for about 5 to 10 minutes, we clearly see a phase separation of copper and silver. So these are still preliminary results. We obtained these results only like 10 days ago. More experiments are in progress in this particular direction. So moving on, I'm not sure how I'm doing on time. Hopefully, I'll be able to show you what we are trying to achieve using in-situ liquid cells. So if you remember the MEMS devices, I've shown you that when you use one half of the chip, you can carry out heating experiments. If you close it with the other half, this was one of the holders I developed during my postdoc. This is now improved, and it is made easier, and it is called the dense solutions climate holder. If you place the top chip here and you close it together and you align the top and the bottom chip, you can carry out, if you plug it together with a gas pumping system, you can carry out in-situ environmental TM studies using the gas. Or if you use this idea to flow a liquid, you can also use this for a liquid cell experiment. So my interest is, I've carried out some in-situ temp corrosion studies formally. I'll not be showing that in view of time right now. But right now, what we're trying to achieve is, we're trying to grow nanoparticles in real time inside the TM. And also, we're trying to look at the interface of nanoparticles and liquids, and we're trying to use phase contrast imaging techniques like electron holography and see how the surface potential is building up. So the idea is, we were initially interested in looking at using a two-half cell, the so-called commercially available liquid cell holder kind of a design, and see whether this can be used to carry out in-situ TEM studies for liquids. One of the first studies we tried to do was growing platinum nanoparticles. This is a platinum hydroxide complex in which I used imaging in TEM mode. What you notice here is, when you're using a high dose, nucleation of platinum nanoparticles takes place at various locations on the surface of the silicon nitride membrane. However, as the dose is high and you keep imaging, what happens is, under the electron beam, because the liquid here can undergo radiolysis, and you're also creating a kind of a, because it undergoes radiolysis, you're creating a concentration gradient here from the surrounding liquid. So what you see here is liquid from the neighboring area diffuses, and then the entire thin window is actually flooded with the liquid. So what is happening here is when you're doing imaging in TEM mode, especially for liquids, because of the unpredictable nature of what kind of interactions can happen between the liquid and the electron beam, and also due to the high dose, you can interfere with the imaging. I've also used the smallest aperture and low dose here, but still the thickness of the liquid is quite high such that it interferes with the imaging. If you want to use this kind of a setup and you want to carry out high resolution imaging, it is quite difficult. If you look at most of the commercially available liquid cell holders which use this 2-half design, there is one holder called the dense solutions stream holder, which kind of allows the liquid to pass through this particular channel. But most of the other holders that you have from Hummingbird, Protochips, and I think the initial one was Nanofactory also. You have some of these designs where the idea is you have a reservoir of liquid around the two chips and the liquid diffuses in here with the capillary forces. So the challenge here is placing the specimen exactly anchored within the window of interest is quite challenging. And additionally, you do not have an appropriate control on the flow rate between these windows. So whichever liquid cell that you currently look at in the market, the biggest issue is you really cannot control the flow rate, and the diffusion here is by the capillary forces, and you really do not know what exactly is the flow rate in your field of view. And in addition to this, the other challenge is, of course, people have come up with solutions like using spacers, but the membranes that you use for these liquid cells, the top and the bottom membranes are of the order of 50 nanometers. So if you look at the cross section, if you're trying to see a total liquid of a thickness of 100 to 200 nanometers plus 100 nanometer of silicon nitride, you would be losing out on the resolution of your nanoparticles. Additionally, you do not have real control on the thickness. So if you have this kind of an assembly going into ultra high vacuum, the liquid here, if it is at the atmospheric pressure or 1 bar pressure, and then the surrounding membranes, outside the membranes is around 10 minus 7 millibar, you can obviously see that there would be a bulging of the membranes. So because of these, you really do not have control on the liquid thickness. And no matter what people claim, I'll go on record stating that you really cannot have absolute control on the liquid thickness when you're using any kind of a current flow holder that is commercially available off the shelf or in the market. So the challenge is the success rate of your experiments is very low. So I'd like to illustrate the problems you have with a cartoon here. The first question is, how do you get a thin layer of liquid into the TEM? And then additionally, throughout the experiment, how do you maintain this liquid thickness constant? So this is a challenge that we are trying to address. I'm not sure by when I'll be able to succeed with this, but we're trying to collaborate with a few friends from groups in Netherlands and Germany to try and address these. So this is one of our research challenges that we are trying to deal with here. And additionally, when you have these nice liquid setup and everything, you manage to get a sample here because of multiple pumping and evacuating cycles. If at all you happen to have a crack within the silicon nitride membrane, you load everything, everything is good, and you start an experiment, your membrane cracks, the entire thing is gone. And then, like I was just mentioning, maintaining the liquid thickness is a challenge. This is exactly the same film, which is about 15 nanometers thick, on a gold 15 nanometer thick film, which is covered by silicon nitride membranes of 20 nanometer thick on either side. If you do not have a control on the liquid thickness, you actually have this kind of a problem. If you're interested in carrying out some kind of high resolution analysis at the liquid solid interface here, you really have a problem. Additionally, most of the pumps that are connected to a liquid holder are syringe pumps. People are using peristaltic pump and differential pressure pumps now, but the challenge is...
Dr. Sairab, can you please conclude?
Yes. So because of lack of control on the pumping, you can have a spray of liquid droplets. So this is one big issue. So if the liquid is loaded outside, you may actually cover the entire area of interest. So with these challenges, we try to approach liquid cells using graphene. This is what we are now doing here. We use graphene, we transfer it onto carbon grids, holy carbon grids, which are coated on gold. And our idea is, once you have nanoparticles entrapped in this kind of a nano pockets of graphene, and you have a nanoparticle of interest, our idea is to use electron holography, where you can retrieve the phase contrast information. If anybody is interested, I'll go into the details here. But the idea is you have a reference wave and an object wave, and by the interference pattern, you produce this kind of a fringe pattern here. And what happens is, if you get a reference hologram and a so-called object hologram, by using a reconstruction technique, you can retrieve the phase information. And this phase information, you can relate it to the electrostatic potential or the magnetic field within the sample. So this is an example of gold nanoparticles encapsulated in graphene liquid cell. The electrolyte here is tris buffer solution. I can give you the details later why, but if you have a basic solution, it is more stable under electron beam, and that's the reason why we use the pH 8 solution here. And the idea is, when we retrieve the phase here, you can see that across this nanoparticle, this phase shift that you have at the edge here, you can actually relate it to the potential, provided you actually account for the liquid thickness here, and you know what is the thickness of the sample, and what are the other factors here which can contribute to the phase contrast. So this is what we're trying to achieve by using nanoparticles. And this is an example of one of the nanocells we assembled here. The idea is, on a holy carbon grid here, quantifoil 1, you have two graphene membranes on the top and the bottom chip here. If you look at this pockets here, this overlapping area is where your area of interest is. And if you manage to get a liquid and a nanoparticle assembly here, you can use this window to carry out phase contrast imaging using electron holography, and you can retrieve information that you can only imagine or simulate from theoretical models. So with that, I'd like to conclude by saying that at IIT Hyderabad, we recently procured the Geol F200, the first cold-fed TEM. It is commissioned and it is functioning now. We also have an FIB here. The in-situ TEM study possibilities are, of course, static liquid experiments, in-situ heat treatment experiments, and heating and biasing experiments. So with this is what is going on now. So before I conclude, in-situ TEM studies can be fascinating, but what is the success rate of these experiments? How representative are these of real conditions? What are the challenges? These could be experimental, these could be scientific, specimen related, or environment related. And what is the effect of the electron beam? How reproducible are these experiments? And what is the effect of the surface? These are a few things that I would advise anybody to keep in mind before you plan any in-situ experiment. Try to do a corresponding ex-situ experiment and define a suitable experimental window, and you can maximize the output that you get from an in-situ experiment. So that is all that I'd like to say. So before I end the presentation, I'd like to thank my PhD supervisor and many people who've been a huge source of support and inspiration to help me achieve a few things in situ electron microscopy. So thank you all. Thank you all for your attention.
Thank you, Dr. Sairam. Thanks very much for a very nice presentation. Time for some questions. Are there any questions for Dr. Sairam?
Yeah, I have one question.
Yeah, please go ahead, Krishna.
Sairam, you showed some aluminum, copper, magnesium alloy in situ heating experiments, right? Hello, Sairam, are you there?
Yeah. Yes, sir, I can hear you. Yeah.
Yeah. So how do you say they are GP zones actually?
Just a second.
You showed some copper layers of copper atoms, parallel layers of copper atoms.
So it is this one, if I'm not wrong.
Yeah, but you are looking at a 2D projection of the 3D, right? They must be pretty big.
Isn't it?
Yeah. They are alternative copper atomic layers, right?
Yeah.
But they are not single layer, double layer like that. They may be multiple atomic columns.
So to answer your question on whether it is GP zones, first of all, what we think of GP zones are actually small clusters of copper-rich layers, which are, say, 3 or 4 atomic planes. So if you look at this, this is something which is after a GP zone and before an intermediate precipitate is actually formed. So if you want to call this a GP zone, I would say it should be much smaller than this. First of all, the length is of course of the order of 5 to 7 nanometers here. But if you look at what we know as GP zones, they should be of the order of 10 to 40 angstroms. This is slightly larger than that. And if you want to actually see GP zones, the best way is only through atom probe tomography. I don't think with the thickness of the specimen that we have, at least in this particular specimen, you can actually see them as GP zones. So I call it as pre-theta prime precipitates.
Yeah. So that's what I'm telling. So you are
GP zones.
Yeah. Next slide. You're showing some pre-theta double theta prime, and P and post, right? P theta prime, and that P theta prime is what P theta. That means theta double prime, right? Before theta prime, theta double prime comes.
This is not really matching with the theta double prime sort of a thing. We saw them in some.
I think in the interest of time, can we?
Yeah. Sorry. Yeah.
Can we discuss later? Thanks very much, Dr. Sairam, because we are almost running behind schedule. Thank you very much for very, very nice presentations.
Sorry for delaying a little. Thank you.
If anyone has any questions for Dr. Sairam, please feel free to contact him. Sairam, you can unshare your.
Thank you.
Okay, the final talk for this workshop. It gives me great pleasure to welcome Thomas Atlantis. He is a tenure track assistant professor in the Faculty of Engineering at University of Antwerp. Thomas did his bachelor's and master's from Greece. Subsequently, he did his PhD from the EMAT, Belgium, and he was also a postdoctoral fellow at EMAT before taking over the faculty position. His main topics of interest are in-situ liquid TM, electrocatalysis, and electron tomography. We look forward to your talk. Over to you, Thomas.
Thank you very much, Ravi, Chair, for the very nice introduction, and very good afternoon, I guess, no, very good evening, I guess, at the moment there for everyone. It is my great pleasure to be here, and I would like to thank first the organizers for giving me the opportunity to give this talk today. And today I will be focusing my talk on something different than liquids. It will be in a gas phase in situ investigation. And I will show you how we can track in situ morphological changes of nanoparticles in a variable gaseous environment at the atomic scale. As Ravi said already, Professor Ravi Shankar, I am a research professor at the Faculty of Applied Engineering at the University of Antwerp, and I do my research between two groups. The first group is, I think most of you know it, is the Electron Microscopy for Material Research Group at the University of Antwerp, or EMAT, where there are 7 professors plus 2 associate professors, 20 postdocs, 30 PhD students, and 7 ATP members. A few words about the equipment that is available at EMAT. We have 6 transmission electron microscopes. One of them being the Titan Themis Z microscope, which arrived quite sometime a few months ago, let's say, very recently, where you can do TEM and STEM, special resolution, even at 60 kV of almost 100 picometer. Very good ADX and EELS also can be done there. And also we have 2 more Titan microscopes, all of them aberration corrected. And a Techni, an Osiris, a Geol, and also 2 scanning electron microscopes, one of them being also possible to work at environmental conditions, and a dual beam system, or the so-called FIB. And of course, there are also plenty of in situ holders, such as a couple of heating holders, also for tomography, like the ones that Professor Maladi showed a few minutes ago. Also gas holders, liquid holders, biasing, also cryo holders, and so on. The other lab that I do my research is the so-called Applied Electrochemistry and Catalysis group, which is focusing on a different field, or the field of electrocatalysis and electrochemistry. And this is a smaller group. It's quite a young group, but still, as you can see, 2 years ago that I joined the group, we were almost 10 people, and now it has grown and we are almost 25 to 30 people. I will skip the outline and I will go directly to the introduction of my talk today, which will be very important for all of you, or most of you, let's say, to understand the reason why we performed this study that I'm going to show you, this very challenging in-situ study that I will show you today, and a few also aspects of the experimental approach and also the experimental, the analysis later. Nanoparticles, we all know, have attracted a lot of interest during the last years due to the unique properties and applications they have in different scientific fields, such as in medical sciences, material and environmental sciences, electronics, energy harvesting, and so on. And of course, a very important application of nanoparticles is that they can be used in catalysis. And for catalysis, we can have different types of nanoparticles, such as monometallic, core cell, asymmetric, also nanoparticles made of more than 2 or 3 elements, coexisting, alloys, and so on. So we can have a very wide variety of nanoparticles that can be used in catalysis. And as you can see from this cartoon, where we explain how catalysis works, you can see that the very important is the surface of the catalyst. So these few atomic layers at the nanoparticle are very important and the most determining for making a nanoparticle a good catalyst. But of course, the material as well for specific applications, but this surface is the most important part. And of course, in order to be able to investigate the surface and different aspects of nanoparticles, so these tiny structures, we need to have a very powerful tool to achieve resolutions at the atomic scale. And such a tool, of course, is the transmission electron microscope. And with such a tool, we can do 2D imaging. We can also get diffraction data from the same nanoparticles, or let's say regions of interest. Also, we can do spectroscopy, EDX, EELS, and so on. And that means that we can get information such as the number of atoms, the distribution of elements, the type of crystallographic facets, and also the overall shape of a nanoparticle. However, all this information, if you think about, and I think this is also like something that was one of the latest discussions during the last talk, is that all these, most of the times, are 2D information. So from conventional TEM, we can just do 2D information, either in spectroscopy or for imaging. And here I have a simple example to understand that many times 2D can be quite misleading. So you can see here the shadow of two, let's say, objects. But if I show you what makes these two objects, I'm almost sure nobody would believe it's just a bunch of metallic parts. Therefore, from this very simple everyday life example, you can see that two-dimensional projections of a three-dimensional object can be very misleading. What we can do in order to obtain three-dimensional information in the electron microscope is to use a technique which is called electron tomography. And this is a specialization of Professor Sarah Balz at the EMAT laboratory, where I did together with her my PhD and postdoc studies. And how the technique works is you have a specialized TM holder with a quite thin tip in order to be able to tilt inside the two-pole pieces of the microscope. You acquire images every 1 or 2 degrees along a wide tilt range, possibly plus minus 80 degrees. You acquire these images, and then you can use these images as an input for the reconstruction algorithm in order to be able to obtain a three-dimensional characterization of the structure under investigation. And as you can see here, by having such a reconstruction, now you can see that we can get orthoslices through the volume, which means that we can perform a further quantification of the structure or of the shape or what is inside the nanoparticle, which is very important in the end, because it's not only important to have qualitative information. Just to understand how important it is to have 3D information from the TEM, I have here an example of a study that we did some time ago, where you can see here 2 assemblies of nanoparticles. So these are not high-resolution TEM images, let's say STEM images, are just assemblies of nanoparticles, which they create this kind of honeycomb-like of structure. And of course, if we see that, I would say it's quite normal to say, by looking at that, I think I have particles that create this honeycomb lattice. These are cadmium selenide and lead selenide quantum dots of 5 nanometer each. They create this honeycomb, let's say 1 layer lattice. But when we performed electron tomography experiments, we realized that this configuration is not in a single layer, but we have 2 layers on top of each other. So we have a silicene type of structure. And also you will see from the orthoslices along the other direction at 90 degrees, we can see very clear the 2 layers on top of each other. And this is a very important observation because the properties change dramatically. And that means that we have a completely different material. And this is also very important information, both for the theoretical and also the synthesis people. And of course, by having such information, you can do further quantification, such as measure distances between the particles, bond angles, and so on. Also, very important for the field of catalysis, that when you have nanoparticles and you want many times for collaborators that do synthesis, it's very important to have information about the shape of the nanoparticles. And by applying tomography, for the example of this gold nanorod, you can see very clear the shape of the nanoparticle, but still, for such cases that normally we expect to have, we see in literature quite often for these rods that we may expect 520 facets or even higher order facets, or this 110, 100, and so on, depending, of course, on the synthesis parameters and so on. It is quite difficult, or let's say challenging, to define the type of crystallographic facets with this resolution. What we can do instead is acquire atomic resolution images along different zone axes, and by combining those with more advanced reconstruction algorithms, we can have a 3-dimensional reconstruction at the atomic scale. And as you can see from this example here of the gold rod, you can see the inner structure of the rod and the position of each atom in the structure. And this will enable us to get more reliable information about the different type of
Hello.
Yeah,
I'm not able to hear. Are you able to hear? Anyone is able to hear?
No.
Yeah, something happened at his
Yeah.
end, actually.
Yeah, I think his thing may be frozen.
Yeah, net connection.
Thomas?
Yes, Ravi, can you hear me? I heard something. Can you still hear me?
Yes, now we can hear you. We lost you in the middle.
Yes, I just see that also my internet connection was okay.
Okay.
Sorry.
Fine,
Did you? Where did you? Sorry, my apologies. Where did you lose me? At which point?
you said you can get atomic resolution and get the
Perfect.
facets.
Perfect. So it was just for a few seconds. Perfect.
Yes. Yes.
Thank you. So indeed, by acquiring atomic resolution images along different zone axes, you can obtain reconstructions with information about the atomic lattice and so on in 3D. But of course, something that you should keep for the rest of the presentation is that in order to obtain such information, we need to tilt the holder inside the microscope along a wide tilt range and get many images. Of course, before I said also that we can do spectroscopy, and indeed, if we use spectroscopic data acquired along different tilt angles as an input for reconstruction algorithms, we can obtain, like for the example here of these iron cobalt nano dumbbells, we can obtain information about the distribution of the elements in 3D, where you can see here we have this cobalt rod, and we have the growth of iron dumbbells at the tip of this rod. But of course, nanomaterials are changing during real catalytic reactions and during real catalytic conditions. And a catalyst, normally we expect to have morphology and size changes, structure changes. Also, for core cell structures, we may have variations in the cell thickness. Also, we may start having alloying between the core and the cell. Also, the quality of alloying may change, also presence of defects and so on. And this is something that we saw also in the different examples in the presentations today. And what people have been doing these years in order to get kind of a more close to the real catalytic conditions results is to use this sort of identical location TEM. where what you do with very simple words is you get a TEM grid with a catalyst deposited before the reaction. You can find a few locations in the grid where you can see different parts of the catalyst, like for the example here. And then you take this grid out, you know where these positions are. You go to do either, for instance, in electrocatalysis, you go to your liquid cell there and you can do all the electrocatalytic cycling, or you can do some other tests for gas phase catalysis and so on. Then you go back to the microscope and you can see at these specific positions what happens. And the same, of course, can be done also with spectroscopy, where you can see for this nickel platinum nanoparticle how the distribution of element changes and so on. And of course, very recently, also in our group, we did a similar investigation for platinum dendrites, where these platinum dendrites are used for the oxygen reduction reaction. So they're very good catalysts for this specific reaction. And what we did is we acquired tomography series of, this is an example of one dendrite, but for many dendrites, in order to get information about the porosity and quantify the porosity in 3D. And then these catalysts were used for different cycling procedures. And then by acquiring tomography series from the cycled material, we were able to see from the three-dimensional information and from the quantification we performed in 3D that the porosity decreased. And of course, that means that if you have a decreased porosity, also your surface amount is decreasing, and this can be the reason why these catalysts have a reduced catalytic activity after a certain amount of cycles because of this loss of porosity. But of course, as I said before, you use this identical location TEM and you get the before and after. And this after can be, let's say, after 10 cycles, after heating at 200 Celsius, after flowing a specific gas, and so on. And you lose all these intermediate steps. And what we saw from all the presentations today, and also from the last presentation, that we always see by using these in-situ holders that you get different times in the reaction, 10 seconds, 20 seconds, and so on. And you can do this kind of evolution, let's say, and the dynamics of the reaction. And as you can see also from my example here, I have here a Syria particle where a tiny gold nanoparticle is at the surface of Syria. And you can see that in vacuum conditions and room temperature, we see that the surface atoms here are very stable. We see no changes and they look quite in their position. But now if we go to an oxygen atmosphere and a temperature of 300 Celsius, we can see that now the surface is very, very mobile. And you can see that it's, although a very fast acquisition scheme is used, still the changes are so fast that sometimes you cannot even capture them. And that means that it's very important indeed to be able to track the changes at every moment of a reaction. How can we go from ex-situ to in-situ? As also Professor Maladi said before, we can use environmental TEM, but the most important there is that if you want to use such a microscope, you need to modify all these pole pieces, let's say, the objective, somehow, let's say, lens system, when you have to use differential pumping in order to be able to isolate this region from the ultra high vacuum of the microscope, and then you will be able to flow gases and use a heating holder to do your investigations. But of course, also there, quite often you are limited to a few millibars of pressure. What else you can do is to use in-situ TEM holders, like the one you can see here, which we also used for our studies, and it's coming from dense solutions, where instead of having, let's say, a copper grid at the end, you have a nanoreactor where you can flow here between the silicon nitride chips, you can flow gases and liquids, let's say, and you can also do heating inside the TEM without the need to modify any in the column. So in principle, you can just use this holder at any other microscope without any further modifications. And what has been done quite often until now is that such holders are used for in-situ studies. And here, for instance, for this example, and also for other similar examples, different types of catalysts like platinum or palladium nanoparticles have been imaged using TEM. And then you can get such TEM, 2D TEM images at, let's say, at oxygen atmosphere, at hydrogen atmosphere, and so on. And then by using these images, you can get a kind of a projected estimation of the projected shape of the nanoparticle. And then by using Wolf constructions and DFT calculations, by considering the gases that you have there and the interface energies, you can kind of get these equilibrium shapes that you can explain what you see from these 2D projections. But of course, sometimes this is not always an easy thing to do. And as you can see from the example I have here, I just got one platinum nanoparticle, which we normally expect it to be almost like a cube in shape. And then by doing TEM, we can see that from this projected shape, we can have two different types of shapes. We can have this type of shape that you have just 110 and 100 facets, but also this shape can also be explained by this type of configuration that you also have 100, 111, and 110 facets, because you see indeed the projected shape along the 100 direction can be quite similar. What we can do instead is, since of course, as I said also before, we need to go at a very detail at the surface and at a few atomic layers, instead of using TEM images, we can use instead high resolution STEM images. And by using such STEM images, by using an approach which is called a statistical parameter estimation theory and atom counting, this is the specialization of my colleague, Professor Sada Van Aert at EMAT, it is possible to detect, of course, the atomic columns. And then, since we also have in such images Z contrast information, we can detect the number of atoms in each atomic column. And then by detecting the number of atoms in each atomic column, then we can position these atoms in each atomic column parallel to the beam direction and symmetrically around a central plane. And that means, and also by using molecular dynamic simulations and that employ the embedded atom method potential, we can obtain relaxed models, 3D models of the structure under investigation. And this was used very recently in an in-situ heating investigation we did in the group, where we got these gold nano dumbbells. We imaged them before heating in room temperature. And by using this approach, we were able to obtain this three-dimensional kind of reconstruction. This is not a calculated model, a theoretical model. It's a model based on the experimental atom counting results, where we could see the facets in 3D. And then we induced heating at 350 degrees Celsius. We saw that the 2D shape was changed here at the tip. And then we could also, by acquiring high resolution TEM images during the heating procedure, it was possible with just one single image to get this three-dimensional reconstruction of the atomic lattice. We use this approach for the platinum nanoparticles that we used in the in-situ study that I will show you now. And these platinum nanoparticles, which were synthesized from our collaborators in San Sebastian, the group of Professor Luis Marzan. As you can see, also I showed you before, we have this projected, somehow let's say square projected shape, which are almost cubes. And then by do atom counting and by using the approach that I just told you, we can obtain a three-dimensional model of the structure under investigation. And here the different colors are for different facets. We have the 100 and the 111 facets, and also the gray are for the more high order facets. Just to validate the approach, for the same platinum nanoparticle, we acquired a full tomography series with high resolution images from -76 to +76 and tilt increment of 2 degrees. We reconstructed the series after alignment, of course, and then from the same exact nanoparticle, which of course I have to say that in order to do this atom counting, you always need to be perfectly in zone axis. We acquired an image along this 100 of the FCC lattice of platinum, and by doing atom counting, we can see here that we get a very similar, I would say, the same result. Here, 77 images, and here just one atomic image. And also here, for instance, you can see from the 3D reconstruction that we have this extra atomic layer, which is also possible to see at the result from atom counting. So you can see that it is not just positioning atoms randomly on the shape, but is really also related to where each atom is positioned in the lattice. And this brings me to the main let's say, part of this experiment, which we got these platinum nanoparticles and we used the in-situ gas heating holder from DENS to do a redox reaction. So we flew hydrogen and oxygen in the cell in order to see how the shape changes and also to quantify the number of atoms and also the atoms at the surface of the particles, which is very important for catalysis. But of course, when we have the reactor assembled and in order to achieve this high resolution, let's say atomic scale resolution, you see that when we only have the bottom chip, which is only a 30 nanometer thick silicon nitride, we see that here, if we get a close-up, the signal to noise is quite good. Then if we assemble the reactor, so we have 30 nanometer extra at the top chip, then we see that now we have a lower signal to noise ratio, which can be sometimes a bit problematic. Also, another thing that we face with such experiments is that, as you can see, we have continuous orientation changing. And unfortunately, since this holder for the moment cannot tilt for more than plus minus 10 to 15 degrees, it's not possible to get a full tilt series. And that means that we need to keep the particle stable at the zone axis. And that means that every time we have a loss in orientation, we have to go to another particle because we cannot get this in-zone axis image. Also, another thing is that we thought about using low dose, of course, and also low acquisition time and very low dose. But of course, you see, even by using low dose and by starting from 1 second to 8 seconds, you see that by increasing the time, so you get a very low dose, let's say, conditions, but then increasing the time of acquisition. By increasing the time of acquisition, you see that we have these distortions, which can be from, let's say, drifting of the sample in the holder and so on, but also some small changes in orientation. Also, another limitation was the fact that now, if we also flow gas, where here is 1 bar pressure and 300 Celsius of hydrogen, then we can see that the signal to noise ratio is decreasing even more. What we did is we reduced the electron dose and we acquired images with very short dwell times in order to avoid these issues with misorientations and so on. So this is the raw data where you can see the signal to noise ratio is very low. And then we acquired fast images of this orientation, let's say 5 to 10 images, and then we average them. And when we do the averaging, you can see that here at the surface of the particle, which is the most important to investigate, we see that we have blurring. And if I go to more close up, you can see that indeed the last few atomic layers are blurred, so we cannot see anything there, any atoms. And also you have these distortions, which is because probably, as I show you, each image has distortions. And if we average, we just average these artifacts. What we did instead is, instead of using these raw images uncorrected for averaging, we used another approach. So these images were first corrected for distortions by using a neural network. So what we did is my colleague, Professor Van Eyre, together with Dr. Ivan Lobato in the group, they trained a neural network by giving different simulated STEM images with and without different types of distortions and artifacts. And then this network can learn how to detect and correct these distortions. And then by using this let's say, trained network, we can get corrected images for distortions. And then these corrected images for distortions are used for averaging by using rigid and non-rigid registration. And just to see the difference between the two, this is the averaged image without correction for distortions. And this is the image, the averaged image, after using as an input for averaging the images corrected for distortions from the neural network. And if I get again this close up, you can see the same region here. You see the defects and blurring, but then the result with the corrected with the neural network and averaging, you see now very clear the sulfate atoms are clearly visually, let's say, visual, and also we don't have these distortions anymore. This is what we did then. We get the raw data, then we average by using the approach that I told you. Then there we do atom counting, where we can get the position of each atomic column and also the number of atoms in each column. And then by using the approach that I told you before, we can get a 3D model of the structure under investigation. We did this. This is for ultra high vacuum and room temperature. You can see very clear the facets. And then we did that for hydrogen and oxygen atmospheres, where you can see for hydrogen, the shape changed. It became more like a truncated cube. And we can see again here the type of facets we have. Then in oxygen, the shape became almost spherical, which is quite expected for oxygen. And then we see here we have almost no 100 facets. We have more of these gray high order index facets. And then we did that in a reversible manner. We did again hydrogen, where again we see that for the same particle always, the spherical morphology became again truncated cube. Then again, oxygen, where again we have this spherical shape. So we can see that we can do that in a reversible manner. And of course, very important is that we could also do a quantification of the result. And we can see here that for hydrogen atmosphere, we have more of these 100 and 111 facets and lower high order index facets. Then for oxygen, we have a spike and a rapid increase of the high order index facets. And then again, for hydrogen, we have a reduction of the high order facets, then again in oxygen and so on. And of course, very important is also, some may say that after this heating at 300 Celsius in oxygen, maybe some atoms escape and so on. But it's very important to say that since we can detect the number of atoms with atom counting, we also did the quantification and we saw that always the number of atoms was the same with just an error of less than 1%, which is very important because that means that the shape didn't change because some atoms escaped the surface and so on. But it was mostly just rearrangement of the surface atoms. And of course, it's very important to prove that this is not only because of heating, and it's also because of the gas, right? And this is an experiment we did for a similar platinum nanoparticle, where as you can see, in room temperature, the shape is what you saw before. Then 300 Celsius, so the temperature we used for the gas experiment, we see almost no changes without gas. And then again, even a step further, 400 Celsius, and again, the shape remains the same, which means that all these changes were due to the presence of course, the different gases. Before I close, I would like to thank all my colleagues at EMAT and also my colleagues from San Sebastian for the samples and all the fruitful discussions we had in order to accomplish this work. Also people from DEN Solutions. Also a very big thank to the organizers of the conference for the very kind invitation to have this lecture today, and also you for your attention.
Thank you very much, Thomas. Fascinating talk. I have a few questions, but let me ask the others first, and then I'll come back later. Questions for Dr. Thomas, please.
So may I ask a question?
Yeah, Pawan, go on. Sorry, somebody else has. Pawan raised his hand. Pawan, go on. Okay, Krishanu, go on. Okay, Krishanu.
No, Pawan is going to ask. Let him finish.
Okay, Pawan, go on.
Yeah, thank you. Very impressive talk. I just wanted to ask a question about your last slide. So you're
that
saying, yes. So the reference is in vacuum, is it?
Yes, this is ultra high vacuum. Yeah, of course, because we would just wanted to check what happens without the gas, just temperature.
Correct.
To see
and
if, yes.
And so there is no loss of atoms in ultra high vacuum. How are you preventing that?
I mean, maybe there are, but for instance, we compare the overall number of atoms in the particle, and we saw that there's not a very big change, because like you saw that in hydrogen and oxygen, you have a very big changes at the surface. Maybe somebody would say that we have many atoms going away or so, but it's mostly a rearrangement or so. It's not really atoms escaping and going somewhere else or so, which of course is not easy to happen, but it's just a confirmation, let's say, somehow.
Okay, but the way I see it is, even if there is atom loss, it seems that the shape is kind of maintained. Is that a fair interpretation, or in ultra high vacuum?
But I think for this, let's say, big particles, because when we discuss about atomic clusters of a few atoms, let's say, then of course things change. And of course, a very big issue always with TEM is that we have the effect of the electron beam, right?
Correct.
I think, of course, platinum, let's say it's a quite stable structure, and you also have the ligands there around. So it's not like, for instance, an electrocatalyst, which is done without any ligands most of the times around, for instance, if it's done during electrosynthesis. Normally you have the ligands that also keep the particle kind of stable, let's say, under the beam for more time. But if it was a freestanding particle without ligands, I would think there that we would really have an issue, and maybe it would just change even shape or so. I could expect, also depending on the structure.
I see. I didn't understand the ligand part, but okay, great, thank you.
Yeah, because sorry, this is made by colloidal synthesis, this particle. So you would have ligands there always.
Right. Okay.
Okay, Krishanu?
Yeah, thanks for a nice presentation, Thomas. I have one simple question. When you reconstruct these 3D dimensional structures, okay, what about the surface reconstructions of the nanoparticle taking place during electron beam interactions?
Thank you, Krishanu, for the question. This is about when we acquire the full Tomos series or just one image and atom counting?
So you are acquiring the full tomographic series, and then the particle is also undergoing simultaneous surface reconstruction, right? Because
exactly.
The electron beam is falling on the sample. So will it not change the shape of the particle during whole observations?
Of course, this is a very big issue that we many times have. And for instance, of course, platinum, it's a quite stable material to work at. But if you have, for instance, now some quantum dots or so, because also there you have more instability under the beam. And of course, there you will not be able always, let's say, to get a full Tomos series. Also depends on the size of the particle and so on. That's why we are always very careful with imaging, and we use low dose. And you saw now that we can use different approaches. You don't just acquire an image and then you just use it as an input for reconstruction. So you use a very low dose. You can also do this correction for distortions. And then you can also improve the signal to noise ratio, of course, and you can use us as an input. And always, since we have also this ability to do atom counting by using only one projection, what we do also now is you acquire an image of platinum, let's say, along 100 before the acquisition of the full Tomos series. Then you acquire your full Tomos series, and then you go back after the end to this same zone axis, and you acquire a new image, and then you compare. If it's something completely different, then of course you cannot show that to anybody else, right? Because you had a lot of changes. But if the result is identical, then you are easily safe. You can safely say that I didn't have any very big problems. Of course, I'm almost sure it would be impossible not to have a few or more atoms leaving, or let's say rearranging or so. This, I think, you can never avoid when you have electrons. Yes?
That's the thing. But so therefore, when you put a gas on the surface of these nanoparticles, there is going to be, as you showed in the beginning, that the change of the atomic configuration at the surface is very rapid. And,
exactly.
And if you want to see the 3D tomography of those particles under the gaseous atmosphere, how the shape is changing, so will it not be extremely difficult to even predict the shape of the particle?
I think yes and no, because in such cases, and I think my colleagues, and especially Professor Sarah Bals, that she's working on that now, because as Ravi said now, this was like something we did some time ago, and this is now, I'm mostly, let's say, switching to the liquid TM. Let's say what is done now is that, for instance, if you have these multiple fast scans, you have a particle, then you flow the gas, and then you acquire fast images, then you can get a few hundreds of images and so during the reaction. And if you can use this as an input for atom counting, because I show you that just by one single image, you can get all the information about surface atoms and so on. If you do that for all the acquired images, of course, if you are still in zone axis, then you can follow these dynamics in 3D. And in our case, we also have a mass spectrometer that you can connect to the outlet of the gases. And also if you combine gases, for instance, you can do carbon monoxide with oxygen, or let's say oxygen with, hydrogen with another, let's say, gas or so, you can also get what comes out of this reaction. Because this is something that was done by other researchers in the past that they saw some oscillatory behavior after changing and so on, let's say with a mass spectrometer and so on. Again, I think for platinum nanoparticles.
Okay, thank you.
Yeah, so are there any questions? If I have some questions, I don't see any raised hands. So thanks, Thomas, once again for a very nice talk. So I had a couple of questions. So how long does it take? I think presumably you do the equilibration of the particles before in the gas, right? How long does that take usually?
For what? Sorry, Ravi, I lost for a moment. To which preparation?
For example, you change over to the gas and equilibrate it, right? For some time before you do the imaging. How long is that done? How long is that equilibration done?
Thus, it depends, because also it's very important before you do any experiment to do a multiple times pumping of the system and so on, to make sure, for instance, if you have hydrogen, you have to make sure your cell is really oxygen-free and air-free, let's say.
Right.
So normally, as far as I see, changes, if you start flowing gas, you have to be very careful, because changes sometimes, and especially at high temperature, occur very, very fast.
Okay. So
yes.
Very fast meaning seconds or minutes or?
I would say, what you see, yeah, it's a couple of seconds, but I think physically the changes happen in even nanoseconds, I think, or so, I guess, sometimes.
Because typically I would think that, for example, equilibrium shapes and things like that would take much longer. So that's the reason I'm asking. For this sort of a number of atoms, considering diffusion and so on, I would guess that it would take much longer. So I thought, would you black the beam, equilibrate it, and then go back into the imaging, or how is it done?
No, now I get it. No, I thought, let's say, changes, any small changes at the surface of the particle.
No, I meant
this is what the overall thing, like the shape we got at the end. Okay.
Yes.
This happens in, let's say, I think, as far as I remember, for this experiment, after from room temperature to 300 and hydrogen, once we started flowing, within 15 minutes, the shape was there.
Okay, 15 minutes. Okay, that seems more
15,
reasonable.
20. Yes. 15, 20 minutes, the shape was there. Yeah. And then the same with oxygen. So you remove all hydrogen, you flow a bit of inert gas, like argon or so, and then you, because also you don't want to interact hydrogen with oxygen in a reactor, and then you flow oxygen, which takes approximately the same time.
Right. Okay. So yeah, one small comment related to Pawan's question. I think the melting point of platinum is pretty high, 1700 or so. Therefore, the vapor pressure should be quite low, and maybe 300 or 400 actually. Of course, there will be some, and vacuum particularly, but that may not be very large, like 1% or something may be a reasonable number. The other question that I had is obviously of direct interest to me, is what is the status on this CNN for bimetallic atom counting?
That I'm not sure, because I didn't follow recently, but I think there is some, you mean in general for bimetallics?
In general for bimetallics, right.
I'm not sure, but I think there is already some kind of progress. I'm not sure if it's really something which is, let's say, like something routine that you can get every let's say, bimetallic structure or so, but I think there is, some progress. I think.
Okay, great.
But still, I'm not sure, because I didn't follow, let's say, that.
Okay, sure. Any other questions from anyone else? Okay, if not, let's thank Thomas once again for a really wonderful presentation. I'd like to thank all the speakers in this particular session. Thanks, Thomas, for coming away from a meeting and taking time to come and give this talk. I would like to thank all the speakers in this session, particularly for sticking to the time and for giving very nice presentations, and also all the speakers overall in the workshop. And I would like to thank the organizers once again for giving me the opportunity to chair this session. Thank you.
Thank you very much, everyone, as well.
Thank you.
Yeah, thanks, Professor Ravi Shankar, for nicely managing this session. And I think we are exactly at 7:30. So we finished all our talks and everything. Now we just spend a couple of maybe 5 to 10 minutes for something about valedictory. So may I request Professor Chandrasekhar to come up also? So he is one of the co-organizers of this work, of the symposium, and he worked really hard. So are you there, Chandrasekhar? Hello.
Yeah, I'm here. Yeah, I'm here.
So now we can see you in camera, right? So I know the way we go ahead with this kind of symposium is that this is a completely online symposium, and I had a nice experience of organizing this because no talk was skipped. Every speaker spoke, and interactions were quite strong among the audience as well as with the people in the panelist. And today I came to know the advantage of this Zoom webinar, that there's very less disturbance from the audience. Even if audience number is very large, suppose we had 180 odd numbers on the first day, there is no disturbance except some disturbance from my side. And the advantage is having a panel. You can create a panel and bring this panel on the front of it so that they will speak and their things are important. That is the biggest advantage. But disadvantage, obviously, interactions between the speakers and the students. Sometimes students feel that they are alienated. So this is the challenge we faced. But finally, I hope we could manage to accommodate all the requests from everybody. So now, because Professor Ravi Shankar has been speaking for the last 2 hours, so I would like to request Professor Ravi Shankar to speak a few words about this symposium. He has attended the several talks. Yesterday also, today also I've seen him, and the panel discussions. Can you start with by saying how good this kind of symposium was?
Sure. Thanks, Krishana, very much. I said this at the beginning also. I think, first of all, congratulations to you and CST for, thinking about organizing such a thing, and actually inviting a range of wonderful speakers, really, right from day one, starting from Sir David Miller all the way to Thomas. Really wonderful talks. It is not limited to only one topic or other. For example, not only liquid cells or not only, it covered all the range from chemical reactions to mechanical properties to, to liquid cells to nanoparticles. Very really wide, and also new techniques like tychography, metals, ceramics, range of materials also. So I think it was really well conceived and also well executed, I should say. No hiccups at all, considering that everybody is coming online. There could have been many disturbances and so on. It was a really wonderful program. Unfortunately, I missed a couple of the industry talks, but I attended some of them today. That was a very good idea, and also the chance for students to present. I think that was also really wonderful. I think this can actually serve as a model for things that we can organize in the future. So I think this is really well organized and well thought out. And thanks to Krishanu and Chandra for putting this together. Thanks to all the speakers, many of them actually, particularly from the US, very untimely, very, bizarre sort of times, very early in the morning or very late at night for them. And they really did not mind that, and they were here. And, for example, Professor Christian Gobel has been around, even after his talk is over, he has been attending on the sessions and so on. It's very nice. Thanks once again for having me as a part of this. I really enjoyed the program. I'm sure others enjoyed it. Thank you very much.
Yeah, thank you. I think I also request Professor Gautama, because he has attended all the talks yesterday and today also, and he came back at the last session. So Professor Gautama, what are your thoughts about these kind of formats and the symposium?
Yes, okay. Yeah, yes, I participated. I'm unable to put up my video, but audio is fine. I'm working.
Yeah, go ahead.
Yeah, I attended yesterday's full sessions, all the sessions. Today I had my lab part running from 3 o'clock to 6:30. So that period I missed. Otherwise, I was been attending. It was a very nice program. And we should get exposed to what is the happening and the challenges, and at that sort of work, when we see, we get a feel the real challenges of doing microscopy, in situ microscopy, whether it is at atomic scale or a little bit coarser scale when we are doing even SEM, in situ experiments, what are the real challenges and micromechanics? We have to get to appreciate that, get a feel of that. And it is really exciting to see those sort of work. Then that will naturally bring in some rigor of whatever work we are doing. Okay, maybe we are doing a routine microscopy, but when we see the sort of things at what level microscope can handle, then we can always just do whatever with that sort of effort to make it a neat and perfect job. We will keep doing. That is what is we can learn as researchers, users of the microscope. So that way, this was a very nice effort, and it has advantage that people can just pitch in and just make that time and share with us. When we actually hold conferences, unless they're available to travel, they will not be able to participate. Here is an occasion where as long as they're able to give us that 2-3 hours, making some efforts to carve out that time in their schedules, they will always be able to do that. People enjoy doing that because they also want to exchange their work with others. So that way, this was a very nice idea. This has come through. Similar these things we can plan, and some of the concepts we can just make it periodic. Maybe every 2 years we conduct on some concept. Already we had been running some of those sort of exercise in other, see, microtexture thing. Anyway, Bombay IIT, they have been doing periodically every 2 years or so. At IISc, again, another that sort of periodic event on mechanical behavior or something. They were every 2 years or so they have been doing. Similarly, maybe we can visualize of repeating about in situ studies after every 2 years, and some organization organizes it, some institution organizes it, and that will be a nice thing. At latest at that year, that time, what is happening, we can get a feel of that. Yeah, it was very nice. I enjoyed.
Thank you. So, Professor Christian, are you there? Professor Christian? Hello, Professor Kugel, are you there? I don't see his speaker getting on. Anyway, so we move ahead. I think one of the young people who attended this or presented this conference is Pavan. Pavan, he's here in the audience. So Pavan has attended all the talks yesterday also, today also. So Pavan, what is your thoughts about such kind of conference?
Oh, I mean, I really enjoyed it actually. I must thank both Chandra and you for doing such a nice job of, and almost no hiccups, right? And also I agree with what Professor Gautama was saying before, which is online mode is something that is going to be the future in my opinion. So I guess we should get used to it. And it's, although there are this trouble of people not seeing each other, I guess you have a lot of variety of people from different parts of the world joining and sharing their expertise and knowledge with all of us. So that's the advantage of online mode. So I guess, and also you have other advantages like you save on pollution and other things. So this is something that we should look forward to. And I think everything that
one good thing that has come out of the pandemic is this.
Correct. Yeah. So that's yeah. In general, it was a very high quality conference, and I'm very impressed by all the talks that I've attended. So that's very nice. And I hope the students and whoever is attending has learned quite a bit from this conference.
Yeah, thank you. So we have Sanjay Vidya. One of the important things Chandrasekhar wanted to bring from the beginning, that the industry people should come and present their take on the different kinds of in situ techniques, and we made sure that all are represented. So in the limited time period we had, And as Professor Visanga said that because of time differences, some of them could manage and some of them could not manage also. So I request Sanjay, you're there, right? Sanjay?
Yes, I'm here. I'm here.
Yeah, yeah. So what is your take on this? I know you have you're busy, but can you spend a few minutes on
Sure,
that?
sure. First of all, I think we all should congratulate you and Dr. Chandra. This was a fantastic concept that you came up with, and I'm very happy to be a small part of this entire program. And the best part is that even at the fag end of the program, generally we see during the conferences towards the end, the attendance starts dropping, but the consistency or the interest was maintained. And personally, I was very happy. And I can assure you that my principals, both of them, were very happy to come and join. I sincerely hope that we can continue such things. And I also assure you on part of industry that we will support such events in future. Thank you very much. Thank you very much.
Thank you, Sanjay. So we have some audience, and one of them are actually one of our students from IIT Kanpur, Subhasis. Subhasis, are you there in this audience? Hello? Subhasis? Very difficult to know who is there, who is not there. Hello, Subhasis?
I just got Subhashis into the panel. Now he can unmute. Subhashis, you can unmute.
Subhasis, you can unmute and speak. Hello? Maybe he's somewhere else. Okay, so
Subhasis unmute. Subhasis unmute. He's there. He's seen but not unmuted. Okay, all right. Yeah.
It's okay.
Yeah. Okay, so I just hand over to Chandrasekhar if you want to speak few things, and we have to thank some of the important aspects, because it was not me and Chandrasekhar who worked hard. A lot of people worked hard behind this event. So we'll do that, but before that, I just hand over to Chandrasekhar. He will like to speak things, or he may allow someone to speak.
No, I think everyone has said. If anyone has a feedback, and I'm sure this online thing, it started, and as Pawan was also telling, it's going to evolve, and I'm sure people are going to get used to it more often, and maybe some of these kind of focus meeting we can have online. And as Professor Gautama already said, maybe we can start making a point that, okay, once in a while, we make sure we have a meeting. And there are several things came out of panel discussion, and also, some of the experts, they suggested that it's, the conferences like this is not just to come and listen the talk. The success of this conference will also be measured once we start seeing people started or trying to make attempt to work. And there are some of the people already doing fantastic, and hope we get some more resources from funding agency and help from company, and we'll be able to start doing rigorous and detailed and some of the cutting edge in situ experiment all across the country. Having said that, as a students, or I'll request the students, to keep their thoughts and start understanding and try to see if, because at the end of the day, most of the research depends on the exciting students, and that, they are the future, or the research community which is going to carry out most of the experiment. I hope some of them will get excited about it and try to come up and say that they want to do in situ microscopy. They are ready to invest at least 3 years of dedication to do these things, and they are ready with the failure of the sample, or these rigorous in situ challenges what is there. And then we hope in India we'll be able to start some of the nice, or we'll make an attempt to solve some of the problems in material science, or in general in any one of the science field. With that, I'll give it to Kishan.
Yeah. So thank you, Chandrasekhar. So just to let you know that this workshop came into my mind in my month of May, and basically my wife was ill because of COVID, and mentally I was also ill. But in the back of my mind, I was thinking of doing something, because the boredom was too much. Although COVID went away from our family, but the boredom was too much. Then I immediately called Chandrasekhar, and then we started making a plan. And so the people who we must thank is EMSI. EMSI actually immediately came up and they approved our proposal, and then we could make the contact with the speakers. But to make the contacts with the speakers, we had a lot of problems with the foreign speakers because we didn't have much time to do that. And in that time, we had a meeting with myself, Chandrasekhar, with Professor Ravi Shankar here, along with Professor P.V. Sattam and Professor Kamini Chattopadhyay. And let me tell you that Professor Ravi and Professor Sattam immediately wrote emails to bring Professor Thomas Atlantis and also this Professor Kubal, and also Japanese speaker yesterday we heard Professor Ushima. So we could get all of them within a day or two actually. So thanks to them, thanks to Professor Ravi, Professor Satyam, and Professor Casey. And the idea of panel discussion was originally there with Chandrasekhar, and then we had some discussion with Professor Casey, and we then thanked him for his thoughts and ideas, although he's not there here today in this audience. But to bring GST, DRDO, and BRS persons for the funding and other issues, it was his things. So special thanks to Professor Casey. And we also like to thank the panelists, because yesterday many panelists were very busy. As I know, even Milind had basically came from after a very disaster. Some of his relative expired, and he went to cremate the cremation ground, and he came back from there. So, but he made his mind to be there at the time. And Professor Murthy, who was very busy, but still he could join. Professor Banerjee, who could also speak and give us a guideline. So special thanks to them. I will also like to thank all the funding agencies, especially the industries, the Cat and Amitech, Den Solutions, the Photochip, and Geol. They just told that we are there with you. So special thanks to them. And obviously, I should also thank all the speakers, because they came up with nice presentations, and students who made who submitted abstract for the posters and made the presentations, and they were there all throughout this conference to attend many of the talks. Thanks to them. And the head of the departments of our material science engineering at IIT Kanpur and the materials and metallurgy engineering at IIT Kharagpur, they also helped a lot in giving various ideas. And the most importantly, the website was created and maintained by one of our staff members at IIT Kanpur, Govind Bhatia. He is not here. Many of you have written me email that website looks very good, cool, and it is his completely his job, and we could do it in a month's time. So the kind of expertise he developed. And another person who helped a lot is one of my staff members, Budvir Singh. You could see him, he's there already logged in, but he may not be here in the audience. So they helped a lot. So I like to thank them from bottom of my heart to organize this kind of things in a short time. In a couple of months' time, we prepared and made it happen. And lastly, I thank all the audience for the questions and many of the interactions happened. So anything else, Chandrasekhar, anybody else you missed out to thank?
Chair session. So, session chair, right? So that was one of the best part, because in general, it's, that's one of the toughest jobs to keep things on time. So all the chair session, they were really fabulous. They made sure that things happen on time, and they were always considerate to have question answer as well. So we are really thankful to all the chair sessions. Started with Rahul Mitra, Raghavendra Tiwari, Ravi Shankar, P.V. Satyam, and all of them. For the industry, we had Amit and Professor Kumar, and the previous day we had a few more people. So all the session chair, they were really
nice, and they accepted to do it on the last moment, and they keep everything in order. So special thanks to them as well. Yeah, Krishanda.
Yeah, so that's it. So from our side, hope you have.
Yeah, so thanks once again, Krishanu and Chandrasekhar. 3 cheers. Well done. And we hope we have more meetings in the future.
Yeah.
Thanks all.
Thank you.
Thank you.
Okay.
Good night.
Good night.
Good night.
Thank you.
Good night.
Thank you, everybody. Very
Good
nice
night and thank you
conference.
to all.
Yeah.
Good night, everyone. Thank you very much.
Good night. Thank you. Thanks, Thomas. Bye.
Bye.
Okay. Good night. And thanks a lot for organizing such a great conference.
Yeah. Thank you, Professor Christian.